sind meine Haare? Wo sind meine Haare? Okay, good morning everybody. Good morning all the contributors that are here with us at Zentrum Paul Klee in Bern. Good morning to everybody who joined us online. I hope you had a good day yesterday and you were inspired to contribute even more to today's Symposium Day. We have quite a dense program, so I don't want to take up too much time. However, I really want to encourage you that are here in the Zentrum Paul Klee, as well as you that are online, to interact with questions and make use of the slot that we have, Meet the Speakers, where you can interact with the speakers in Gather Town. Please note, for you that are following us via live stream, that there is a slight delay between what we have here as live and what you may experience on your screen. So that means it might be good to pose your questions that you have to the speakers as you go along, and not wait until the end of the talks. So with that, I hand over to Michelle to introduce our first international keynote speaker.
Thank you, Andrea. And good morning also from my side. The sun is already up, so this perfectly fits with our energy balance session today, this morning. But of course, radiation is not the only variable that matters. We are honored to have Karina von Schuckmann with us today, and she will open this energy balance session with her keynote address. She is an oceanographer specialized in ocean climate monitoring at the Mercator Océan in Toulouse. She was lead author of the IPCC special report on the ocean and the cryosphere in a changing climate, and a specialist in physical Earth energy budget studies. So please, Karina, the floor is yours.
Thank you very much. Thank you very much for the opportunity to provide you an overview on the Earth energy balance and the remaining challenges that I want to present today. So I'm starting with a general introduction that the Earth's energy budget is determined by the main flows of energy into and out of the Earth system. So the state, variability, and the change of the climate are to a large extent driven by the energy transfer between the different components of the Earth system. And so the flows can alter clouds, weather, and external and internal variations. Forcing can alter the Earth's energy imbalance at the top of the atmosphere. And those can take place over periods of days to several decades. So the Earth's energy balance is one of the most fundamental conditions for making planet Earth conducive to sustaining life. So how does the Earth's energy balance changes and is taking place at the top of the atmosphere? So the perturbations of the equilibrium Earth's energy budgets arise from internal or external climate variations, as stated before. They can create either a positive or a negative Earth energy imbalance, manifested as radiative flux imbalance at the top of the atmosphere. So how can those changes and the variations of the Earth's energy budget are determined on how the energy flows govern the climate response to radiative forcing? So changes in atmospheric compositions and also in the land use, for example, anthropogenic greenhouse gases, can affect the climate through the perturbations to the Earth's top of the atmosphere energy budget. And the question on how the climate system responds to a given forcing is determined by the climate feedbacks, which in turn are associated by physical, biogeochemical, and also biogeophysical processes. So another statement to be made here is understanding of the changes in the Earth's energy flows helps understanding of the main physical processes driving climate variability and climate change. So how do these changes are driven by different climate forcing? So this is an overview provided from the last R6 IPCC assessment report in chapter 2, leading to variations in the Earth's energy imbalances and changes. How can those changes be induced? Some major examples included here and distinguish between the scales of change from subseasonal to decadal scales. Is climate variability as internal forcer, which can lead to either positive or negative Earth energy imbalance. Those can include, for example, El Niño Southern Oscillation, Pacific Decadal Oscillation, etc. Large volcanic eruptions, which would lead to a negative Earth energy imbalance. And at decadal and longer time scales, these changes can be induced by either changes in solar output, for positive and negative changes, Milankovitch cycle on a very long time scales, also positive and negative changes, and human-induced changes, which lead to a positive Earth energy imbalance. So where do we are today? So this is the current status of what has been assessed in the last IPCC report, with the statement that human-caused net positive radiative forcing causes an accumulation of additional energy, heating, in the climate system. So this is an estimate here on the left-hand side on the radiative forcing, the function of accumulated energy change, and the heat inventory for the past decades. And you can clearly see that there is an accumulation of heat with different contributions from the different Earth system storage components like the ocean, the majority, the ice, land, and the atmosphere. So these are different estimates to just provide you an idea on what has been published independently from different approaches and determining either direct measurements at the top of the atmosphere or by the inventory of the heat stored in the Earth system. And this is a study which had been established under GCOS. One of the results, and I've added here in green the recent results from IPCC R6. You can see that there is an estimate and that there is a change of the Earth energy imbalance over time as consistently estimated from different publications. So, and these are the different contributions to precise. So the ocean heat uptake is by far the major contribution, and followed by land, so which is the second largest heat storage component, melting of ice, and warming of the atmosphere. So these are these different numbers for different periods obtained, and I've also added the numbers which have been obtained by the calculation done in IPCC R6, and ranging for the ocean of about 90%, for land about 5%, the cryosphere about 3%, and the atmosphere 1 to 2%, depending on the period and estimate. So I want to go and navigate through the different topics on the Earth energy balance through the different methodologies on how to monitor and how to evaluate the Earth energy balance by considering 4 different types. So the first is the evaluation of the Earth's surface budget, then the radiation at the top of the atmosphere, through the heat inventory, and the climate models, particularly for which fundamental test line for climate models and their projections. So I will start with the Earth surface budget. Provided here is an estimate of the current state of the energy cycle at the Earth's surface as provided by different studies, particularly from the study on the so-called NASA News by Legria et al. 2015 and updated from recent from the Cirrus group at NASA, from Norman Loeb and Seiji Kato. And these are the results and for the different radiative and turbulent fluxes, and providing different estimates. What I wanted to mention here is that when the surface budget is not constrained by the Earth's energy imbalance, there are different biases which exist, and so the Earth's energy budget does not balance, and leading to differences depending on the estimate of ranging between 10 to 20 watt per meter square. So this is an example on a constraint approach, where you can see that there had been constraints provided for different Earth energy imbalance values from 0.6 to 0.8 watt per meter square, and providing a different constraint for the different estimates. And there are several groups which are working on those estimates. So these are some recommendations which are particularly based on a discussion, breakout discussion under GCOS, which had been taken 2 years ago. And so this is the outcomes say that the global mean energy balance at the Earth's surface estimates of the current state of the energy cycle are subject of vigorous research for more than a century. And so the center of accurate observationally based benchmarks of energy flows to evaluate and refine the model physics. So the satellite observations of improved calibration and increased spatial and temporal resolution, and they have played a central role in refining the reconstructions of the Earth's energy balance at the surface. And there's also a growing network of surface-based measurements which has provided substantially better constraints for the evaluation of the Earth's surface budget. And there are improvements in the global atmospheric reanalysis through both increased resolution and the ability to assimilate extensive ground-based and satellite observations. So together, those efforts have led to major advances and which have enabled new reconstructions and the development of constraints by combining different tools. So in situ observations, remote satellite data sets, and also reanalysis systems. So the way forward had been and should be in the future to bring together complementary expertise and data sets to provide a comprehensive view of the Earth's surface energy budget. So something which had been done, for example, under Northern News, for example. So the key issues remaining here is to improve the uncertainty understanding of the 10 to 15 or 20 watt per meter square of global surface energy balance residual. So, for example, reduce uncertainties in the surface fluxes by reducing uncertainties in the near-surface properties, like for temperature, water vapor, and wind speed. To investigate the surface energy budget at smaller temporal and spatial scales, for example, going for subseasonal scales, but also to check, for example, the annual or the seasonal cycle, so something which has not yet been done so far. Address and specify accuracy and stability requirements, which can widely vary depending on the applications, so depending on what should be done, right, on long-term and global scale for climate change, but also to address regional aspects, and by the flux type, so radiative fluxes and also turbulent fluxes. And so particularly the in situ observing system and the surface data products play here a particular role. And though the horizontal energy transport to achieve regional energy budget closure for the regional energy budget approach is an approach which could be of high interest in order to achieve further advantage, particularly when regarding also the uncertainty understanding. So I just wanted to mention here for further reasoning that there continuous assessment and comparison are taking place under GWEX GDAP, a specific group, and they have also now included evaluation of the Earth's energy imbalance. Assessment, not evaluation. So now I want to go to the Earth's heat inventory. So just to remind, as I've presented before, that we have done a study, and this was taken with the first meeting taking place also here in Bern. It was at EC. And so the Earth's energy imbalance can be best estimated from the Earth's heat inventory, complemented by radiation measurements from space. So this is a statement which came out from this group. And so also here the approach is to collaborate, to combine multiple expertise, multiple types of measurements in an optimal way in order to estimate the Earth's energy imbalance and to cross-validate, and in order to evaluate the status of global climate change and related uncertainties of our estimates. So, so we have done under GCOS a study which was called the Earth Heat Inventory, where does the energy go? And this was a collaboration, a huge collaboration from a multidisciplinary international team addressing the heat storage evaluations for the different Earth system components done for land, and which there had been an estimate for the heat available to warm land from borehole temperature measurements. Then also the atmospheric heat storage, been evaluated by a combination using of atmospheric reanalysis and remote sensing data, the ocean heat content, estimates from in situ data, and heat available to melt ice, with every estimate in terms of how much heat is available to melt the cryosphere part, with the different components. So I apologize, there's one slide missing, and the slide is there had been, beside the evaluation, also community-based observing system recommendation provided for the different Earth system components. So the one is for land, that there is a call for a global monitoring program for land temperature, for a continued and consistent or current estimate for the continental heat gain, and with a particular focus on such a program for the pool sampling of the borehole data in Africa, South America, and also in the Arctic area. The recommendations for the atmosphere were going for the sustainability and also the enhancing of the atmospheric long-term monitoring. For the cryosphere, there was a longer list, which was first a sustained remote sensing for all cryosphere components, but also for sea ice that both are needed, thickness and the albedo measurements for sea ice, for the evaluation of the heat storage or heat available in the cryosphere. Then for ice sheets and glaciers, it's important to have information on ice thickness and density. And also one statement which has been provided for the cryosphere, but is valid for all components, is that there is a continuous need of cross-calibration from in situ data and remote sensing data. And then for the ocean, there is a recommendation that there is a need of in filling gaps, measurement gaps in the deep ocean below 2,000 meter depths. Programs are under the way. And in marginal seas and shelf areas, and also in the areas polewards of 60 degrees latitude, also there are programs starting to evolve. So what are the results of this study? So it's a question, where does the energy go? So this is the evaluation we have obtained from this community work on the total heat gain of 358 zettajoule during a period starting in 1971 to 2018, with the contributions, as mentioned before, on for the different Earth system components. And by taking the rate of change of time of this inventory, we obtain two values for the Earth energy imbalance. First, for the longer period of about 0.5 watt per meter square, and for the most recent period, starting from 2010 to 2018, we obtain a value which is about 0.9, so almost a doubling of the Earth's energy imbalance. So other recommendations coming out from the study was that the various phases and impacts of the observed climate change arise due to the positive Earth energy imbalance, and which thus represents a crucial measure of the rate of climate change. And so the Earth's energy imbalance is the portion of the forcing that the Earth has not yet been responded to. And it provides us, and I would like to repeat the statement as highlighted from James Hansen, provides us an information how much heat is still in the pipeline. So this Earth's energy imbalance is the most critical number defining the proposed prospects for continued global warming and climate change. So the simple number, the Earth's energy imbalance, is very critical to be known by the scientific community and the public, in order as it provides us also a measure of how well the world is doing in the task of bringing climate change under control. So just a summary on the major recommendations from this work is that there is a continued qualification and reduced uncertainty in the Earth's heat inventory necessary, and they can be best achieved through the maintenance of current global climate observing system and its extensions in areas of gaps of sampling. And a specific call, again, to repeat, was the call for a global monitoring program for the land components, and also to establish an international framework for concerted multidisciplinary research on the Earth's heat inventory to assure a gateway in order to establish those multidisciplinary international exchanges. So further unravel the underlying uncertainties, identify buyers, and further advance on the observing system recommendations, aiming to fill critical measurement gaps, to foster multi-product approaches and physical budget constraints, advance on the role and external variability. So I would like to go now to the constraint. So I think I have to speed up a bit. So now we have this is a constraint between the top of the atmosphere evaluations and the Earth's heat inventory. So there's change in the top of the atmosphere net variation and rate of global ocean heat storage from independent global climate observing systems should be in phase and in the same magnitude to annual and longer timescales. So I will continue a bit faster. And so what has been done here is to benefit from the availability of the global climate observing system, which include, for example, the in situ measurements starting in the 50s and with the best estimate of the implementation of the ARGO measurement started in the year 2000 and which has achieved global coverage in near global coverage in the year 2005, the targeted one between 60 degrees north and 60 degrees south. The availability of altimetry measurements provide an indirect estimate of ocean warming. The series for the colorimetry for ocean mass evaluation and this top of the atmosphere measurements starting in the year 2000. So what has been done is to benefit from the Earth's energy imbalance on the physical budget constraint, which is a fundamental tool for the evaluation of the Earth's energy imbalance and its uncertainties from the underlying GCOS components. So these are some examples here for the most recent one from Leopard et al., providing a nice demonstration on how this constraint fits between these independent observing systems. You can see in red the direct measurements from remote sensing at the top of the atmosphere, and in blue the planetary heat update, so uptake with a specific ocean heat content product, and the other components from the GCOS paper. On the right hand, the results for heat content from GCOS. And there had been many advancements, and I have not time, it would fill also 30 minutes in order to explain how powerful the use of this budget constraint was and how it advanced our evaluation, particularly on the evaluation of the uncertainties. But I want to come back to a point I already mentioned, is that there is an increase in the Earth's energy imbalance over the past decade. So, yes. So what we have seen here on the left-hand side is also an outcome from GCOS. So it's a rate of change for different periods and for different depth layers and for the ocean warming, and provides you an information that the ocean warming might have reached record values for the closest periods, like for example 2010-2018, as I've mentioned earlier. There are also other studies here, I want most recent studies, which also state the same information, that there is an increase, an almost doubling of the Earth's energy imbalance over the past years or decade. And so to be roughly, so this, for example, the Loeb et al. Also stating that there is an increase, and with an explanation and discussion that clouds, but also an increase in greenhouse gases and water vapor are one of the factors which might have induced this change. Then this is the Kramer et al. Study is a study which is based on the flux components, also from the series measurements, and also providing here information on radiative forcing, and their increase is linked to radiative greenhouse gases, well-mixed greenhouse gases, and aerosol emission changes, which could explain this. Then there's a study from a long-term reconstructed Earth energy imbalance. It's an update so it's an update from an earlier study, and so it's increase of also of 0.6, and also there is a mixture of, they are discussing the redistribution of heat as a major factor for changes in the Earth's energy imbalance. So there are different results which just should demonstrate that there's still an open question and a very important question. And there's another study I would like in this context quickly go through, is on the paleo perspective of the Earth's energy imbalance. So I will not have time to detail, but I invite you to read the paper. But they have provided also an indication on the changes of the Earth's energy imbalance, and particular peaks of those changes had been linked to ocean circulation changes. So it's also another piece to understand on whether and how are the internal variation, particularly for the ocean, could account for such strong changes. So climate models, I will go quickly. Just these are two studies which have evaluated for CMIP5, but also for CMIC6, the different budgets. So just very quickly, because I'm already late, I apologize. There you have, what I wanted to demonstrate here is the importance to have the observations as a validation threshold for this climate model elevation. So here we have seen the Earth heat inventory in CMIP5 historical simulations. From a person which has auto-contributed GCOS study. And what they show is that in comparison with recent observations, the CMIP5 ensemble overestimates the ocean heat content and underestimates the continental and cryosphere heat storage components. And so these are the results and which have been mostly attained. So what have they used here are the results from our GCOS study and also the earlier study based on observations from Church in 2011. And this is a result from WILD on global energy balance components in terms of for the evaluating and comparing the observations also with the radiation components from CMIP6. So they show that there is a better agreement with recent estimates compared to earlier model generations, but particularly for shortwave clear sky budget evaluations. So, but still there are substantial biases and spreads in the model, and however that CMIP6 has these improvements and so should be served as downstream compensated by an underestimation of the downward long wave radiation in terms of a discussion which is linked to the multi-model mean here. So these are my key messages. So the first is I would like to pull back the main messages why we should care on the Earth's energy balance approaches and further understand the uncertainties and remove them. So the Earth's energy balance is one of the most fundamental conditions for making planet Earth conducive to sustaining life. So understanding the changes of the Earth's energy flows helps understanding of the main physical processes driving climate variability and change. The Earth's energy imbalance is the most critical metric that the scientific community and public must be aware of as a measure for prospect for continued global climate warming and change, and as a measure of how well the world is doing in the task of bringing climate change under control. And the Earth's energy imbalance has increased over the past decade, and drivers for this change of anthropogenic and natural origin need further evaluation. So these are my final slides on the synthesis for future opportunities. So these are the advancements in uncertainty and understanding and specific accuracy and stability requirements for all energy budget approaches. A point I want to mention, something which has been raised by Sonia, to have also an evaluation in terms of the target developments and uncertainties in the GCOS framework, such as storage components, but also there are many derived parameters for the surface budget in terms of the fluxes, which are not directly measured. Then the further advances of observing system recommendations, fill critical measurement gaps, and maintain GCOS. Further advances on the simulation of the global energy balance, and investigations of different temporal and spatial scales through regional energy budget closure approaches, further advance on the role of planetary heat redistribution, and further foster multi-product approaches. Thank you very much for your attention.
Thank you very much, Karina, for this excellent overview on the energy balance. And I noticed that we could also have titled our session the Energy Imbalance Session for the next time. We have a few questions here. I'll start with a question from Martin Hölzle. He's asking, how do you see the altitudinal change of energy balance changes in mountain areas?
So the mountain areas is something which has not been really addressed in this component because, and this is one of the components we have written also, we need to further engage this community in order to add this to the evaluation of the cryosphere component. So this is one point of uncertainties and further needed advancements for the Earth's heat inventory.
Okay. Then I have another one from Jörg Clausen. He's asking, could you elaborate a bit more on the type of constraints imposed you mentioned at the beginning of your presentation? This seems like a critical element in gauging the overall imbalance that is driving climate change.
Yes, so as I said earlier, I did not, as a matter of time, edit all the immense and impressive results we have obtained by applying such a constrained approach, budget a constrained approach. And there are huge opportunities in order to advance in this sense. Also, the recommendation was to do this outside regional scale, but there is a need, and that's why I have added this here in the end, to have information on the lateral exchanges, so for the atmosphere, but also for the ocean, so on the transports, which is a huge uncertainty in terms of measurements and also derived from reanalysis. So it's also an important question, important topic, important opportunities with this approach, but still ongoing research topic.
I have another question coming from Luca Egli. He's asking, can you quantify how much heat from the ocean will be released to the atmosphere in future?
I mean, there are evaluations on the heat fluxes from the ocean into the atmosphere, of course. So there are climate model evaluations which have provided information. theoretical, you could link this also because this is the amount of heat, which is determining also the time scales. So adjusting the ocean in terms of the heat which is already stored in the system will take about several hundred of years or even longer. So the IPCC even has one highlight statement saying that because the ocean is warming and because the ocean is storing this accumulated heat in the ocean is making climate change irreversible.
A few more questions coming in. Let me take one last question coming from Laurent Vignier. Temperature is very easy to understand for the public. How much vulgarization effort is there to give easily understandable explanation of Earth energy imbalance and its meaning?
That's something we are trying since years, and I think the pioneer here is James Hansen, who also brought this in terms of discovering that there is an imbalance which has explained a bias in the model which has not fit the surface temperature increase. So yes, there's a lot of evaluation, a lot of activities, also collaboration with communication experts. I just had, for example, an interview with WWF, who are aiming to put this indicator forward and to help also with communication experts to bring this message further through. So there are a lot of activities going on because there's a more and more a perception that this is an essential measure we have to bring forward and to inform the public about it.
I just saw a very important question, so I take this time to also put this one in. It's coming from Sonja Seniviratne. Thanks for the great talk, Karina. What are the new observations that could help constrain best the Earth energy imbalance?
Yes, as I said, so there was this overall recommendation. Of course, the ocean, as I said, because it's a large component. But there are also the other components which need critical observation. So again, the land, for example, the question is coming from Sonja. So it's a second larger component, and so there had been recommendation that there is a need of increasing gaps in boreal data, for example, or the cryosphere, because although you might imagine that those numbers on the percentage are very small, but this 3% of the cryosphere is explaining the majority of global mean sea level rise, right? This 5% now, which had been upgraded from the new studies, is explaining all which is taking place in warming the land. The same for the atmosphere, this 1 to 2%, depending on the estimate, is explaining the changes which are taking place in terms of warming the atmosphere. So even in terms of an energy imbalance, that those values are small, they're huge. So all recommendations are important for all the components in order to assure that the monitoring and of climate change and its implications will be assured with best targeted uncertainty elimination.
Good, thank you very much, Karina.
Thank you also from my side, Karina. Let's move on to the first national speaker of the Energy Balance session. I welcome Martin Gisel of the Paul Scherrer Institute, PSI. Martin is part of and represents a strong Swiss aerosol research tradition. He's very active in the setup of the European Aerosol Clouds Trace Gases Research Infrastructure Network, ACTRIS. Today, Martin will talk about the GAW-CH contributions to constraining aerosol radiative impacts with in situ and remote sensing measurements. So we're looking forward to what you have to say, Martin.
Good morning, everybody online as well as here in the room. So it is my pleasure to present the GAW-related aerosol observation and research activities done by PSI and also PMOD WRC. Atmospheric aerosols have many different sources, natural ones, anthropogenic ones. Maybe somewhat less known is the secondary aerosol formation process where atmospheric oxidants transform volatile precursor gases to secondary particulate matter, which roughly contributes half of the aerosol. The image here is an artificial image, which is a synthesis of model simulations, observations, assimilated observations, and I think I kind of like it because it gives some impression of the challenges faced when one tries to quantify aerosol impacts. These are high variability in space and time of the aerosol, a large number of relevant chemical, physical, optical properties of the aerosols, and also the processes we deal with often happen on short spatial or small spatial and short time scales, sometimes non-linear. So this really makes it a challenge. In this talk, I'm mostly addressing in situ and remote sensing observations, which are tightly linked to infrastructures, and give some examples of process understanding. The main motivation behind the aerosol observations in GAW are driven by their climate impacts. Aerosols can cause climate impacts by or radiative forcing through interaction with solar radiation by scattering or absorbing solar radiation. They also can cause radiative forcing by aerosol cloud interactions when particles act as nuclei for cloud droplets or ice crystals, thereby modifying cloud albedo and further relevant cloud properties. The reasons why we care about the aerosols, one is that aerosols are accepted to cause a cooling effect, which partly masks the warming driven by greenhouse gases. And also important is that aerosols remain a main source of uncertainty in quantifying effective radiative forcing, which also propagates into predictions on future climate for given scenarios. At the Jungfrau Joch, we've been doing aerosol measurement of climate-relevant properties for 25 years now. And you may ask the question, is it worthwhile to add another 25 wiggles to these graphs? My answer is yes, it's worthwhile to do so because there's many things we can do with this type of measurements. One is, of course, trend analysis. Then we can use these data to characterize really the free tropospheric aerosol. We can look at plumes from different sources. We can do associated research on process understanding, or we can use the data set to benchmark model simulation results, or also try to validate parameterizations which are used in model simulations. The first example given here are trend analysis. Martin Kolokoen is our expert for trend analysis. And the example here looks at 10-year trends of single scattering albedo of aerosols. Single scattering albedo relates light absorption to light scattering by particles, so it tells us something about design, whether the particles have a cooling or warming effect. And the example from the Jungfrau Joch here shows that at around 2010, the trend of the aerosol SSA was increasing, then it flattened out, and now we see a decreasing trend. And this change of aerosol properties is driven by air quality motivated emission reductions, which change the amount and the properties of the aerosols. Martin also has done this analysis for data from a wide range of GAW stations which have sufficiently long records, and there are certain threatening aspects we can see here. For example, we find more stations which had a switch in trend from increasing to decreasing in SSA, or if we look at Asia and also Northern Europe, we see that stations which currently have an increasing trend in SSA. And an important aspect I'd like to emphasize is that this heterogeneity over time and in space really motivates the importance of having global coverage and also long-time records of such observations to really cover the different environments and changes that's happened on the emission side. Those living in Switzerland may remember 6th of February this year when an impressive dust cloud crossed the Alps, also passed by the Jungfrau Joch, where we observed record-breaking mass concentrations and light scattering coefficients. And the aspect I want to point out here is the graph provided by Florian Filipic here shows photovoltaic energy production in Germany on that day. In red is the forecast, and in green is the actual production. And the gap between forecast and production is as large as roughly 9,000 megawatt hours, so 1/3 of an atomic power plant on that day, which is quite impressive. And so Florian Filipic and his co-workers from WD and KIT, they tried to improve such forecasts by including aerosols in their models, including radiative impacts and feedback. And for that purpose, also the in situ characterization of aerosol properties in these plumes are useful for them. Oops. Another example, which we also heard yesterday, are wildfire plumes. They obviously cause strong local impacts, but they also cause aerosol plumes that can travel over long distance. Some of these plumes pass by the Jungfraujoch, and Benny Bremer had a look into such wildfire plumes passing by the Jungfraujoch between 2015 and 2019, and we found a number of roughly 10 plumes per year, which we can identify, quite considerable. The map shows where these plumes come from. So for the most part, they come from Europe, Iberian Peninsula, North America, some from North Africa, and occasionally from other locations. An interesting aspect is when Benny looked into the statistics of the aerosol properties in these plumes, he found that, here shown with the example of single scattering albedo again, he found that the plume-to-plume variability was actually surprisingly small. So it seems that the aging processes during transport lead to quite defined properties of the aerosol in these plumes, which should help to detect them via remote sensing or quantify their impacts. Atmospheric is a topic I'm strongly related in. So in Europe, when it comes to aerosol cloud and trace gas observations, the ATRIS research infrastructure plays an important role, and ATRIS is tightly linked to the GAW observations here in Switzerland and also most other European countries. The good news is that on European scale, the research infrastructure should be established by the end of this year or beginning next year. We are almost there. In Switzerland, we got funding for the current period, which really strengthened the research infrastructure landscape in Switzerland. And the GAW science project, they also helped in preparing the ground for ACTRIS Switzerland with projects given to PSA and also ETH Zurich. Now I'm switching hat and present aerosol remote sensing done by PMOD WRC on behalf of Stelios Katsadis and Julian Grubner. PMOD has been designated the World Radiation Center by a mutual recognition agreement between the International Bureau of Measures and WMO quite a while ago. One of the units of the World Radiation Center is WORC, the World Optical Depth Research and Calibration Center, which looks at aerosol optical depth, a parameter which directly relates to the columnar impact of aerosol on the radiation balance. The method of choice for ground-based AOD remote sensing when it comes to accuracy and stability are precision filter radiometers, in short PFRs, and PMOD WC has the task to maintain the primary calibration reference for AUD measurements done worldwide. So they operate the PFR triad as calibration reference. The calibration of this triad goes back to calibrations done at mountain sites, Mauna Loa and Isonia using the Langley approach, and the accuracy or uncertainty is on the level of 0.01 in AOD absolute, which is very impressive for aerosol measurements. The work also supports GAW and GCOS in many aspects, so PMOD is involved in scientific advisory groups and expert teams, and thereby they also support GCOS by reviewing requirements for measurements. And of course, they develop quality assurance and quality control procedures to ensure homogeneous data sets over time and around the globe. One way of transferring the calibrations from the triad into the different stations are comparison workshops, which are done on a regular basis. The figure here shows results where 13 instruments were pulled together in the last comparison, and the key message and the success is that essentially all markers fall within the quality band defined by WMO to have good homogeneity. Work is also involved in the ACTRIS Calibration Center for Aerosol Remote Sensing, with the goal to relate all the AOD measurements done within the ACTRIS network to the primary WMO AOD reference. And the way this is done is that PMOD puts transfer standards to the main ACTRIS calibration sites. And the figure here in the end again shows that the comparison between the calibration standard and the ACTRIS main calibration standard again agrees within the required quality limits. The Langley-based approach of AOD calibration is not SI traceable. So it has high quality, but it's a current activity trying to link this to SI traceable measurements. For this purpose, it needs absolute calibration of the filter radiometer detectors, and it needs satellite-based extraterrestrial solar irradiance measurements. So in this project, what they did for this graph, they calibrated PFR traditionally with the PFR triad transfer calibration, or with SI traceable calibrations, and there we get different results because different satellites have some different measurements. But again, all the markers from the two methods fall within the shading, which is the WMO limit, which means the SI traceable method and the traditional method, they again are consistent within the required quality limits. Work operates PFR instruments at GAW stations around the globe, sometimes on their own and with associated partners, and they make sure that these instruments are upgraded and replaced. And the one key aspect of this method is that it is very stable also over time. So it's the method of choice for trend analysis. And this network also is important, for example, for ground truthing of satellite-based AOD measurements. Last but not least, PMOD also has two GCOS Switzerland funded projects. In one of them, they take existing long-time data sets and reprocess them, including the calibrations, to really ensure high consistency over time for the purpose of accurate trend analysis. In a second project, they develop a web interface for these high-quality AOD data sets with the goal to really make them available for science and also to disseminate results to the general public. Switching briefly back to our work at Jungfrau Joch, we also address aerosol cloud interactions in several experiments, and in this specific example, we look at aerosol cloud droplet number. The bottom axis of the figure shows droplet number from in situ observation, and the vertical axis shows predicted droplet number, where we use the parameterization and fed the parameterization with observed aerosol size distribution, composition, and updraft, which is the driving force behind cloud formation. The good agreement we find here in the end shows that this parameterization, which is used in global model, performs well for real clouds in the atmosphere. So this brings me to conclusions and outlook, and maybe besides the importance of GAW, GCOS contributions and infrastructures, I'd like to point out the open data effort, which has really induced massive changes. So considerable efforts currently go in establishing near real data chains all the way from the observations into CAMS modeling services and resulting products, which I'm optimistic that this will cause some substantial change or boost the use of the data we have. Where are we going in the future? I assume for the aerosol we are going to move away from just mean global climate radiative forcing, but probably the regional effects or short-term effects there, including aerosol in a dynamic way there, we are looking forward to see to what extent this improves understanding and accuracy. And certainly integration is important. This is across environmental domains, for example, atmosphere, cryosphere links, but it is also about integration of different approaches like modeling, in situ measurements, remote sensing, ground-based, satellite-based. With this, I'd like to thank you for your attention.
Thank you very much, Martin. We have a couple of questions. The first one coming from Tom Peter, ETH Zurich. He says, the aerosol trends over the past 15 or so years are very interesting. Can you say a bit more about the cause?
Yeah, I mean, I said air quality is the main driver behind it because we know aerosol also have adverse health effects. So a lot of effort is put in to reduce emissions from engines, which causes, for example, particle filters in diesel engine, which causes a decrease in light-absorbing aerosol. Then we have acid rain was a topic, so the sulfur was taken out of fuels and still being taken out on the ship side, which causes a decrease in, or in those places where it was done, it causes a decrease in sulfate component of aerosol. So these are some examples where work is done, but then there is of course also trade-off at some point. So switching from fossil fuel to wood burning as an energy source, which is good from the climate perspective, may be an issue from an air quality perspective. So sometimes we also have competing decisions there.
Julian Gröbner of the PMOD WRC, he asks, did you find striking differences in the aerosol transported across the Atlantic from the Californian fires?
So the trend we haven't yet looked at. So as you saw, we looked at the data sets from 2015 to 2019, and this is just too short to have to say something about trends. And probably satellite-based fire data are maybe much more useful to assess trends. I think if we would want to do trends from in situ observations, we need longer records and bigger spatial coverage because in the end only some of the plumes hit the Jungfrau. So one site there is not enough. Yeah.
Not quite sure whether he meant trends or talked about differences in general. He's talking about the US California forest fires and aerosols that seem to be transported.
I mean, we find them quite regularly. And maybe one interesting aspect there is that it's also good to detect these plumes on a different continent because we also have with colleagues from Mainz, we have a study ongoing where it looks like at the Atos site, the models are getting plumes from the Amazon region very well, but there are also many plumes coming from Africa, and the models don't get these. So it's when getting the aerosol loading right, one needs to get the sources, but one also needs to get transport and removal right. So I think from that point of view, that's a very interesting or important aspect of detecting plumes on a different continent.
Okay. So excellent. Thank you very much, Martin. I hand now over to Michelle.
Yes. Thank you, Andrea. It is my pleasure now actually to introduce Julian Gröbner as our next speaker. Julian Gröbner is working at the Physikalisch-Meteorologisches Observatorium Davos and the World Radiation Center. This institute combines several contributions to the central facilities of GAW and WMO. Therein, Julian is responsible for the World Calibration Centers for UV, infrared, and the atmospheric optical depth, which we actually heard of just before. So Julian, please take the floor.
Thank you, Michelle. Thank you, Andrea. Thank you to those present and to those online. I will give a presentation on, the title was given to me, on radiation balance measurements from the surface and space. And I've added a subtitle to that, from a metrologist's perspective, because my talk will be not so much about radiation balance results and the impact of these radiation balance measurements on the Earth energy budget, but more about the challenges that we have in producing these data sets and these measurements. So briefly, the contents of my talk, I will be talking about the radiation balance status, about the figures that Martin Wild and his colleagues have produced that have been used in the most recent IPCC assessments. I'll go slightly into the top of the atmosphere solar irradiance measurements, where our institute is involved in. I'll talk about the ground-based measurements, and I'll discuss some of the challenges in producing these data sets and the related calibration activities that we perform at our institute. So I'll start off with this very well-known and quite famous Earth global radiation balance schematic produced by Martin Wild and his colleagues. You see the different radiation fluxes, the fluxes coming from the sun, which are on the left of this figure, and emitted infrared terrestrial radiation fluxes that are on the right of this figure. And when you combine this, and as Karina has discussed previously, you try to get a balance or an imbalance, depending if the radiation fluxes are summing up, or if there's some residue that either increases or decreases the radiation or the energy in the Earth system. And so you see these values, and all these values are quoted in watt per square meter, and it's actually global values of the Earth system. And you can imagine that these global values are quite difficult to obtain. You have to do averages over time, over seasons, to get these individual values. And you can see in brackets some of the uncertainties related to that. And it's really difficult to actually get these numbers. And so some of these values are obtained from measurements, a mixture between measurements and models. And this is actually the basis for the work that is being done to assess the Earth energy budget in terms of the radiation fluxes that are coming into the Earth system. I'll be focusing on a few of those. So we have the top of the atmosphere, the incoming energy from the sun, that is the driving force of the Earth's climate system. Clearly, there's no other energy input into the Earth that has the magnitude of the solar energy that is coming in every second. And I've shown just on the left a picture of one of our technicians that just shows that our institute has been involved in these measurements since the 1970s, so for 50 years or so, in producing measurements that have been on balloons initially, on rockets, and finally we are producing experiments on satellites to measure the incoming solar radiation. And and complementary to that, you can see on the surface there are some fluxes where we are also involved in. These are the surface fluxes for the energy that has penetrated through the atmosphere that is reaching the surface. And so you have the incoming solar radiation, you have the emitted terrestrial radiation, the re-emitted terrestrial radiation. So these are measurements for which we are also responsible for. So if I start off with this top of the atmosphere, incoming solar irradiance, you see here a figure that is quite famous. I've taken it from a presentation from Greg Kopp that he did quite recently this summer. And you see the whole climatology of the different measurements of solar irradiance done from space. And you see there's quite a large spread of this data, and the more consensus data the last 10, 15 years, where we have been able to find a common value for the incoming solar irradiance, which is at the moment at 1,361 watt with a small uncertainty. And there has been a lot of work to bring these measurements together, because as you can see, the instruments, each of them don't really agree with each other. And so it was quite a lot of work to bring that together. And this was mainly achieved by having overlapping measurements. So in that sense, the instruments by themselves are not able to give this information of the solar incoming radiation with sufficient information and uncertainty. There was a need to bring them all on a common scale, on a common relative scale. And so you see here the community consensus TCI, which I also took from Greg Kopp's presentation, where you can see that there has been now a consensus of how to produce a long-term time series of the incoming solar radiation with an uncertainty which now is estimated to be very, very low. So we are talking of 1/10 of a watt per square meter for this incoming solar radiation. But the big question still is a little bit about how is the absolute value. So we know the trends, we know how stable and how it changes over time. You can see this 11-year cycle, which is of the order of 1 watt per square meter, so it's really tiny, in fact. And the question is, how well do we know this absolute value? And so I'm just giving you the outlook for that. There has been increasingly work done on providing this type of, I will call it traceability, to measurements that are not only performed in laboratories or on the ground, but also to satellites. The name for that has become SITSATs, for SI traceable satellites. And I will just mention one of them where we are involved in. It's the satellite called TRUTH. TRUTH stands for Traceable Radiometry Underpinning Terrestrial and Helio Studies. It's led by the National Metrology Institute of the United Kingdom, and PL. We are a partner, and there are some additional partners that all together are trying to provide traceable measurements from space. And so this is not only the total solar irradiance, but there will also be some measurements done with spectral radiometry to produce the reflected radiation from the Earth in order to have the key inputs for this radiation energy budget of the Earth, with measurements that now will become traceable in the sense that you will know the uncertainties of these measurements to a very high degree. If I jump to the ground-based measurements, there are two major networks that are producing the ground-based measurements that go into the assessments that form the basis of these IPCC reports. I have shown here two. The one on the left is the baseline surface radiation network. It's operating around 70 stations, of which 50 are still operational. And on the right, you see a global energy balance archive that has been initiated by Atsumo Mura from DTH, that now is being taken care of by Martin Wild. And it's also supported by the GCOS program of Meteo Swiss. And these data are measured from the surface with tens, hundreds of different instruments. And so there you can see already the problematic that these measurements need to be homogenized, put on the same scale in order that if one makes averages, you produce something that is consistent with the other instruments. And so this is where I lead to the activities of our World Radiation Center. You have seen this slide before from Martin Giesel. Now I'm just focusing on the two different sections of our World Radiation Center. We have the solar radiometry section and the infrared radiometry section, which are responsible for these two major fluxes, the solar fluxes and the terrestrial long-wave fluxes. And briefly, just to show the history of these measurements that go back to the 1970s for the solar radiation, but only to the beginning of the year 2000, so not even 20 years ago for the infrared radiometry section, we can see that, for example, these radiation fluxes in the databases for the solar radiation measurements are fully traceable to our institute. So all of these different sites that measure solar radiation can all be traced back to the references that we have at our institute, while for the long-wave radiation measurements, we are still in the process of providing that traceability, especially backwards in time to historical data sets. And so there we have made an assessment, and a bit more than half of these stations are really fully traceable to our institute. If I go for briefly the work that is being currently done on the solar side of these fluxes, you probably all have heard of the World Standard Group that is being hosted at our institute that was created in the 1970s. That is actually an artifact-based reference. It's simply the average of several instruments, and the consensus is that this average then defines the solar irradiance in watt per square meter. And we have started a process more than 10 years ago to move from this artifact-based reference to a detector-based reference that will then be trying to produce an SI traceable measurement of solar irradiance based on a cryogenic solar absolute radiometer. And you can see in the middle of my slide some information that Wolfgang Finsterle, who is responsible for that work, has put together for me. You can see the history of the solar irradiance scales that start on the left at the turn of the last century, so in the 1900s, where the scale uncertainties were quite large, and you can see how it gets better and better. And the current consensus result for the solar irradiance scale is that it is very close to what we expect from the SI traceable measurements, with a slight offset of maybe 0.2%. So this is something that we will try to resolve in the next couple of years. For the long-wave irradiance, the traceability back to SI is slightly different, because we are talking of radiation fluxes that are thermal. They are of the order of, if you talk about temperature, of the order of ambient temperatures. And you can see the traceability chain on this figure. If I start on the right, these are the measurements performed in the networks. We have a set of transfer instruments that are being hosted and operated at our institute, and you end up in the laboratory. The realization of the watt per square meter scale for the long-wave irradiance is simply a black body where we know very well the temperature and its characteristics, and that is the realization of the watt per square meter in terms of long-wave irradiance. And all of this, of course, needs to be consistent in order to produce the Earth energy budget schematics that I've started with. The stability of this infrared standard group, I'll spend just a few minutes on this, is very high. You see on the top the time, the data set in time since the creation of this reference from 2004 to the present. And the stability is very high and very satisfactory. We have a 1 watt per square meter maximum variation of this, and it looks very stable. So in terms of tracking the stability, we are very good. The question is about the absolute scale again. And there you can see on the bottom some, I would say, recent results of the last couple of years that show that this seems to indicate that the long-wave infrared measurements that are being performed currently are of the order of 4 to 5 watts lower than what they should be. And I'll simply ask you just to remember that value of 4 watts per square meter. We have done some recent work to try to pin this down, and this is simply just showing you some work that we have been doing in some European projects with the German Metrology Institute, PTB. I've shown you that we realized the scale in Davos with our black body. We have recently been able to compare our black body with the black bodies from these national metrology institutes. I will simply jump to the conclusion. We have found perfect agreement between our two scale realizations. You can see the results on the right in this figure. The scale is 1 watt per square meter, the full scale of this figure, and you can see the agreement is within a few tenths of a watt per square meter. So we were very satisfied to see that, at least from the point of view of the scale realizations, we have a very good agreement between these different realizations. So how do we disseminate the scale to the world? We do that through international campaigns, comparisons. The international pyrheliometer comparisons, you can see them on the pictures, are very old. The initial campaigns, we didn't even have color pictures. They are in black and white. They were done in the beginning of the 50s. We have continuously held these campaigns every 5 years or so. There's been one exception, that was last year. We had to postpone the campaign to this year, and we will have the 13th International Pyrheliometer campaign starting in a week from now for 3 weeks. What happens is that institutes from all over the world come to our institute in Davos. They bring their own instruments. They run them in parallel to our references, and through comparisons between the references and these user instruments, we can transfer our reference calibrations to these institutes. And this is a way to homogenize measurements across the world. Back to the Earth's global energy balance, you can see these measurements. I have shown you how difficult it is and challenging is to get to these numbers. Let me focus just briefly on a comparison that was also done by Martin Wild in a recent paper on some of these fluxes. These are figures taken out from his publication, and you can see the variability of the models that have been used to make the CMIP6 assessment that has been also used in the most recent IPCC report. And the values are simply taken out from these bar charts. You can see that for the shortwave radiation, clear skies, so no cloud effects, the mean model values are around 245 watt per square meter, and the measurements 247 watt per square meter. So that seems to be very good agreement now between the models and the measurements when looking at a global average and when we simply take only clear sky results. For the long wave radiation, you can see the spread is much higher between the models. And if you look a bit more carefully, then you can see that over the course of the last years, the models have continuously increased their long wave irradiance that is being measured on the surface. And if you compare that to the measurements, they are between 314 watt per square meter and the model 318 watt per square meter. And it was really nice to see that this bias of 4 watt per square meter seems to be consistent with what we have seen in our laboratory calibrations, where we have seen that the WISG, who is producing the reference for the long wave irradiance, seems actually also to underestimate long wave radiation. So this gives a consistent picture. So I'm coming to my conclusions. Thank you for giving me this one more minute. I have tried to put it into the successes and the challenges. And I would say the biggest success in terms of radiation measurements is certainly that solar radiation at the top of the atmosphere is extremely well known. And there's a really good process put in place on a global level to assess this measurement also in the future. You have seen the efforts that are going into producing SI traceable measurements, not only on the surface, but also in space. And so very soon we will have also satellites in space that will be able to demonstrate their traceability to SI and therefore having consistent measurements that can be put together. The challenges are that, at least for the long wave radiation, we need to put this traceability into the networks, especially to historical data sets, to before the WISG was created. That's 2004. There are measurements from much, much earlier than that. And so we are involved in trying to produce this traceability. As I've just mentioned briefly, producing global means is really difficult. For that, we are needing to use the models. And as Martin has discussed in his publications, the spread among the models is still quite high, and so certainly there's a need to improve the models in that sense. And by that, I will finish my presentation. Thank you.
Thank you very much, Julian, for this perspective on radiation. Up to now, I see no questions on my pad, but I heard that Andrea has a question for you.
I'm very happy that. So coming back to Karina's keynote, where she says the Earth energy imbalance should be measured, maybe naive question would be, are the instruments that we have at our disposal fit for this purpose, and is it a matter of coverage, getting the right coverage, or do we further have to improve our measurement accuracy to reach the goal of quantifying the Earth energy imbalance?
Yeah, this is my personal, of course, opinion. But as Karina has shown, and as is shown on these figures that I have had of the Earth radiation budget, the imbalance that we see is of the order of 1 watt per square meter. And it's a global value. And I've tried to show that it is really difficult to get these global values and to get them to within 1 watt per square meter to resolve this with our radiation measurements. I think it's extremely challenging to be able to measure the outgoing fluxes to better than 1 watt per square meter, the ground-based fluxes to better than watt per square meter, to have averages that we can trust to within this 1 watt per square meter, and then make subtractions. It's very challenging. Yeah. So I'm really impressed that through using the global heat contents, you can get to this information.
Okay. Thanks.
We have one question coming from Martin Hölzle, and he's asking, on which altitude will be the top of atmosphere measured in general?
At which top of the atmosphere is measured?
On which altitude will be the top of atmosphere measured in general?
The top of the atmosphere is really meant to be outside of the atmosphere.
But this is which altitude, right?
Well, where satellites fly, I would say you can take the International Space Station. I think it's around, 400 or 700 kilometers? So this is where it's measured. So what you are trying to do is to produce a value that is not affected by the Earth atmosphere. And so you're measuring it outside of the atmosphere. And where exactly that is then not really relevant as long as you exactly know at which distance from the sun this was measured, and then you need to, again, homogenize it to a standard distance to the Earth-Sun distance of 1 atmospheric unit.
Good.
Okay.
Thank you, Julian, for this talk.
You're welcome.
So we have now scheduled a short break to stretch your legs or to take a health break, and it's scheduled for 10 minutes. We are running on a very slight delay, so we'll be back at 10:25. That's 8 minutes. Thank you.
Andrea, Sie sind bereit?
Hä? Ich sehe nichts. Nein, ist noch grün. Wart noch ein. Bin ich schon online? Aber es ist nicht rot. Hello? 1, 2. So, welcome back. Welcome back from this short break. We're very happy to have Ulrike Lohmann from ETHZ with us today. Ulrike and her group have substantially contributed to the GAW-CH on the complex subject of aerosol cloud interaction, including the development of measurement devices now almost continuously observing at the Jungfrau-Joch station. Consequently, her contribution to the symposium today is discussion on aerosol cloud interaction in orographic clouds, observations and simulations. Please, Ulrike.
Yeah, thanks a lot for the opportunity, and it's a pleasure now to do what Martin has introduced should be the next step. And the next step should be to look at short temporal events and to looking at things at a regional scale. And if you have to do with clouds, this is what obvious is what's important, because clouds vary on such small scales. So why are we interested in orographic clouds? If you're here in Switzerland, it's obvious, because orographic precipitation is crucial for freshwater resources, and also what Sonja showed convincingly, intense precipitation will become even more intense in a warmer climate. So what are the consequences? Consequences on the one hand that we'll have landslides, flash floods, avalanches, you name it. I have renamed the title to mixed phase clouds, and mixed phase clouds means that you have cloud droplets and ice crystals both in it. Why does it matter which phase the clouds consists of? If you look at this map, then you'll see that you have the light blue colors in the northern hemisphere, and that means that approximately half, 40–50% of all the precipitation that we have originates via the ice phase. So ice is crucial, and this is the element that we want to understand better. How do you do that? Well, there's different ways, but before I come there, I will go into the detailed mechanism that we will be studying, and this is called cedar-feeder mechanism, at least that we are studying in the topic that I'm discussing today. What you have is an upper layer cloud, schematically shown here, consisting of ice crystals, seeding cloud, and you see that there are some ice crystals sedimenting from it. If you know, for whatever reason, due to orographic uplift or so, produce just a normal cloud that by itself would just be hanging there. It could be that you have the ice crystals from above that fall into it will collide with the cloud droplets from the lower cloud, and so you form larger ice crystals or rimed ice crystals, and that will then lead to precipitation. And it has been estimated that there is precipitation enhancements of up to 20–50% by this effect. And it also has been estimated that the cedar-feeder process contributes to extreme precipitation. So we took the approach to conduct in situ studies. And why in situ? Well, if you have measurement in complex terrains, what do you want to do? You have mountain slopes, you have valleys. How do you access it? Of course, you can access it from satellites, but we have just heard surface energy budget is hard. Looking in detail into clouds is hard. Yes, there is satellites that have radars on it, but they have a reputation of like every 2 weeks or so, so you don't really get very far if you have a measurement point every 2 weeks. What you can do instead is being at research stations, and yes, we have been taking measurements at Jungfrau-Joch, although I will not discuss them today because I knew that they were discussed before. but I will look at different approaches. Aircraft is also a possibility, but aircraft in the mountains is dangerous, and you don't get into the valleys, so that's maybe also not the best. So what else? What we did is we have an holographic imager that I'll describe in a minute, and one thing we did first is to put it on a cable car, and then optimistically we thought we have the cable car going into the cloud and maybe at the top going out of the cloud. But that, for one, doesn't happen so often. And also, if you take a cable car in any touristy winter sport season, there's no tourist when there's bad weather. So we either could have sunny measurements, that's not so interesting, or the cable car just didn't run. So we reverted to what has been known in atmospheric science for a while. You can have a tethered balloon. Similar to what you see here, we have our own now. And we did have it in Davos for 2 months in 2019 in the wintertime. And if we zoom in, then you see it here. You see it's approximately 8 meters wide. We have a 1 kilometer long cable, so that's how high up we can go. And you see that below the balloon we have our measurements. The most important one for cloud measurements that we have here is our holographic cloud imager. And of course, we have next to it the meteorological instrument package. How does it work? Holography works that you emit a laser, you collimate it, so you have a parallel wave, you turn it, and then you have your reference wave. If you have obstacles, like cloud particles in the way, you produce a scattered wave, and then you get an interference pattern, and that you can reconstruct backwards and obtain cloud droplets and ice crystal images. So as shown here. And there you see that you have, especially on the small side, there's zillions of cloud droplets, only very few are shown. What you see from that is that we are limited in resolution. We can't detect anything that's smaller than 6 micrometer. And the other thing is that it's approximately, the particles have to be approximately larger than 25 microns to be detected as ice crystals, so that we can distinguish between ice crystals and cloud droplets. Okay, and if we reconstruct all the measurements that we have, we obtain size distributions. So here we see a typical size distribution, which, like a typical cloud, has many more cloud droplets, just because there are so many more aerosols that are able to act as cloud condensation nuclei, and very few that act as centers for ice crystals. And then we have ice crystal size distribution with much fewer concentrations and larger particles. Okay, so on to the case study. We have been, as I said, we were in the Davos area in February, March 2019. The day that we were looking at is in the free troposphere, we had prevailing westerly winds. And so there was a cloud there. And in addition to that, we had in the boundary layer winds coming from the northeast blowing up Wolfgang. And that helped due to lifting, forming a lower level cloud. So we had the setup that I showed before with the cedar cloud on top and the feeder cloud below. And the instrumentation that we had, Holy Balloon, quite there where the feeder cloud was. In addition, cloud radar, so that we see all the extent, we see into the cedar cloud as well. We have ice nucleating particle measurements, so that's the link to the aerosol. And we measured those both also in the valley near Davos Wolfgang and on top of the Weißflurjoch. Okay, and so let's first look into the cedar region. What's going on there? Which processes operate in a cloud like that? You see it here, typical radar picture. You know it from your smartphones when you're trying to avoid the next thunderstorm. The redder the color is, either the more particles you have or the larger they are. And then translated into heavier precipitation. And blue colors meaning either smaller particles or few of them. Okay, let's focus in this first 1.5 hours and blowing this up here. then we see that we have regions of enhanced radar reflectivity near cloud top. And that is where we think that the ice crystals form in the cloud. And those are, because you see it there at the top, that you have really high values of reflectivity there. Those are so-called generating cells. We have seen in the literature before that ice forms predominantly in those generating cells. As you see at the pictures in the lower panel there, that the solid blue line says the size distribution inside such a generating cell with larger crystals, many more larger crystals, than measurements that were taken between those cells. So those are the regions where we have turbulence, where we have high upwinds, where we can cool more, where we can produce ice crystals, and where they can grow larger. So those are important for precipitation formation. And so we were going more into detail and looking into how is the ice forming there. Okay, so the link to the aerosols, and those are also measurements that we are doing at Jungfraujoch, is to study primary ice nucleation. So having those solid aerosol particles like Sahara dust that Martin impressively showed, whenever we see a Sahara dust outbreak coming over Jungfraujoch, we find enhanced concentrations of ice nucleating particles. So those, as what you see here, are centers for ice crystals. We measured them at different temperatures on the Weißflurjoch, and then you see that their concentration is very strongly temperature dependent. So there's one in a cubic meter, so it's like looking for the needle in a haystack, literally. 1 in a cubic meter at -5, increasing by 2 orders of magnitude at -20, approximately to where cloud top is. And if you compare here the ice crystal number concentration to the number concentration of those ice nucleating particles, you see that for approximately 1.5 hours, there's a good agreement. And then it's easy. So we have one ice nucleating particle, one ice crystal. Fertig. Understood. But then later on, you see that there's higher ice crystal number concentrations, and there's no increase in the aerosols contributing to it. So this is not everything. What else can we do to try to understand what's going on? Well, if we look closer in those generating cells, well, they are of course higher in altitude, i.e. at colder temperature, and we saw the strong temperature dependence of the ice nucleating particles. So if we extrapolate our measurements to where the cloud overshoots to, this increases how many ice nucleating particles we have by a factor of almost 4. And so this gives you then the dashed line, and then there is a better agreement with the ice crystal number concentrations later on, but there remains a discrepancy. So aerosols is not everything to explain ice crystals. So there is something that we call secondary ice production. What is that? Well, secondary ice production is something that if you have an ice crystal that collides with something, it can splitter. That could happen. Or what could also, and yeah, something like that is pronounced if you have high levels of turbulence, and you see that here. You see indicated here near cloud top, there's rather high Doppler velocities indicative of updraft in that case, downdraft, both of them. And so there's lots of turbulence and more chance for collisions. And also, if you have higher updrafts, the cloud droplets or the ice crystals can grow larger. The other thing that can happen is droplet shattering. So imagine that you have a large cloud droplet and that starts to freeze. It tends to freeze from the outside, and then, because with ice having a lower density than water, then all of a sudden there's this pressure build up and you have the shell around it. So at one point, the cloud droplet will just burst and inject small crystals. That's a rather prominent mechanism that we also started to look at in more detail and found evidence for this mechanism to happen. Can we use our measurements to infer something like that? The importance of primary versus secondary ice formation? Yes, we can, because here is where holography comes in and where it's important to look at the shape of our crystals. And what you see here, as Fabiola, who did this study, highlighted, orange, with the orange circle, we have large and rimed particles. So you do have this scenario of an ice crystal falling through cloud droplets, and when they collide, then you form rime. But then there is the small pristine ice, very tiny one, that are encircled with this green color. And this is now the feeder region, the lower laying cloud. So those small particles could not have come from above. They must have formed there in situ. Now, the lower cloud is at -3. If we think of what the ice nucleating particle concentration is at -3, this is even less than 1 in a cubic meter. There's nothing. So definitely that can't be the process. And the number concentration of small ice crystals is a factor of 1,000 higher. Now, is this just one out of a blue moon scenario? No, it's not. Because we did look also in all the clouds that we observed during the case study. And what's shown here is the ice multiplication factor. So one would be if we had the same ice crystal number concentration as ice nucleating particle. And then in red, you see the average enhancement is a factor of 100. And the dashed line is a factor of 6,000. So there is on average in all the clouds that we have observed a large enhancement due to secondary ice production. Now, the last question, okay, I'll skip this, if I could, and come to the last slide on the modeling to see what impact that has on precipitation. So that we cannot observe anymore, this we need the model to infer it from. And the modeling studies that we conducted is one, a normal one, and one where when the ice crystals tried to enter the feeder cloud below, we omitted them, we took them out. And then we looked at what happened. And we could show for that case study that we simulated, it agrees with our theory. If you remove the seeding particles, you don't have the riming, and you have less precipitation, and you see that highlighted there, 0 minutes. Okay, take-home messages. We observed both the cedar feeder process and secondary ice formation during the Raclette study. And we could see that the cedar feeder process led to reduced precipitation at the surface, and also that secondary ice formation is something that is very common in almost all the cases that we have seen, increasing ice crystal number concentrations by at least a factor of 100. And in summary, the connection to GCOS and all the observing that you have seen so far is, this of course is not something related to trends, but this helps with the detailed understanding that we need to improve the models and also need to get closure between satellite data and in situ data to figure out what's going on. Thanks a lot for your attention.
Thank you very much, Ulrike. Any questions from the audience here? I have no written questions so far, so I take the opportunity and ask you the microphysical schemes that you need in these simulations. Are they particularly heavy, or are you able to do it with current day operational schemes?
No, you can't do that. That's the big discrepancy. Operationally, what you use for forecasting is what's called a one-moment scheme, where you just have the mass mixing ratios of cloud water, rain, ice, graupel, snow. But what you need to tie it to aerosols and anything that's related to pollution or something like that, you need some information on the number of cloud droplets, on the number of ice crystals. And those are what's called two-moment schemes. They are available for Cosmo and will be available for ICON, but so far, for weather forecasting, they haven't improved the forecast skills to the extent that the added CPU time is worthwhile. And that's still, so at the moment, that's still for research and deeper understanding, and I'm sure at one point it will be transferred into operational weather forecast.
And the radiative properties of the clouds, like in the GCMs, do they differ significantly when taking into account these kinds of processes?
We have no chance. I mean, if we do climate simulations and everything what you have seen, the radiative forcing estimate that Martin was showing as well, there you need to have a relation between aerosol number concentrations and cloud droplet number concentrations. So we need to take number concentrations into account. And yes, there are differences, of course, because the minute we have problems with not knowing the right emissions, what Dominic yesterday showed, for instance, if we are missing hotspots of emissions, then also the cloud properties in those areas are wrong. So there's still lots of uncertainties related to clouds, definitely.
I realize that questions tend to come in late. Also for the last talk we had, the questions came in after the break. So I really encourage you at home to pose your question as early as possible during the talks.
I think there should be.
Oh, now I have a question from Tom Peter. Are waves which remain unresolved in even the most advanced state-of-the-art cloud models not also important for understanding cloud particle number densities?
Waves?
Waves.
Oh, really waves? Oh, I thought I misunderstood. Yes, yes, definitely, because you have small Kelvin-Helmholtz oscillations, for instance, that are much smaller, and they, of course, contribute what I now call turbulence, or what you also have in very small scales, and that helps to explain overshooting and updraft velocities. And of course, Tom is correct. If you don't resolve them properly, then you may not understand the processes going on in the clouds. So yes, that's also a topic that we are still working on.
And this is for altitude differences and temperature differences?
Yes, yes, because I mean the updraft determines how many aerosol particles activate. And if you have a stronger updraft because you have turbulence, because you do have a wave, then that enhances the cloud drop number that you would have. And if you don't resolve it, then you're lost. Or you have to parameterize it, and that's fraught with uncertainties, but that's the way that we are trying to do it. I mean, you can parameterize it by assuming, say, a Gaussian distribution of the updraft velocity and adding a standard deviation to it. That's one trick that we have been doing.
Okay. All right. No more questions for now. So thanks a lot, Ulrike and Michel. I hand over to you.
It is my pleasure now to introduce a colleague of ours to the stage. This is Anke Düger-Tetzlaff. She is a senior scientist at Meteo Swiss and working in the climate division and a specialist in, let's say, satellite applications. So therefore, we are very much looking forward to your more service-oriented presentation. Anke, please.
Yes, it's my pleasure to be here. Thanks for the invitation. So I'm switching back to radiation, and I'm switching back to applications. But before I start with my applications, I just want to tell you the framework we are working in at Meteo Swiss. Since more than 15 years, we are part of the Climate Monitoring Satellite Application Facility by EUMETSAT, where we derive satellite products and services for climate monitoring. The CMSAT now has a huge variety of products for the Earth's energy budget and its water cycle, and including cloud properties, precipitation, water vapor, and surface radiation. Our task at Meteo Swiss is the surface radiation budget. We retrieve albedo, surface incoming solar radiation, surface outgoing long-wave radiation, surface downward long-wave radiation, and our Belgian colleagues, they calculate latent and sensible heat fluxes. And what we do is actually something which is quite innovative in the satellite business. We retrieve all these components in a joint retrieval algorithm to ensure consistency. This seems logical, but in former times there were single groups, one deriving albedo, one deriving surface incoming solar radiation, with different kind of boundary conditions, and I think we are quite advancing here by really trying to be consistent and trying to use the best algorithms available. So we are consistent in terms of boundary conditions. So we have one aerosol forcing for albedo and surface incoming solar radiation, for example. We are consistent in terms of cloud forcing, one cloud retrieval algorithm for all the different parameters. Our retrieval algorithms are consistent. We use the albedo we calculate also as input for surface incoming solar radiation algorithms. We are consistent in terms of calibration, and we are also consistent in terms of radiometric transfer. So I just want to stress this because also in the satellite community we are progressing. I want to point you to one challenge we had over the years. This is one of the first images from Meteosat, some were taken in the 80s. And we are being so crazy that we are trying to squeeze out information out of this very old data. And we had a huge challenge this last years to get the calibration right. But I want to show you that EUMETSAT, so we were cooperating very closely with EUMETSAT and all the space agencies, that we made a big progress here. On the upper side, you see the uncalibrated data people used since years, with the Mythos satellite data are not stable. On the lower side, you see the calibrated data, which were calibrated in big projects like Fiducio, 10 years experience, permanent exchange. And we start seeing now very stable time series. The small differences, they are physical because we have to have different sensors. They need to be here, I can correct for it. But I think we made quite some progress here. And this plot, which was produced by the UK Met Office and Darren Gent from University Leicester, is just kind of highlighting the progress we made in terms of satellite calibration. We use land surface temperatures derived from satellites to calculate the clear sky surface outgoing long-wave radiation. And Darren Gent, they compared the satellite-based land surface temperatures against air temperature measurements over Europe. And what is really nice that we start now being consistent. Also, we have apples and pears. So we compare in anomaly space, we compare nighttime, but we start seeing being consistent with the anomalies we also see on the ground measurements. I want to take you to another point I want to stretch before going to the applications, I promise. And I want to face you with two very nice images, just to show you, to demonstrate you again, the influences which we have on the surface incoming solar radiation. On the right-hand side, you see the clouds. On the left-hand side, you see the aerosols. And of course, all the rest is easy to model, the sun geometry and also other atmospheric gases. And I put these very nice images here to tell you that what we do from the satellite community is we only retrieve the clouds, and all the rest is kind of modeled, or we need external input. And I want to stress this here, that what we are really still missing is the input from the aerosols. We had a nice talk this morning. So many satellite people actually use a climatology. So there's no way to compare trends in satellite data with trends from the surface. There are also nice aerosols now from climate models we are testing. There's also an attempt to use aerosols from satellites, but we would kind of need more support here or more initiatives in order to get the surface incoming solar radiation more advanced, better, to meet your requirements which were raised so nicely this morning. Just very shortly, because we have the newest algorithms, we are doing this joint retrieval, just to give you an overview where we stand a year before data release. So with the surface incoming solar radiation, we have a precision of 5 watt, albedo 10 watt. The long wave fluxes are also our problems, 11 watt, 10 watt evaluated against ground measurements. It's a bit frustrating if I see your 4 watt per square meter. You presented earlier, but you need to know that particularly for the surface outgoing long wave radiation, we are dealing with different pixel size, pixel windows, 5 kilometer versus a very precise measurement. We have uncertainties in the ground data, but which are definitely also high. I think you mentioned 4 watt per square meter. But what we can offer from the satellites is a measurement at all corners of the world, 5 kilometer, including also mountain areas. I promised to talk about applications. I will do so now. First of all, what is very nice for us now that the WMO have defined new climate normals, a new period, a new reference period, 1999 to 2020. And what is so nice from us, from this climate, from the satellite community, that it's the first time we can actually serve reference data for climate change. That's important for our climate service. And of course, we use this data in our climate surface. So we use this data for climate monitoring, climate reports. It's very simple, but I just want to mention it, that since years we use satellite data to describe the state of the art of the climate in Switzerland. I also want to point out a nice climate service BASF published since years, and probably many people know. Do you recognize the small image you see here? That's the building we are sitting in. And on top of this building, you see an estimation of the solar energy potential. You see if it's well suited or not. And this kind of estimation is done for every roof in Switzerland now by the Bundesföderal Agency for Energy and MetroSwiss. That's a very nice climate application where people actually use our surface incoming solar radiation as input. And I just want to say this is not a service which is frozen. We just have the new development we did now on the solar incoming solar radiation is now integrated. We have produced new data sets, and we have provided new reference data sets for this really nice climate application. I also want to show you highlight one more application where we are using the solar radiation data, where my colleagues have used the solar radiation data. On the left-hand side, you see a modeling of the heat stress days for the years 2021 for the end of this century. You see that there is a significant rise in heat stress days in Southern Europe. And of course, these predictions are done with climate models, of course. But in order to have predictions on a high resolution, our climate modelers need to do some bias correction, and they require temperature, humidity, wind, and solar radiation data. And they actually addressed me because they couldn't find 40 years of high resolution solar radiation data, and here my colleagues actually have been using the CMSAF global radiation data to make these predictions. And last but not least, I want to show you some very nice results we recently evaluated by Dominique Michel from the ATH. Evapotranspiration is a pretty important parameter for us. Perhaps we remember we had quite some droughts in Switzerland. It was not this year, but the years before. And of course, we are trying to collect parameters for our climate services which could be relevant in terms of drought or to better understand drought. And evapotranspiration is a very critical parameter which might explain some of the droughts we experienced the last years. And perhaps you remember I told you before that my Belgian colleagues, they use our radiation data we produce from satellites to calculate evapotranspiration. And the ETH has compared this evapotranspiration data against ground measurements. So it's a land surface model which is driven by our soil radiation data. And for us, and in Switzerland, you have two nice stations. It's the Wietholzbach, where evapotranspiration is measured since many years. And for us, it was really promising that when you look in terms of anomalies and you compare satellite data and measurements, this is the measurement at the Wietholzbach, this large lysiometer, which is very correct, is in blue, and our modeled CM-SAF evapotranspiration data, which use the satellite input, are in this pinkish line. In terms of anomalies, you start seeing very nice agreements. And this is very promising because what we can now serve with satellite data is not only a measurement at one point at Switzerland, but we can produce this kind of evapotranspiration data now with a pixel scale of 3 or 5 kilometers for entire Switzerland. So these, I think I'm the only one being a bit faster, but let me conclude. So the last years, there was really a strong progress on satellite data calibration. We have also a strong progress in how we retrieve data from satellite, this joint retrieval, this consistent retrieval. We can see improvements in temporal stability, also in precision accuracy. What is really important is that our satellite climate data records now cover the new WMO climatological normal and can be used as a reference. And also satellite-based radiation data are integrated in Swiss climate services. Many thanks for your attention.
Thank you very much, Anke, for this insight and your update on what's been going on at Météo Suisse during the past months and years. I see a few questions here, and I'll start with a question by Christoph Malti.
Yes.
He's asking, why do extreme temperature anomalies show less good agreement between the shown CRU temperature and satellite temperature?
Why they show less?
Less good agreement.
So I would like to ask more. I actually thought they've shown a pretty good agreement, I mean.
Maybe, Christoph, you can ask Anke afterwards in the Meet the Speakers session directly. And
I'm not sure if I got the question right.
I'll move on to a question by Dominic Brunner. He's asking, what we also see in nice paintings is that radiation effects depend on wavelength. Do you also investigate the wavelength dependencies of albedo, incoming solar radiation, etc.?
Do we investigate the wavelengths dependencies? I mean, of course, we have a physical model, and we take into account the spectral response functions. And of course, we kind of calculate the incoming solar radiation specifically for the spectral response of the satellite sensors. Mm-hmm. I hope this was the good.
And we have one question from Tom Peter. He is not asking a question, but a comment. The apps from Météo Suisse for weather and climate forecast are great, with all their special features and applications. Much appreciated. So with this, I hand over to Andrea.
Okay, thanks again, Anke, for your contribution. I used sonnendach.ch, by the way, and it's impressive. It's an impressive service because at the fingertip you have very solid information on photovoltaic potential. So, a big thanks to all the speakers of the energy balance session. We are now encouraging you to use the Meet the Speaker slot, especially from home. So our speakers will get online on GatherTown and be there to talk about your questions or other ideas. Now we have a slight delay, and I suggest that we meet back at 11:30 for the synthesis discussion of the energy balance session. See you at 11:30.
Welcome back, everybody, from this Meet the Speakers time slot. It was really busy here in the auditorium at Zentrum Paul Klee, so I hope this worked without any technical difficulties. We now move to our second synthesis discussion, and I directly hand over to Karina. Please go ahead.
Thank you. Thank you very much. So happy that we have the opportunity to have this discussion with all the speakers. So thanks for your presentation and input. So just one general overarching word on this session is that we have seen or discussed the critical importance of the energy balance from the surface budget also to the synthesis on the Earth's energy imbalance from global but also very local perspectives. And also with specific focus on major challenges of those estimates like the aerosols, the clouds and the surface patches, so particularly uncertainty in the fluxes, and the spanning from research to society with the services. So I would like to start with questions I would like to ask you all. So my first question is on how you see improvements or major gaps on reducing the uncertainties for the specific topics you had been discussed. Maybe we can start with the overall surface budget, where you had demonstrated by using a synthesis approach, by retrieving the entire data on the idea of the entire surface budget is a promising way forward. But which are the major ways of opportunities for advancing and reducing the uncertainties from your point of view?
Yes, as I mentioned before, I think it's the joint retrieval. We are missing input, external input and aerosols. I think this is what I also stretched. But I also think we should focus a bit more on areas from satellites like mountain areas, for example, where we could help. I mean, in flat regions, I see that ground stations can easily be interpolated. You don't have so many unknowns. But I definitely think we should start tackling the mountains. And from a satellite perspective, it's not impossible. It's just a lot of work.
And do you think that specific frameworks could help to foster this, filling those gaps? For example, specific collaborations established for the aerosol groups or for this mountain community?
I think we should start building a satellite-based aerosol dataset we could use for our retrievals. But also what we are missing in the satellite community is this focus on the mountains. There's no one founding us to develop algorithms specific for mountain regions or for the Alps. And I think this would be very, very useful to have to fill your needs on having high resolution data or surface energy budget in mountain areas. Because in the CMSAF it's Europe. If I try to focus on mountain regions, the DVD will not be happy. Because there are always this local interests, and I think we should come over this local interests. If you want, and I think we can really help with satellite data in this all corners of the world, which the big, like America or German Weather Service are not touching.
Yeah, but then specifically for the connection link between in situ data and remote sensing data, so I would like maybe then go over to the observed surface fluxes. So where do you see the critical gaps and opportunity in order to increase collaborations and to fill gaps? So maybe you can start with your point of view on the major uncertainties and gaps, and then maybe see some opportunities and how linkages could be established.
So in my opinion, with regard to the surface fluxes, as I've pointed out in my presentation, I think trying to trace back all these also historical data sets back to a homogeneous and consistent reference is certainly one of the key activities that we should be following up in the next couple of years. So that when we assemble these data sets to produce some global means and global averages, then we are more confident in the values that we get out from these networks.
Mm-hmm. So it's a recalibration also of the historical database. So it's a topic, it's an overarching topic for the energy budget, because you have the same issue, for example, for the ocean heat content, where you have still lots of gaps and where you could recover information by reworking and recalibrating the historical data set. So this is your biggest recommendation?
This is certainly something that I think where I can be involved in. This is one of the topics that certainly need to be improved, yes, where we would like to work on. Well, we have some ongoing projects and which, yes, we certainly should continue working on that.
And thank you. And for the perspective on the aerosols?
Yeah, I believe understatement could make even be a bit more extreme. Aerosols are a big nuisance. But being a big nuisance also means by combining these retrievals, you can also learn a lot about aerosols. I think really there's still a lot of potential for combined benefit by addressing these. And probably the fact that these near real-time data chains are implemented, this also offers opportunities to have time-resolved data, have them available on multi-sites. And maybe here comes the buzzword. Machine learning can also be important, and not because it's better, but I think because it, from a computational efficiency side, it can help to get it in real time, or also to reprocess all the data, which would be difficult with traditional methods. And maybe for aerosols alone, there are many things, but I think we also shouldn't forget about the small steps, because if there's repeated signs from different approaches on inconsistencies, it's worthwhile to keep looking into these, and sometimes one finds just a major or a bigger issue in one of the approaches, and this can help with looking at small problems, one can find also bigger issues. And maybe aerosols alone, I'm not perfectly sure, but one thing we would also like to look more into, to get aerosols right, simply you need the sources, you need transport, and you need removal. And on the removal side, I think there hasn't been made sufficient use of the data that are around to verify on the removal end.
Thank you. So, and clouds. Clouds are a very critical discussion component, in particular for climate models. So it's a large uncertainty also for the budget. So having specific process studies, advancements, as you have presented today, how do you see we can decrease, not increase, the uncertainties with these specific new knowledge steps?
We are trying everything. So we are also trying to look at satellite data. But with satellite data, to understand aerosol-cloud interactions is fraught with the problem that you only observe aerosols in the absence of clouds. And yeah, and if you have clouds, you don't see the aerosols. So how to get the correlation there? And even if you observe both, then you at most get a correlation, and machine learning by itself can also not tell the causality behind it. So you do need the physical understanding to make proper use of the machine learning, and then you have something that's called physics-guided, or as a different word, Gaussian processes, that you use prior knowledge about the processes to make use of machine learning. And that's something that we are trying as well. So that's a completely different project, but we are trying that as well. But in order to do that, then you need to understand the processes. And I mean, I have been involved in cloud parameterization since my PhD thesis, so quite a while ago. And at that point, the first estimates of the aerosol cloud interactions on the radiation budget were around -1 watt per meter square, and that's where we're still today. So 25 years later, nothing has.
But what do you see an opportunity? So
the opportunity is that we do understand the processes better, and then we can say in those areas the model is really doing something strange, and we need to look into that, and we need to go to the step where we can say, okay, this is related to water clouds, or this is related to ice clouds, or to mixed phase clouds, and this is maybe in orographic terrain more complicated, or the waves that we don't have, the dynamics that we don't have. And the opportunities that we have is that we have now climate models that have more flexible resolution. So we can resolve some of the dynamics that are important, and we do understand the processes better, and thanks to all the long-term measurements that there are. So that helps to constrain it from all different sides.
Yes, I was just connecting to what you have said already. I would like to come to my second question. That is the idea on how synthesis concept, like the Earth energy budget, whether you look at from a surface perspective or from the integrated perspective, how you think how it could foster multidisciplinary research and also help to tackle those challenges or to grab to those opportunities?
As long as you study clouds, you don't need to be too multidisciplinary because that's purely in the atmosphere. But when you mean it in a way that you need the remote sensing and the in situ measurements and the modeling, then yes, you need the different approaches. That's definitely needed to bring everything together because all by itself have their strength, and if you combine them, you get better, and that's what's being tried. And you have seen today a few times, and also yesterday, the CMIP models that you use the suite, and you showed it yourself, I think, the suite of different models helps you to see where are uncertainties. Are there uncertainties related to when it comes to clouds or to ocean heat uptake or I don't know what. And that tells you much more where we don't have the knowledge to improve the parameterizations well enough to get rid of those uncertainties.
And in this sense, also with the interaction or linkage cloud and aerosol effects, where do you see opportunities, or do you see opportunities when one would more focus on the synthesis approach, on the budgets, in order to advance and grab the opportunities for the challenges for your specific aerosol topic?
You mean budget approaches to better constrain the aerosol effects?
And to go new ways and to discover new or establish or implement new constraint approaches, etc., which could help to tackle some of the uncertainties and challenges.
I mean, one big challenge there in the end is that, particularly for clouds, this is number-based. If you do, and so that's a big challenge generally with aerosols, that getting the mass right is often much easier than getting the number of the aerosols, and balances are most often done in mass-based, and number budgeting is very, very difficult. So therefore, there may be ways, but I see more a pathway that we also to work on to get the mass number links better and to quantify where are the uncertainties on particle number, because that then also feeds back to how you distribute mass across number, feeds back to how you interact with clouds, it feeds back how you interact with radiation.
And I think I thought what you meant was like, can you constrain it? And yes, we have been trying to estimate the aerosol effect on climate from that you start from the observed warming that there is, and then you look at the CO2 increase or greenhouse gas increase and the ocean heat uptake, and then as a residuum you infer what the aerosol cooling should be. And that is more or less in the same ballpark as if you estimate it from models. So it works, that helps, but there is still a large uncertainty, and Martin showed it again.
Does this help also on smaller spatial or shorter timescale? That's where one tries to go.
But it could help maybe to identify new source of opportunities, which could open new ways of maybe tackling some problems, right? Independent approach. And so you both have already benefited from a synthesis approach, right? So maybe I reformulate the question for you in terms of where do you see more opportunities coming up in terms of, or do you see that there is a more international framework needed in terms of defining the synthesis approach, just as suggested now for the cycles, the energy cycles, because you have demonstrated that that using the synthesis approach was an impressive way forward in terms of retrieving your data. So do you apply them also for the communication part and for the services that you provide, services which are linked directly to the surface budget? Or do you see other opportunities in framing the surface budget for these projects?
I think it's a good question. I think just one point, we have this joint retrieval, but of course we are not including surface data yet. And I think we should link these two communities a bit more, because we are doing our own validations without too much knowledge on the, I think, understanding, because what I haven't shown yet, we have also not calibrated data, we have also data with uncertainties now. We just didn't have the time to use those data yet, because we first needed to advance in our algorithms. But I think for the next phase we have uncertainties. And then I think it's even more crucial to work together with the ground observation people, with your uncertainties, to really understand uncertainties more in detail. Because if I come up with 10 watt per square meter having point region intercomparison, I think we have to advance in intercomparison our uncertainties to help putting uncertainties on the entire budgets.
Yes, for sure. That's certainly something that we should be working together on, yes, trying to understand how to combine the data sets from satellites and the point sources from the ground.
Yes, and how to associate uncertainties at the end, yeah.
I mean, it's a clearly linked outcome to have a framework or somehow where you can establish these collaborations and to link
Yes.
the in situ component with the satellite component through a framework such as the energy budget, but maybe also have more discussions on the carbon cycle we had and we will have on the water cycle. But it's
So one point of the baseline surface radiation network when it was established was that it would be set up at sites which are spatially representative for a larger area, so that this problem of a satellite pixel would not be as strong as if you are in a very heterogeneous environment. And so these BSRN sites were designed so that the comparison to satellites or even models would not be that much hampered by having this heterogeneous area. So
I mean, for the thermal...
some of this has already been taken into account originally when these networks were established.
Yeah, but I strongly believe what we are missing are, I mean, thermal components are difficult, I mean, to have homogeneous, that's for sure. But I mean, for example, for surface outgoing long-wave radiation, we have 2 or 3 BSRN measurement sites. So this is not representative at all. I can't tell you much on the quality of our surface outgoing long-wave radiation. And the same is on surface downward long-wave radiation, so we would need much more of those stations actually to put uncertainty.
So there are more, and so it's really just a matter of trying to discuss it together.
Yes,
and
I think we should discuss and we should come closer. And
yeah, so it could be also across work in order to identify critical gaps for
Yes.
the different application, and then they have the opportunity later on to fill those gaps. And so I would also like now to drive to another topic which had come up in the questions you have received during the session today, which is going a bit more on the communication side and also linked to society and the services. So I would like to bring up here the keyword of indicators and linking also that many of the budget components are derived components. We have heard this also yesterday from Sonja on the recommendation that, for example, the storage component not yet really implemented in GCOS as the essential variables, and also target and recommendations are needed, but in turn that they can be also importantly bridge the communication need between research and society. So what is your vision on the major key indicators from your side where you think and where we could move forward and better communicate, and on the one hand, but also on the other hand, where there's a need at GCOS level to further foster develop targets, to implement those in these frameworks?
I mean, I have to say, I'm a satellite person, I'm not a climatologist, so it's hard for me to say the need on the indicators exactly. But all I know that it's so hard to get the satellite world to produce indicators because they're saying, this is not my business, while the other ones are waiting for those indicators. And it would be fantastic to make this link. Who is producing indicators, or who is producing the climatological reference period 1991 to 2020? It would be fantastic to have this reference data out as a product, but the satellite community say this is not our funding, this is not our budget, and I'm missing this kind of link to produce indicators or to produce reference data sets if we are not doing this with own MetroSwiss funding.
So what the main message is here, that this bridge gapping could be helped
Yes.
if we have reference data set, but also definitions and framework indicators. There are
Yes.
already some at place, like the GCOS Global Climate Indicator Framework,
Yes.
but this could be maybe extended and would then help also people at the interface in order to better improve the communication or the power to communicate and to link also research with the communication, right? Okay, it's
I
a very nice
Because we
outcome
had
as
an
well.
ASAP project where we produced indicators,
Yeah.
but from the satellite side alone. And this was not, I mean, we had nice indicators out at the end, but we didn't really had the users, or we're not connected. So we need somehow more connections.
But I think Sonja had it very well in her talk yesterday. If you can explain to the society that this heavy rain that we have seen is because of climate change to this and this degree, that helps. But maybe I'm not sure what you mean with indicator, but I think something like that helps, because many people think already, okay, this extreme precipitation event, this thunderstorm, this hail event wouldn't have happened before. And if this is substantiated by how much of it is, or how much more likely it is with anthropogenic climate change, that I think is a message that's very easy to bring across.
So it would really good to really work together. And that could be also another way of foster collaboration to refine or extend the indicator framework, and could maybe a way also to bring communities together to tackle, also coming back to the uncertainties, right? Because you need to have the targets and you need to reach this target, and then you would work together on the uncertainties. Like, so maybe you have also a point on this indicator question.
Well, when I think about what could be shown to a public in terms of demonstrating changes over a long time period, then there have been a few things in the radiation budget that certainly have probably caught the public, like the discussion on global dimming and global brightening that was started with Atsumu and that Martin Wild continued, which actually shows that the radiation on the surface has been changing over decades based on how the human pollution has changed, for example. So it was really based on aerosols, on cloud changes. So this is something that I would say can be taken out as a climate or as an indicator how this radiation has been changing over time.
But in general, you see also there an opportunity to bridge or to foster collaborations across disciplines, across silos, and also to help bring communication forward, to bridge between science and society?
I don't know about society. Among the communities, the scientific communities, certainly, because you have to combine the modelers, you have to combine those that take the measurements, those that assemble the data sets. So there you certainly need a collaboration. Mm-hmm. How much that works then towards informing the public and going towards the society, that I have not been involved so far.
Yeah, no. But it's a very strong information already on how such a framework, maybe from the essential variables to the indicators, could also help to foster multidisciplinary communication. What is your opinion for this point?
For me personally, looking at the new IPCC report and also things I have heard yesterday, for me it's very impressive how much progress in understanding and kind of solidness of the result one has made. But still it's difficult to get that over to the people that action is needed. There are many reasons, like it's too long time scale, so it's not really immediate. So the extremes are something people can grab more. And maybe it's a negative piece of news which also people try to put away. And one thing we also heard yesterday, that exchange of data and knowledge between WHO and WMA has improved on the health side to improve those health studies. And I think the air quality and climate are often linked on an emission side, and I think on the health side there's also a lot of positive news, of a lot of good achievements with emission measures which have resulted in improvement. And maybe one can also, with some positive news, and show that we really get things together to one way how one could try to communicate.
Thank you very much. And so we have one question from the audience, and it's from Tom Peter, and it's a question for you. I think it's in this discussion round, not a small-scale meteorologist missing. Clouds which affect the radiation budget so fundamentally are not only affected by aerosols, but also very much by small-scale temperature fluctuations, aren't there?
Yes, yes, of course. I mean, it's a similar question to what he asked after my talk. Yes, we need the small-scale information for sure. We need small-scale temperature fluctuations and humidity fluctuation, depending on which clouds are concerned, and the dynamics are very important. So yes, that's why the clouds on the small scale are a completely different beast than if you are trying to simulate them globally for climate change projections. But of course, the global mean number that you get out is comprised of all the small clouds that you have. So yes, Tom is right, as always.
Thank you very much for this great discussion round, and I thank you all for your intervention.
Thank you very much for this exciting discussion panel. That was very lively. Thank you. So we're just a small step ahead of our lunch break, but before, let me point out that the second part of our poster exhibition with new posters will be up in just after the lunch break. The exhibition of the posters is again just outside this main virtual conference hall, but today it will be on the right-hand side.
Again, all presenters have prepared a short poster pitch following on this live stream right afterwards. The poster exhibition then starts at 1 o'clock, as Andrea said, after the lunch break, and will last for 40 minutes.
We will open then the last of our 3 Earth system cycle sessions at 13:40. That's 20 to 2. Ein gute Miteinander.
Ein gute.
Hi, my name is Stefan Brönnimann, and I will guide you quickly through our poster. Long meteorological records are, of course, very important in climate research. In Switzerland, we have 2 very long records, the one from Basel and the one from Geneva that go back to the mid-18th century. But actually, Switzerland is very rich in early instrumental records, as this inventory has shown. The goal of the project now was to complement the existing records from Basel and Geneva and to generate new long records. For Basel, for instance, the existing record is based mainly on 2 observers, Danone and Merian, who observed from 1755 to 1864. However, there were many more series that were obtained in Basel that could help, for instance, to fill a gap of nearly 26 years in the record with data from Basel. Another example for a new record is the record from Bern, when we can generate a 270-year-long record based on the data from many different observers that are shown here. More information also on a very long record from Zurich is found on our poster.
Hi and welcome all. My name is Helga Weber and I'm a postdoc at the Remote Sensing Research Group at the University of Bern. Time series of snow cover extent from space can fill essential knowledge gaps on past snow occurrences, especially in climate-sensitive mountain regions such as the European Alps. Today, we present you a novel fractional snow cover time series from 1981 until 2021 to support climate studies in Switzerland. The novel daily and upcoming monthly dataset of fractional snow cover extent is optimized for snow detection in forested regions, will include pixel-wise uncertainty measures, and extends former space-bound time series retrievals to 40 years. I'm happy to share with you the first results and hope to discuss with you at poster 2.
Hello, my name is Christian Haug from the Department of Geoscience, University of Fribourg, and I welcome you to our poster. So permafrost monitoring is usually being done by temperature measurements in boreholes, but that's very costly and also very often not possible in high mountain terrain. which is why also geophysical techniques come into play, like, for example, these geoelectrical measurements here. So at very few sites, we have an annual monitoring of permafrost with these geoelectrical techniques, and we see here that the resistivity decrease with time over the last 20 years. But usually that's not possible because of the high logistical effort. So what if we could use single measurements, which have been done in the past, and then repeat it after a decade or two in order to see whether there has been any ice changes over that time period. But for that, we would need a database where all these historical electrical resistivity data are stored, which we then can decide which of these we would like to repeat after 10 or 20 years. And this has been done in this project, and on our poster we show first results of this initiative and also the implications for an operational international database, which we currently try to achieve. So looking forward to see you at our poster.
Our study is mainly about a physical retrieval method of the rain rate. This physical method is based on a kind of relationship between the rain rate and the rain opacity. The rain opacity can be got very accurately by ground-based microwave radiometer. And also we test this method by comparing it with two rain gauges using 15 years data. And this method can derive the changes in cumulative rain over the day, the month, and the year. The monthly rain rate estimation has a good performance. The R-square can be 0.77, and the root mean square error is only about 22 millimeters per month.
Alpine Wells is a project on ECV monitoring in Swiss glacier lakes. We compiled an inventory of glacier lakes in the Swiss Alps and the years since 1850. It comprises of 1,200 lakes in total and revealed that lake formation between 2006 and 16 was faster than in any previous decade. We now use the inventory for the development of glacier lake mapping algorithms using Sentinel-1 and 2. We also test different means to monitor other ECVs in glacier lakes. In 2 lakes, we are monitoring the thermal structure. In 6 lakes, we acquire pressure measurements and bathymetry maps. During all fieldwork, we measure spectral reflectance in order to validate Sentinel-2 derived lake color. Our colleague Manu Tom will also investigate lake ice monitoring in glacier lakes based on experience from a previous GCOS project at ETH. Alpine Wells is funded by Meteo Swiss in the framework of GCOS Switzerland and the Federal Office of the Environment. Please contact me at daniel.odermatt@eawag.ch for any questions concerning this project.
Hi there, and welcome to the poster on aerosol observations on the Jungfraujoch, supported by the GAW program. This poster covers 3 aspects of what we are doing up there. On the left, there is the general description of the station and what is planned in the future. In the middle, there is a big data analysis effort explained by Martin Kolo-Cohen from Meteo Swiss, which analyzed all the optical properties data of the entire observation record we have. On the right side, there's the special topic on the COVID lockdown effect on black carbon emissions, where the Jungfraujoch was used to constrain these emissions in a modeling effort. Feel free to ask me any questions, and thank you for your attention.
Model estimates of aerosol ice cloud interaction and their climatic effects are still with large uncertainties, because the abundance and sources of isolated particles remain unconstrained. Presently, only few automated IMP counters for long-term studies are available. Here, to fill these gaps, we developed a fully automated online IMP counter, Hink Auto, and firstly implement the high-resolution monitoring of IMPs at one of the GAW stations, the Jawfrog, for 1 year. The results indicate that median concentration of IMPs in the free troposphere is quite low compared to previously thought, and majority of the emerging IMPs at Geoffrog are likely mineral dust. We also propose that ceilometers may be useful to predict the IMP concentrations in dust plumes.
Good afternoon, my name is Luca Egli from PMOD and the World Radiation Center in Davos. I will present the Swiss Global Atmosphere Watch project, which investigates the future evolution of the ozone layer above Switzerland. In Davos, we maintain now the longest time series of ozone monitoring, which started in Arosa about 100 years ago. In Davos, we now have 10 different instruments for monitoring the total column ozone. In particular, we have a fully traceable instrument based on Quasume, which is the world reference for UV radiation and serves now as an independent source to monitoring the total column ozone with an uncertainty of less than 0.8%. In our institute, we also have a climate model group, which focuses on the chemistry on the atmosphere and also on ozone. And now with this huge number of instruments and the model, we have a good tool to investigate the evolution of the ozone layer in Switzerland. Thank you very much for visiting my poster.
My name is Julian Gröbner, and I am presenting the calibration activities of the World Calibration Center for Ultraviolet Radiation, which is hosted at the Physikalisch-Meteorologisches Observatorium in Davos, Switzerland. The calibrations that we perform are both on-site, where we characterize and calibrate broadband UV radiometers, as well as on-site validations and calibrations of UV monitoring sites with our traveling reference spectroradiometer Quasume. The poster will be presenting some of these activities and some results from the last calibration campaigns that were performed recently in Davos.
Hello, my name is Martin Gieselbeer, and I present our GAWCH science project. In Europe, the ACTRIS research infrastructure addresses aerosols, clouds, and trace gases. In Switzerland, we are about to include the Pion Observatory in the ACTRIS network. This project contributes a puzzle piece to get there by supporting the implementation of aerosol observations at Pion. The importance of both traffic emissions and new particle formation is shown as an example. Aerosol remote sensing includes the inverse problem to retrieve aerosol physical properties from light scattering phase function measurements. We develop an in situ polarimetric instrument to validate and advance polarimetric retrievals. Meanwhile, we have built our own prototype, and we successfully achieved proof of concept in lab experiments.
Hello, my name is Tedios Kazadzis. I work in the World Radiation Center in Davos, and in my poster you are going to see about WORC, the World Optical Depth Research and Calibration Center. So what is WORC? WMO has designated WORC as the primary aerosol optical depth reference center. WORC provides the traceability of aerosol optical depth measurements, guaranteeing the data quality needed in climate studies. And you're going to see about WORC-specific activities, including maintaining a reference scale for aerosol optical depth, about the Global Atmospheric Watch BFR network for AOD, also global homogenization activities for different aerosol optical depth networks, aerosol optical depth metrology, new calibration methods, and finally technology advancements. You're welcome to my poster number 12 on Tuesday afternoon. Thank you very much.
Are we on? Yes. Hello, welcome back. Time flies and we are already starting our last session dedicated to looking at Earth system cycles. The last one to go is on water. For the water cycle, we are very pleased and honored to have Annie Kaznav with us. She's Director of Earth Science at the International Space Science Institute here in Bern. She pioneered satellite altimetry and contributed to a greater understanding of sea level rise in the context of global warming, and served as a lead author on the sea level section of the IPCC assessment reports 4 and 5. Without any further ado, I welcome Annie Kaznav for her overview keynote lecture on the water cycle. Please, Annie.
Okay, thank you very much. And first of all, thanks for the invitation. I'm very pleased to be here. Good weather, which is perfect. And I have been asked to talk about the global water cycle, but I have to say that I am not an hydrologist, so I hope I will not forget some important things. But I know that in the audience there are many participants that can correct me. So I would like to start to remind you that with the carbon and energy cycle, the water cycle, the global water cycle is one of the most important topics to study, to understand how the Earth system is functioning and how it changes under various forcing, including anthropogenic forcing. So, as you all know, the water cycle is the exchange of water between different compartments of the Earth system, ocean, atmosphere, land. And it changes through time because of various factors, climate change and variability, and also direct human factors like groundwater mining, irrigation, urbanization, deforestation, etc. And it is very important to know the various components of the global water cycle for a broad range of application. I will not go through all this, but you all know that it goes from water resource management to study the impact of the global water cycle on climate, etc. This figure just depicts various fluxes and stocks between the different compartments. So the flux consists of precipitation, evaporation, and runoff, and the stocks are water vapor in the atmosphere, water storage on land, and ocean mass in the ocean. So this figure shows you have in the top part of this figure the water budget on land. I will separate water budget on land and over the ocean. And I would like to briefly go through each variable and just remind you, summarize why they are important. So precipitation is the main driver of the hydrological cycle, controls water storage and runoff. Evapotranspiration is also a very important parameter, drive mass and energy exchange between the lower atmosphere and the surface. Runoff is a return flow to the ocean. It contributes to the water balance of the ocean. And of course, it is a major resource, water resource on land. Now, concerning the water storage, which is the S term on the left-hand side of the equation, it consists of different components: surface water, snowpack, soil moisture, and groundwaters. And each of them are specific importance. So maybe I cannot go through all of these because of time. So now moving to the ocean, we have not exactly the same equation as for land, because here, instead of the minus sign for runoff, we have a plus sign for runoff. I would like to recall that precipitation over the ocean represents 77% of surface rainfall, and it results from the condensation of atmospheric water vapor, and it is the largest source of fresh water entering in the ocean. Now, evaporation is the largest flux over the whole Earth surface, 85%, and I think it is also important to mention that evaporation is enhanced as the global mean Earth temperature increase, and in particular the temperature of the ocean. And because of all of this, the ocean dominates the global water cycle. Now, concerning the S term, the ocean mass change, it results from exchange of water with land ice, and terrestrial waters. And as we will see in a moment, it causes the global mean sea level to rise, to vary, to rise. So now I would like to briefly talk about the observation. The global water cycle is a global phenomenon, but it has global, regional, and local effects. And to understand all these effects, we need a broad range of observation over various spatial and temporal scales from ground and from satellites. So let me start with land. I will not go into all variables, but the only thing I would like to stress here is the lack of data in some region of the world. And here is an example for river runoff, river discharge, and river water levels. You see a map from the Global Runoff Data Center that summarizes the date of the last available data. So the color you can see here, for example, for the red and yellow and even green color, we don't have any data beyond year 2000. So you can see that only North America, Western Europe, and part of South America have up-to-date data. We have a similar situation for soil moisture, and you can see again that in general in the southern hemisphere there are lack of data. This brings me to talk about the importance of remote sensing, satellite data. By the way, I am a satellite person, so I would like to spend a few minutes about the contribution of space data to this problem of the water cycle. And I will first focus on water storage on land. And here we have different type of sensors that inform on the different components of the water storage on land. For example, satellite altimetry informs us on surface waters. There are specific dedicated missions to measure soil moisture. And we have also the gray space mission that inform on the vertically integrated storage from which we can deduce groundwaters, a quantity which is very important for some application and which is very poorly known from ground measurements. So just to, I will show you now a series of examples. So let me start with satellite altimetry. It measures lake and river water level. And here you have an example of what satellite altimetry provides. This is for the lake, the Tonle Sap Lake in Asia. We can see this water level time series from which, after calibration, we can deduce. Okay, okay. So not for lakes. We don't have discharge for lake, but for river, for equivalent measurement for river, we can deduce discharge. And This is an example where satellite altimetry is very important in some region of the Earth, in particular ungauged basins. This is the case for the Congo Basin, where there is almost no in-situ data, and all white points you can see on this figure correspond to what we call virtual station, that is the intersection of a river and a satellite track. And on the next figure, you can see an animation that shows the change over time from low waters to high waters, depending on the season and the year, deduced from altimetry. The problem with satellite altimetry that has been optimized to study the ocean, not to study rivers and lakes on land, is that it works only for very large rivers, but not for small rivers. And next year, in November next year, we will have the launch of the SWOT mission, which is an international mission involving NASA, some European countries, and Canada, that will provide water levels and river discharge over the whole Earth and covering rivers smaller than 50 meters in width. So it will be probably really revolutionary. So another example is soil moisture. They also measure by space and from space. And here you can see, not very clearly, but you have time on the horizontal axis. You can see the blue and red color, succession of blue and red, which illustrate dry and wet condition depending on time in different regions of in Europe. And you can see the last red spot in southern Europe, which correspond to a very dry drought condition in 2017. So now I move to another example, what GCOS provides us on land. And here is an illustration of the GCOS measurement over a few large aquifers of the Earth. And you can see that for the period here from 2003 to 2013, the depletion of water, the decrease in water storage in these large aquifers. And another example from GCOS is a figure from a publication by Vincent Humphrey. It shows water deficit over this period 2002-2017 over the whole land area. And you can see this red spot over Amazon. It does not mean it is a linear decrease, but it reflects a particular event, a drought event in 2011. So now moving to the ocean. First of all, for precipitation, we don't have, like over land, in situ rain gauge station or high-frequency radar, but we have, again, satellites to measure rainfall over the ocean. And in particular, the Global Precipitation Measurement Mission, which is a constellation of different satellites that measure precipitation, the intensity and the variability of precipitation, and also the 3D cloud structure. Another quantity which is important over the ocean, which is not part of the water balance over the ocean, is sea surface salinity. Sea surface salinity is currently measured from space by the same mission as for soil moisture on land. And sea surface salinity is a key indicator of the strength of the water cycle because it is directly related to precipitation minus evaporation. And on this figure, which is not based on satellite data, by the way, but from in situ data, you can see the trends, the change over the period 1950 to 2000 in evaporation minus precipitation. So the red color means saltier water, which means also that evaporation minus precipitation increase. And the blue color means less salty water, and evaporation minus precipitation decrease. So we have a clear picture of the intensification of the water cycle, in particular in the Atlantic, as you can see, and in the tropics, by the way, Indian Ocean and Pacific Ocean. And finally, the last component of the water budget over the ocean is the ocean mass. And it is currently routinely measured by space gravimetry, the GRACE mission, and also by satellite altimetry. And here you have a figure that shows the evolution of the global mean sea level measured by satellite altimetry. And by removing the thermal expansion contribution to this curve, we get the ocean mass. And we know now that about 60% of the global mean sea level rise, this curve, is due to an increase in ocean mass. So now I move to the still unanswered key scientific questions and challenges. So the main scientific and societal goals to understand the global water cycle and its application to societal issues could be summarized as written here. So here I use the formulation of the NASA Decadal Survey, but it represents a consensus in the community, and we can see almost the same issue priorities in a variety of white papers or other documents. So the first key issue is coupling the water and energy cycle to predict changes, to look at availability of fresh water and coupling this topic with the biochemical cycle and the problem of hazards and extremes. So let me start with the first one, coupling the water and energy cycle. So the key scientific question behind this topic is how is the water cycle changing? Is it intensifying? And we have seen in the previous figures that, yes, we think it is intensifying. Are evaporation and precipitation accelerating? And what is the spatiotemporal distribution of such changes? Concerning issue 2 and 3, that is about prediction of change and the issue of fresh water resource, I group them. So the key scientific question we may ask is, what is the impact of anthropogenic climate change and direct human activities on water storage? How do change in water cycle impact local and regional freshwater availability? And another question is, what is the impact on land use, land cover change, water use on agriculture and food production? And finally, about hazards and extreme events, how does the water cycle interact with other components of the Earth system, like, for example, the energy cycle, etc., to change the predictability and impact of geohazards, like floods, drought, wildfire, landslide, etc. To answer all these questions, we need, obviously, observations, global, regional, and local observation, very accurate, homogeneous, and long-term time series from all observing systems available. And you will see in the next 2 slides that for each hydrological variable, we have problems. For example, for precipitation, because it is highly variable, both in space and time, because it can vary from less than 1 meter scale to more than 100 kilometers, at subdaily to interannual and decadal time scales. The current observing systems are not fully adequate to measure all this range of variability. We have seen that we have poor coverage of ground-based. Oh no, okay, we have not seen that, sorry. But I have to say that we have poor coverage of ground-based radar in underdeveloped countries and in mountain areas. And it is also very difficult to measure rainfall in high latitude areas. The other issue is that snow is undersampled. And finally, the detection of extreme remains a big challenge because they are very localized in space and in time. Now, concerning evaporation, also a lot of problems. First of all, evaporation and evapotranspiration on land are not observed directly except on land at very localized, very local scales. So current estimates are mostly based on empirical models that need a broad range of different observations, which are not always available. So it's a big problem to estimate evaporation and evapotranspiration on large scale. And about soil moisture, we have some in situ measurement on land. But you have seen the poor coverage, in particular in the southern hemisphere. And from space, the passive microwave sensor do not have the needed resolution for a number of applications. I have to mention that there is, in addition to the two missions that have been dedicated to measure soil moisture, so the SMAP mission in the US and the SMOS mission in Europe. SMAP is no more working, but SMOS is still in activity. In addition to this, there is a Sentinel-1 satellite from ESA, Copernicus, that will be very useful to measure soil moisture with a resolution better than 1 kilometer in near real time. So it's worth to be mentioned. Concerning river runoff, I remind that from all hydrological variable, runoff is the most important for water resource management. We have seen the problem of ungauged basins. And from space, we still have poor spatiotemporal resolution. This will improve, as I said before, with the SWOT mission to be launched next year. But SWOT will be just one mission for 3 years, maybe a little longer. And one perspective in this domain will be to launch a small satellite constellation, like, for example, CubeSat or slightly larger satellites. For example, several satellites in the same orbital plan will allow to have daily or sub-daily resolution measurement of river discharge, river level or river discharge, which is the quantity of interest for hydrologists who are involved or interested in water resource management, which is not provided today by current altimetry mission because the best time resolution is 10 days. About groundwaters, clearly space gravimetry, the GRACE mission, is recognized as a unique tool for monitoring large aquifers, but it has a 2-course resolution for monitoring small aquifers. The ground resolution of GRACE is 300 kilometers. So it's of limited value for a number of applications, water resource management, decision making, etc. And finally, snow and permafrost. The terrestrial snow and frozen soil are still poorly represented in the global water cycle. And there are not enough, yes, I'm nearly finished. The retrieval of cryospheric variables like snow depth, snow density, rate of snow melt, permafrost dynamics, glacial mass change is still very challenging, in particular in mountain areas, and some effort should be put on this particular topic. Because all these hydrological variables are measured by different sensors, different observing systems from ground and from space, they are not necessarily very homogeneous, and it is very important to cross-calibrate these different variables. In particular, as written in this slide by GCOS, in studying the closure of the global water cycle, at different scale, globally, regionally, and locally. And this is a perfect approach to detect, for example, systematic errors, instrumental drifts in some sensor, etc. So this is really the thing to do. And finally, this is my last slide. I have talked mostly on observations, but modeling is also very important at all scales. For example, global and regional hydrological models, climate models, of course, and forecast model for extreme events, drought, floods, etc. And okay, this is my last slide anyway. And of course, this is already done, but I would like to stress the importance of combining data and models through data assimilation. And this is really the way forward to follow now, the combination of data and observation and models. So this is all. Thanks very much.
Thank you very much, Ani, for giving us this overview. I have a few questions on my pad. I'm looking into the audience, whether there are any direct questions. All right, I cannot see any hands. So Martin Hölzle has a first question. What is the reason for the decrease of surface observation in the 1980s and 1990s?
From what I know is that it's due to economic and political issues, in particular in Africa, for example, but not only in Africa, but also in some part of in Eurasia, for example, in Siberia, there is so it's mostly economic and political.
And he has a second question saying SWOT will help us also in mountain areas?
Yes, I think so. I'm not sure of the answer. I don't know if there is somebody here who can help me, but depending, for example, on the width of some valleys in mountain areas, it will be possible to monitor the river. So as I said, the expected resolution of SWOT will be, for rivers, 50 meters. Yeah. So I normally should work in mountain areas.
Sonia Seneviratne asks, are continuous measurements of the global water cycle using satellite gravimetry with GRACE, follow-on and other missions guaranteed for the coming 2 decades?
Okay, so GRACE was launched in 2002, the GRACE 1 mission. So it stopped working in 2017. Unfortunately, we had a gap of nearly 1 year. The GRACE follow-on mission has been launched in 2018, so it's currently working. After that, we don't know. We are doing some lobbying in Europe to have a GRACE-type mission in Europe, for example, launched by ESA, developed by ESA, but it's far from being a success at that time, because GRACE is a joint mission between NASA and the German Space Agency. And so I think it would be very important to have a GRACE-type mission in the future, because today we talk about GCOS for measuring water storage and sea level, but GCOS is measuring everything that moves on Earth and at the surface and inside the Earth. So all mass redistribution. So it's, I think it's a revolutionary mission.
Then probably, let me see. You have shown, it's Sonia again. You have shown, yeah, you can ask it directly, Sonia.
We need microphone.
I don't know, I cannot see her.
There is one, no worry.
Yeah, thanks a lot, Tani, for the great presentation. And I had a more general question, more in terms of strategy. I don't know that anybody of us has the answer to that, but you have shown that we are lacking ground observation in many locations. That would be really important for the validation, for instance, of the satellite. So how do you see, maybe from your perspective also at ETH, how do you see that we could maybe foster having more observations, and how can we improve the state of the observations?
You mean the state of in situ?
Yeah. Do you see as I mean, I guess maybe through GCOS, yeah. Open question, yeah.
I have not the answer, obviously, so I don't know. It's really a political issue. I don't know.
Jörg, you can add yours. Which
well,
seems
yeah, my question was actually related, I think, maybe because we sit next to each other. If you had to choose and a few dollars available, would you invest them in satellite ground truth, or would you invest them in expanding the ground-based observing systems? We can't do everything, and you presented a whole lot of challenges. So where are the priorities?
It's a difficult question because depending on the application, we need information on, for example, for water management, we need information on river runoff and groundwaters. For the application, we need other kind of variables. So it depends on which focus you want to insist. Of course, we want everything, so...
Being at the GCOS, joint GCOS GAW Symposium, probably... Yes.
So, first of all, we already have a lot of observations, and they are under, to me, they are under... they are not analyzed enough. And we can already do a lot of things with the observations that have been collected from ground, from satellites, and so on. And a project like the ESA Climate Change Initiative that try to homogenize all observation available for a given essential climate variable is a thing to do. And for some hydrological variable, for example, it has been done for soil moisture, for, I don't remember the other one. And so to me, the priority is to improve the data set we already have in hand, trying to combine them, homogenize, and so on. And obviously, we have to continue to make some lobbying, to have more satellites, more ground stations, and so on. It's all I can say.
Reto, does this answer part of your question, or do you want to go ahead and pose your question?
Yeah, maybe I can pose part of my question. So,
sorry, I'm sorry. I thought it was finished.
So, if you had a wish to the other cycles, they're not independent. What would be the most missing part from the other cycle that would help you to close the water cycle?
I think I did not catch the. Can you repeat the question?
Yes. So if you could wish input from the carbon cycle or input from the energy balance to close the water cycle, what would you choose?
I'm not sure I understand the question.
So maybe I have the full question. So in most of the modeling things, you realize when you try to fix something, there's something else that actually is responsible for your thing. So in land modeling, there's we have the energy cycle and the water cycle, and we realize we can only do those right when we have the carbon cycle right. And when we have the carbon cycle right, you realize you can only do that right when you have the nutrient cycling right. So from the water cycle perspective, what is the most missing link for you to close the budgets of the water cycles from the other cycles?
I'm not sure I will give the right answer, but maybe Sonia will correct me. I think one of the least well-known variable is evaporation, evapotranspiration, and because except very locally from in situ measurement, it is only derived from models, and these are. I'm not an expert, but Sonia can complete. It is based on empirical models, and a lot of variables are needed to fit the model. And I think it's the least well-known quantity. Do you agree with that?
I have an answer, I think, to that specific question related to carbon. Because I think if you know GPP, for instance, very well, you can start working with the water use efficiencies and have also a better handle on evaporation. And so there are links that would allow you, if you measure both, and it's the same what you were saying about modeling. If you want to model the water and energy cycle correctly, you need to have a good vegetation model.
Yes,
well,
vegetation
consists of a lot of carbon, and all of that basically links into GPP, and there are increasingly good estimates of GPP from satellites, and they're well validated also by FluxNet sites. And to some extent, it's a bit of a surprise that I don't hear much either this morning and this afternoon about FluxNet, which has all these direct measurements of surface energy fluxes and evaporation. But that's a separate story. We might come back to that in the discussion. But my answer to your question is basically GPP.
Yeah, I think I agree with Annie's answer. I would say the part that is most uncertain is evapotranspiration, and I would say there is no perfect answer to the question that Reto asked, because evapotranspiration is both driven by radiation and vegetation status, and so I would answer to Han, GPP is important, but radiation is also very important, and I think that's the whole question is how much is their relative importance. I think you need all three, basically. You need some estimate of the water cycle and good estimate of radiation and carbon. I would not choose one over the other.
Okay. Very good. So thank you again, Annie, for your input, and the audience for your inputs and questions.
That was very good.
We move along in our program, and I welcome Lukas Gudmundsson of ETH Zurich on stage. He is a senior scientist at the Institute for Atmospheric and Climate Science and a specialist for freshwater climatology. His talk is all about observations for land water resources and drought conditions, soil moisture and runoff. So please, Lukas, take the floor.
Yeah, so thank you very much for this kind introduction. And maybe the first thing I'll do in my presentation is to add on the discussion before, and I think that everything that relates to the surface energy balance would be highly relevant to get a better control on factors contributing to land hydrology. Typically, if we are talking about land hydrology or the water cycle, we are confronted with diagrams like this one, where we see that ultimately all the source of water on land, or the source of all of water on land, is the ocean, where water transpires, no, not transpires, but evaporates, and then is transported to land and then processed through a large array of different processes. But unfortunately, these type of diagrams are also highly disproportional, because there's something what I like to call the bitter truth of terrestrial water, and that is that it only contributes to a really small fraction of the total available water on land. So if we look at the proportion of, for example, groundwater and surface and other freshwater resources, which, by the way, involve also atmospheric water, we see that this adds up to less than 1% of all water in the Earth system. So ultimately, we might ask us the question, yeah, why should we bother? And because it's really tiny amount. And of course we bother because it matters to us directly. We need it for drinking water. It's relevant for agricultural production, energy production. We also ship goods on it, on large rivers like the River Rhine. And it's also important because on terrestrial systems, water is a controlling factor for many really important Earth system processes. And one example that I brought here to you today is a simple scatter plot that relates the global mean total terrestrial water storage, or anomalies thereof, to anomalies in the yearly CO2 growth rate in the atmosphere. And this global terrestrial water storage, which has been introduced previously in the previous talk, is influenced by groundwater, but also largely by, for example, near-surface soil moisture conditions. And what we can see that there's a strong and clear relation to the yearly CO2 growth rate. And we can, for example, translate this into the statement that exceptionally dry years are associated with high CO2 growth related to, of course, ecosystem respiration. This ultimately has also implications for ongoing climate change because it influences the concentration of CO2 in the atmosphere. So this also implies that there might be interactions between projected climate change in terrestrial water resources or land water availability and the carbon cycle, ultimately also contributing to interactions controlling ongoing climate change. What we can ask us now, given state-of-the-art model projections that indicate that some regions of the world are drying while other regions of the world are wetting, is whether we can already detect climate change impacts in a global freshwater dynamics. And to answer this question, we started to assemble large quantities of in-situ streamflow observations based on the collection of the GRDC, but adding on top of this. And we've been looking at trends, and we focused on regions which are highly sampled and to overcome issues related to observational noise and large amounts of natural spatial variability. We aggregated the data to regional mean trends, and we see that there are certain trend patterns emerging, like in wettening of Scandinavia or drying of the Mediterranean region. And based on this observational evidence on ongoing changes, we of course have been also interested in the question on the drivers. So there's the ongoing debate in the literature, for example, that these large-scale changes might be driven mostly by human water use, for example, water abstraction for irrigation. Or then there's, of course, always the climate change question, or ultimately maybe also a combination of both. To answer this question, we focused on this observed trend pattern, and we compared these trend patterns to simulated river flow trends in models that can account for human water and land use. And we've been comparing this to two different modeling experiments. One of the modeling experiments where global hydrology models were driven with climate model output that has been mimicking pre-industrial climate. And the other experiment was an experiment that was driven with historical radiative forcing and thus being able to pick up the most important features of historical climate change. And based on a quantitative comparison on these maps, we can show that the observed and the simulated trends are only to a certain degree similar if ongoing climate change is considered. But what about like more regional phenomena? For example, in Switzerland, so we can zoom in a little bit in Europe. In Europe, we have what I teased already before, this seesaw pattern where we have a drying tendency in the south and a wettening tendency in the north, which is visible in observations and also is picked up by many model simulations. Zooming further in on Switzerland, and now not only looking at observations, but actually projected climate change and a high emission scenario for the far future. And we see that in annual stream flow in Switzerland, there's a clear tendency towards drying, which gets more pronounced, for example, in the southern parts of the Valais region. Similar patterns are also visible in other near-surface freshwater variables, like, for example, soil moisture. What we see here is an analysis focusing on 5 macro regions in Switzerland, and each of the panels below shows change for the 4 seasons, winter, spring, summer, and autumn, for 3 different time frames. So in short-term time frame, and medium-term time frame, and long-term time frame in 2085 is the label. And also here we see a clear tendency towards drying with variability across regions and also across the seasons. But what is also apparent is that there's a large spread in these projections. And the spread is partially related to internal climate variability, but it's also related to uncertainties in our best available models today. And therefore, I think it's imperative to develop further observational constraints for reducing these uncertainties. And this directly links up to the mandate of GCOS, which is to provide better observational data products, either in the form of in situ monitoring or maybe also in kind of blended global data products. At our group, led by Sonja Sine-Viratne at ETH Zurich, we've been trying to contribute to this effort, for example, by establishing a soil moisture monitoring network in Switzerland with stations strategically placed mostly in the Swiss plateau. And in these stations, we are measuring soil moisture profiles continuously over time at a variety of depth, also with a mix of different sensors, also contributing to research on sensor longevity, for example, and sensor accuracy. The network was established approximately 10 years ago, and since these are sensors buried deep in the ground, they are, of course, also difficult to maintain. And in electronics buried into the ground is, of course, also prone to corrosion. And what people at our institute in the context of a GCOS project did is to focus on or investigate which of the deployed sensors are still operational for different sensor types. What you see here is an overview of all the available sensors in the network alongside depth and alongside size, and each of the panels would indicate a different sensor type. And we see that there's like an increasing number of non-functioning sensors. And currently, people are evaluating sensor technologies that allow for a more efficient, for example, replacement of broken sensors. That could be probes that can be removed more easily from the ground, for example, without digging an entire hole. Just to give you an insight of what this monitoring network is able to do, I show you here, like in gray, the long-term seasonal cycle of the SwissMex stations. And a few years are highlighted here. It's always starting with 1st of January, ending end of December. And in orange and red, there's, for example, exceptionally dry years that have emerged in the recent past. And then this year, apparently, was, I think most of you remember, was not that dry, but rather wet in summer. Moving on from like this kind of sensor-based or station in situ monitoring-based like data products, there's of course also the question whether we can have alternatives, because we cannot have everywhere monitoring stations. And also within the context of GCOS projects, the capabilities of alternative sources, like from remote sensing sensors or from reanalysis, have been investigated. In this particular example, the remote sensing sensors, unfortunately, failed to capture the most extreme events as seen by the observations, and a data product based on global reanalysis, so basically a global land hydrology model that is driven with atmospheric reanalysis, captures the extreme events, but there seem to be issues with the shape of the seasonal cycle. So I believe that there's really a need to advance the capabilities of global monitoring products, and we try to contribute to this. For example, by first investigating how the availability of stations look like. And what we have here is an overview on the best available collection of global soil moisture stations, and you see in blue operational stations, in red discontinued records, and we see that there is a big geographical bias in station availability. And we can also project this not into a geographical space, but into a climate space, for example, by looking at the station density per square kilometer in Köppen-Geiger climate classes. And also there we see that there's like large parts of the climate phase space that are not well constrained or well covered with observations. To overcome this category of issues, we are working on machine learning-based approaches that can help us to fuse these sparse in situ observations with more globally available data products, for example, on precipitation and temperature. We've been experimenting with this using streamflow observations, and we are actually able to deduct from these sparse observational networks global data products that can actually capture the dynamics of runoff at this location with great accuracy. We, of course, also validate these products. All the orange boxes are different flavors of our data-driven estimates, and higher numbers are better compared, for example, to alternative products that we have been using for benchmarking. I want to close this short presentation with a brief look into the structure of these global data-driven runoff reconstructions. We are looking here at, in the first column, runoff values at specific points in time in the past. In the second column, we are looking at a drought index derived thereof. Redder means drier. And finally, we are looking at the rank of the anomaly, so the question how extreme this drought event was compared to the past. And these global data-driven reconstructions really allow us to, for example, in Europe, monitor our surrounding more precisely, or in the second case, it's an example of the US Dust Bowl in the 1930s, characterize the situation in the past, maybe helping us to understand what has been going on in climate dynamics then, and also help us to explore some of the under-observed regions where, for various reasons discussed before, station density is unfortunately not as high as we'd like to. With this, I'd like to conclude that terrestrial freshwater is a relevant component of the water cycle and a controlling factor of many Earth system processes. Anthropogenic climate change is already impacting freshwater dynamics at the global scale, and feedbacks at the planetary scale are clearly possible. And at last, their water cycle observations are crucial for monitoring change. And I believe that data science methods can also help us to fill in missing gaps in situ observation networks and possibly also in satellite observations. With this, I'd like to thank you for your attention. I'm happy to take questions.
Thank you very much, Lucas, for these insights into the observation of freshwater and soil moisture, respectively, despite the bitter truth, as you stated it. And also thank you for the reminder of the beautiful summer we had. I have a few questions here on my iPad, and I'm starting with a question by Martin Hölzle. He's asking, how well is the soil moisture situation not only in Switzerland, but also for other regions in the world? How are mountains observed worldwide?
Yeah, so I think the overall message is that the available observation networks are very sparse. So there's like the high station density of still operational stations are in the US and in Europe. And in other regions, there's surely like small individual efforts, but they are often not fed into global databases, for example. So there's probably both a lack of observations being done and also a lack of mobilization of the observations that are there.
And I have a second question pointing in the same direction as the previous one. Your soil moisture example omits high mountain areas. Is it omitted just because sensing in mountains is harder, or are these areas simply not that significant?
So mountainous areas are, of course, very significant in Switzerland, but with the design of monitoring networks, they usually come with certain objectives. And the objectives of the SwissMax network were clearly also motivated by the investigation of land-atmosphere interactions, where, for example, dry conditions in summer contribute to, for example, heat wave dynamics. And the SwissMax network was partially designed, for example, to investigate these type of processes.
And one last question I have is, what is the influence of several dry years on the long-term soil moisture at a certain place, and how fast a certain site can recover from dry years?
So this definitely depends on the size of the anomaly. So if storages are depleted completely, it of course takes longer until these storages are replenished. And then it also depends on the local climate. So if we would be in an overall humid climate, it will take less long to replenish the storages, of course. For example, if we consider this year with quite significant amount of precipitation, this clearly would have contributed to replenishing storages of previous dry years.
Good. Thank you very much, Lucas.
Welcome.
Back to me.
Back to you.
All right. Thank you, Lucas. Next up is Francesca Pellicciotti from the Swiss Federal Institute of Forest, Snow and Landscape Research, VSL, where she's a team leader in the research group Mountain Hydrology and Mass Movements. Her contribution to the discussion on the water cycle today is on glacier changes and water resources in a changing climate in the water towers of the world. Francesca, good to have you with us.
Thank you very much. It's very nice to be here. I was asking myself, that is a long title, and I cut it there, in fact. I was asking myself why I've been invited as a national speaker, because definitely today I'm moving the perspective to the global water towers, where together with my group I've been working for many years, and we've been looking at glaciers and water resources in those regions. So let me start from the big problem that we tackle. How glaciers are responding to climate is one of the most important questions of climate change research today. Glaciers provide water for millions of people downstream, and this is an emblematic example of high mountain Asia that you see there. The map shows in blue the amount of ice, and in red the population density. And you see that high mountain Asia contains the third largest ice masses outside the two poles, but it also, unlike the two poles, contains a lot of people. Those glaciers support the economy and agriculture of China, India, Pakistan, Afghanistan, etc., etc. in a situation of often political instability, poor governance, poverty, and increasing pressure on water resources. Glaciers are also the only source of summer water in dry areas, especially in some of the areas where I work, so the Andes, for instance, the Cordillera Blanca in Peru, the dry Andes of Chile, but also Tajikistan, where we work together with Martin, and Tibet and other regions in high mountain Asia. Glaciers support key ecosystems, and I would say this is the case everywhere, and they are also key contributors to sea level rise. So if this is the big problem, how do we tackle that? Together with my group, we use a combination of field observations, remote sensing from across scale, from drones to high-resolution satellite images. There is an explosion of incredible satellite products at the moment, and models of different complexity to gain a mechanistic understanding of glacier processes, glacier changes, high-elevation hydrology. And then we use those models to project for projections of future water resources in the various mountain areas of the world. And what you see there, these are projections, I'm going back in fact just to, these are projections of glacier retreat in a valley in Nepal and the corresponding changes in the runoff up to the end of the century. I think this combination of observation, satellite data, and modeling is quite important, is interesting for the discussion we are having today in the panel, but this is where we work. Definitely we don't work in Switzerland. As I said, we also work in Switzerland, but we work especially in some of the most vulnerable water towers in the world. There was a paper by Walter Immergel and co-authors in Nature last year, where they classified the water towers of the world, the major river basins that flows from mountains, based on their importance and the vulnerability. And some of the most vulnerable are in the Andes, but especially in high mountain Asia. And you see on this map some of the sites where we work. And now to tackle this question of how are glaciers changing and how does this affect the water cycle, our work revolves around three main pillars. The first is on process understanding. The second is on, and we use for this field observations and detailed physically based modeling. The second is on large-scale glacier changes, and this is fundamentally based on remote sensing. And then the third is on glaciological modeling, which really is a synthesis of the previous two. And I'm going to show you some example of both. This is of all three, sorry. This is a glacier in Nepal. It's called Lirung Glacier. We were doing field work there. This is a drone, and this is a drone survey. This is part of a research program to understand how much those glaciers melt and how much they contribute to the runoff of the valley. These are debris-covered glaciers that you see here. And you, sorry. Oh, there is no pointer. Yes, so I start again. I wanted to use the pointer. So you might see those cliffs and ponds that form on these debris-covered glaciers that have been suspected to be responsible for anomalous mass losses. These are many orthophotos that you can use to derive a DEM, a digital elevation model such as this one, of very, very high resolution, few centimeters, that we then use for validation and initial conditions for a model like this one. This is a model this is a 3D model, physically based for the evolution of the cliff of a such glacier. We can use that to quantify the melt of those features. We also got some interesting results on which of those cliffs survive and which die on those glaciers, so which do contribute to the glacier mass losses and runoff. But the key point here is how do we go from the scale of I'm not going to use that again, from the scale of a single cliff to then the scale of an entire glacier, on which you see many of those cliffs and ponds, and then to an entire catchment or valley with many glaciers and many cliffs and ponds, and how do they affect, so how those supraglacial features affect the hydrology across scales. We use for this remote sensing and modeling. And I think I'm here today to really argue for the combination of using these three elements, observations, remote sensing, and modeling. And we were able, in that specific case, for instance, to identify the cliffs and ponds that form on these debris-covered glaciers. They are responsible for these anomalous mass losses of debris-covered glaciers. They melt up to 30 times more than the surrounding debris-covered ice. Now then, the next question is, okay, we were able to identify cliffs that you see there in orange and ponds in blue. You can map them from remote sensing. This is a glacier, a number of glaciers in the valley. But how representative are the results and the modeling results we got from the entire high mountain Asia, or for very large regions? And so this leads me directly to the next of our pillars, which is large-scale changes from remote sensing. And since I was talking about debris-covered glaciers and their importance for the hydrology, for the water cycle of high-elevation catchments, I'll stay there for a few more slides. This is a very beautiful debris cover glaciers. I was not on that one because that is Baltoro Glacier in Pakistan. It's not accessible at the moment. And until, I think, a few years ago, we didn't know where debris was, how much debris there is on the glaciers on Earth. So glaciers are becoming darker and darker. Debris is increasing in a warming climate. So what we did, and this is work that we published just last year, we mapped using remote sensing images, so this was Landsat images and Google Earth. We mapped the distribution of debris on every single glacier on Earth, above 1 square kilometers. And we also established then, we also estimated which stage of evolution the debris is on each glacier on Earth, from the initial stage, a glacier is clean, to the final stage in which glacier is completely covered by debris. That you can imagine changes completely the melt and hydrological contribution. Another example of the large-scale changes that we derive from remote sensing and physics, of course, knowledge of physics, to understand the state of glaciers and their contribution to the hydrological cycle is this one. This is a paper that we just published, and in which we reconstructed, if you look at the dots, every dot there is a glacier in high mountain Asia. We reconstructed the altitudinal resolve mass balance for all the glaciers of high mountain Asia. And if you look at the legend, red is mass losses, -1 meter per year, and blue is mass gain. And you can see that it's all red, except this famous, by now, anomalous behavior of the Pamir, if you see this, because I don't, of the Pamir and the Karakoram region. In the middle, if you see there is a yellow region and then a blue region, this is the famous Pamir-Karakoram anomaly. And this is an incredible data set that is available, that was possible to generate through a combination of remote sensing and modeling, only because amazing remote sensing data sets are available by now. For instance, we exploited the glacier velocity that was just published a year before by Amoridec and Cortes. And you can use this for these data sets for a number of evaluation. And this was, again, a combination of remote sensing and modeling to estimate the melt contribution of all the glaciers of high mountain Asia to the major river basins in the region. Now, the point I want to make here is that all the large-scale change studies by our group, but by many other groups at the moment, are possible thanks to increasingly standardized data sets from remote sensing and from observations. And a very simple one in our field of glaciologists, hydrologists, is the RGI, the Randolph Glacier Inventory. It was key for that analysis that I'm presenting there, that we had a database of a glacier inventory that was consistent, that had been validated and proved. And another key data set that is supported by GCOS is the WGMS mass balance data set. We tried to validate that mass balance for every glacier with all the possible observations that we could collect from the ground. And some of those, and some of the best, are from the WGMS. And I show you here, if you go to the supplementary information of the paper, you'll find plenty of figures like this in which we validated the simulated mass balance, the reconstructed mass balance with the observations. So our estimates are red lines with the uncertainty estimates, and then in blue you see the WGMS observations, and they are available in high mountain Asia in a region. There are few, but in a region where otherwise there is almost anything else, nothing else. And this is the third pillar of our work, and a number of other groups are working now at the interface between remote sensing and modeling. We use physically based models of the catchment water cycle, and we use them, so models that we inform with the process understanding from the field work, and that we calibrate and validate mostly with remote sensing observations. And we use them to understand the response to climate of glacier ice catchment in different climatic settings. This is an example of a comparison in the two panels. You see the projections of future runoff and the runoff contribution, the runoff component for the Langtang, which is a catchment, mid-sized catchment in the Himalaya, and one, the Juncal, which is a mid-sized catchment, same catchment size in the Andes of Chile, in the central semi-arid Andes of Chile. And you can see that in the first panel, you see probably this idea of a peak water is there. Runoff increases, then decreases, goes back to the level to the present level, whereas this is absolutely not the case for the Andes, where you can see this decline, and this is a steady decline. So people in the dry Andes of Chile and most of the Andes in South America, in fact, have to be prepared to cope with water scarcity. You can use these models. This is for a number of research, to answer a number of research questions. This is an example from the Andes, in fact, was also a different type of model. This is a much shorter period of simulations, but you can see also, this is a different catchment. You can see also there this very strong interannual variability, right? But this very clear decline. Chile was hit in 2010 by a mega drought. They declare a state of emergency. So 2010 is really when the mega drought hit. And I want to show you where those simulations come from. So this is the reconstructing mass balance for 3 glaciers in that region. And the dots indicate observations from remote sensing. And what you can see here, there are 2 striking things. The first is this period of positive mass balance that has been now confirmed also by other studies. We would never get that if we only had observations. This is the model that gives you force with the right input that gives you those. And the second thing that is very interesting we're working on at the moment is the behavior of the debris cover glacier. So there are 2 clean ice glaciers that we were considering there in blue and green, and a debris cover glacier in red. And you can see that the debris cover glacier, because the debris insulate the glacier, reacts to climate, the mass balance is more positive when it's positive. But once the mega drought hits, the debris cover glaciers has a dramatic loss of mass. It's much more than the clean ice glaciers. There is a threshold effect there, or a tipping point, because those debris cover glaciers, because of the debris, can survive at much lower elevation. Given certain anomalies during mega droughts, this tipping point will be hit, and it will contribute disproportionately to the hydrology of the catchments. This is another very interesting insight that models can provide into processes that shape the water cycle of high mountains. We know that the glaciers of high mountain Asia and the water cycle of high mountain Asia is dominated by avalanches. A lot of mass is redistributed, not by ice flow, but or precipitation, but by avalanches. And we found there that the same was happening in the Andes. So we just ran the model. So there are plenty of lines there. Just focus on the red line that just goes down like this. So if you run the model, these are the same simulations I was showing you in the previous slide. If you run the model without avalanching, you see that the mass balance will be much, much more negative. So the model will be doing everything. Well, I mean, we're predicting definitely the wrong mass balance, much higher mass losses. And this was the first evidence, I think, of the importance of considering this process also in the Andes. Thank you. Oh, wow. Or South America. Yeah, I'm going to be quick there. I'm sorry I prepared for a presentation for 20 minutes, so I'm going to skip, I probably misread that. I'm going to skip some of my slides. The point I want to make here, though, is that these model simulations are possible because of new field data. We spend months, I mean, my group by now, not myself anymore so much, but in those regions collecting field data. But also because, and this was just an example of the data we collected, but also because of this incredible amount of high resolution, higher accuracy remote sensing data, which had really pushed the frontiers, at least of our understanding in glaciology and hydrology, I would say. Models are increasingly advanced. Local knowledge is crucial because really it points to new processes, but this local knowledge needs to be embedded in large-scale understanding, and this can only be supplied by remote sensing. And the key point for discussion here, maybe too, is that long-term observatories are crucial for long-term simulations. We were able to do that only when we had long-term simulations. I was asked to provide some perspective. I will you'll tell me when I need to stop, some perspective on innovative research and potential for cooperation. I think we are at the stage now in which we really can afford a new generation of models. Integrated, holistic, physically based, hyper-resolution. This is a schematic representation of the model we are using at the moment in my group. I mean, Sonia and her group are also using land surface models. This, I think, is the future. But we need to use them at hyper-resolution, at very high resolution, because mountain processes are extremely complex. And we also need, I think, truly intercomparative studies. And they have to be intercomparative in terms of models, in terms of experimental catchment, and monitoring programs too. And I just want to provide here an example about the models. So this is one of the region that is best studied in the Himalaya is the Everest region with Khumbu Glacier. Yes, thanks. And these are the projection of volume changes at the end of the century in 3 studies, the only 3 studies that came out all together at the same time. And you can see that the projections of future volume changes in the whole region vary from 99 to 8%. And this because people, well, the different groups were using different models and empirical models. And I finish maybe with this slide. I think the last key message here in terms of potential for innovative research is about experimental catchment. Most of the results I was presenting today was from one catchment in Langtan that we equipped and been monitoring since 2012, together with a number of other groups. And I think we don't know if the results that I've been presenting are robust. Do they hold for other catchments, other glaciers in high mountain Asia? Do glaciers and glacial features have the same characteristics across this huge variety? What we've been doing is trying to equip other catchments in the same way. This has been a great effort, I have to say. There's really push for cooperation, but this cannot be done by individual groups. This really need institutional support and the support of monitoring programs such as GCOS, for instance, and large international initiatives. And so maybe that my take-home message here, or my conclusion here, and then I stop, is really that we need not only to include single observations, but also experimental catchments in observation networks. And I think, thank you very much for your attention. And sorry for being long.
Thank you very much, Francesca. Impressive drone.
Impressive photos.
Photos and film. So this is the end of LiDAR flights to get the catchments and glacier surfaces. You can do that all by video and.
But you mean no field work anymore?
No. No, just to get the DEM of the glacier.
Yes, that was a drone flight to get the DEMs, repeat DEMs, yes.
So I have a question by James Thornton. I don't know his institution. So he said, we recently proposed some potential modification to the GCOS ECV framework to reflect the specific characteristics of mountains. For example, specific priority variables. Do you think such an approach could be of some value to deliver more standardized and useful interdisciplinary observations in such terrain globally?
This is a very good question. Maybe it's for the discussion later on, I think. I definitely think that there is a need to adjust maybe the global observation network for the mountains. I was impressed by Annie's presentation and also Lucas. They were showing all the run of all the observations. There is nothing in the mountains, right? All these maps with the global observations. And I really think this was one example that I was trying. Well, I have a few more slides about this. I think one thing that we need is high elevation observations, absolutely. And in terms of sensors that we need, because the maintenance, I mean, Lucas was showing how difficult it is to maintain even soil moisture sensors, but imagine how difficult it is to maintain. And you've seen some of my photos from fieldwork in those conditions. So we need also new generation of sensors, more sturdy, able to. Well, I think this is a whole thing to rethink. And then I think we need to go from point scale to catchment scale understanding, if we want to. I mean, one automatic weather station at one point doesn't really help much if we don't have the understanding of the entire catchment. And there are more and more efforts by individual groups to set up monitoring catchments, as we've been doing in Langtan, now in Tajikistan with Martin, and with a number of other. There are many groups doing that, but this then requires a program and a program that takes all those measurements, standardized them, probably guidelines, how and what to measure. Yeah, it requires a whole thinking, I think, for the mountains. I completely agree. Yes.
So, indeed, Martin has a question. Large-scale changes, distribution of debris cover. How do you determine the thickness of a glacier from remote sensing?
Very good. So that was not in that study. There is one just now in review on the debris thickness, in review in Nature Communications. We submitted maybe a month ago. It's very difficult. This was the key unknown, right? The question is from Martin.
Yeah.
Yes. So I'm looking at. I don't know what I'm looking at, but yes, this was the key unknown, right? And also, I think there is really the potential that once we know the debris thickness, we will have to rerun all the global simulations of glacier contribution, and they will look different. So what we did, there was a paper by Dave Rounds that just published in GRL. They reconstructed it. They used thermal images and inversion of the energy balance with thermal images. There are very large accuracies. It was also very difficult for Dave to validate this. What we are doing is a combination. So we are using that data set of surface mass balance. Then we run an energy balance model on every single glacier, altitudinally distributed, using ERA5 downscale data. And then you can reconstruct millions of Earth-strong curves. For those of you who know, this is a bit of a glaciological conversation. And then you can, if you have a surface mass balance data set, that is the one I was presenting, then you can enter in an Earth-strong curve and get the debris thickness. And we'll see what the reviewers think. I mean, this is, and I know that there is another group trying to do that at the moment. It's one of the frontiers. I think we need to understand how much debris there is on these glaciers, and there will be more and more in the future.
I have a question from Mario. I think Mario Rohrer, probably. Thanks a lot, Francesca, for the fascinating presentation. Can we really say that, generally speaking, debris-covered glaciers are melting faster in dry years?
That was that finding, we are now we are running simulations here in Mountain Asia trying to find out if that was the case. That mega drought, this is also a conversation maybe for the drought expert, that was forced, this has been lasting for 10 years. So it's really a unique thing. It's an extreme event that has never been seen, nobody was expecting it, and it's not driven by temperature anomalies, but by precipitation anomalies, so by a precipitation deficit. Temperature, to my surprise, because I was expecting this is a temperature effect, because these debris-covered glaciers lie very low at low elevations. So I was expecting that this was a temperature-forced feedback, so to say, whereas it seems to be a precipitation-forced one, but probably because these glaciers are avalanche-fed. I wouldn't say that could be the case for the Alps. It really depends on the distribution and then the characteristics of those glaciers. But I think this is the next, we're going to work on it for the next couple of years. I think it's super interesting.
Right. Yeah. I'm looking forward to the synthesis discussion. You have more to say, I can tell.
And sorry for it.
So thank you, Francesca, again, for the presentation. We have now reached a short, originally planned 10-minute break, but we propose to have it a 5-minute break. So just quickly go to wherever you need to go and be back at 3:05. What time is it?
Yep.
Yeah, 7 past. Okay, welcome back everybody to the last two scientific presentations of our symposium already. So as it was the case for Francesca's talk, we stay at higher altitudes with Nadine Salzmann's talk on combining approaches for improved quality and quantity of precipitation estimates in high mountain environments. Nadine Salzmann is a senior researcher at the Department of Geosciences of the University of Fribourg, but I learned today that she will be the new head of the newly founded research unit Alpine Environment and Natural Hazards at the WSL Institute for Snow and Avalanche Research, SLF, as of mid-October already this year. So please, Nadine, the floor is yours, and we're looking forward to your talk.
Yeah. Thank you very much, Michelle, for this nice introduction. Welcome, everybody. It's a great pleasure to be here, and thanks a lot for the invitation. So what I'm going to present to you today is not actually the target of this studies was not especially for GCOS, but maybe it's about to you to decide afterwards. Some of our results can be interesting in terms of activities of GCOS. So the work I'm going to present, or the results, are mainly based on two PhDs, one from Rebecca Gugerli, who has just finished, and one ongoing from Matteo Guidicelli. And it was also in collaboration with Matteo Svizzera from Locarno, with Marco Cavella, and Darren Desley from Hydronovia from the USA. So the water cycle. High mountain areas, we have several times today already heard that this is a key region of the water cycle. It's for many disciplines, it's probably a key region for hydrology, meteorology, climatology, but also for glaciology, and that was also a little bit the main motivation for the research we have done. Because snow accumulation and precipitation in high altitudes is probably a key process for also the future behavior of glaciers, permafrost, and so on. So it's also thin air up there, so we have already heard there is a lot of data gap, there's missing data up there. And one of the reasons is because of these very harsh environmental conditions. It's very cold up there, it's windy, there is complex terrain. We also heard this morning that also you need cable cars to go up there. So we have a lot of technical challenges with common devices of measuring precipitation or snow in these very high altitudes. Access is difficult. That also means maintenance of these devices is difficult. And we also have a huge, a very dynamic environment with processes from liquid and solid precipitation, and also melt, who complicates the whole measurement enormously. As a result, in situ precipitation and snow observations at very high altitudes are typically very low in spatial and temporal resolution and also coverage. We have to deal with large data gaps and so on, and therefore also the validation of available observations is very difficult. And as a result, reliability of these observations is really very low. And this is also very nicely pointed out in the WMO report SPICE, in this solid precipitation into comparison experiment that has been finished a few years ago, where they clearly stated that there is a high inaccuracy and uncertainties of available observations in these high altitudes. So the mountain areas, the very high altitudes, are not only key regions of the water cycle, but also we have key unknowns up there. What can we do? How can we improve the quantity and quality of precipitation estimates in high altitudes? So this was with the main motivation of the work I'm going to present you. So two ways we went was one, we tried additional kind of, well, not new, but new in this field at the moment, new devices based on cosmic ray sensors. I'm going to introduce you to that and show you some results just afterwards. And also by combining different methods and approaches from different disciplines. Concretely, we used the cosmic ray sensors, and we used weather radar, we used numerical weather prediction models, reanalysis, and also machine learning tools. So I'm going to present you some results of these two ways forward. So in the focus of our research was then always a snow water equivalent, which is an integrative variable, but also an essential climate variable. And it's closely related then to incoming precipitation, snow density, etc., etc. So the cosmic ray sensor, you see here one lying in his nice white and soft bed. Directly on the glacier ice on Plain Mort. So this white tube, this is the cosmic ray sensor, and what this sensor measures is the neutron. It counts the neutrons from the cosmic ray, the second cosmic ray shower, and we can use these counts of neutrons from this cosmic ray to infer snow water equivalent. So what you basically do, you just put your cosmic ray sensor on the glacier ice, as you see on the left, and you let it buried by snow through the winter, and it measures you hourly the estimates of the snow water equivalent. So we have two of these stations in Switzerland, one of the Plain Mort Glacier since 2016, and one on Finland Glacier since 2018. And we have, in addition to the cosmic ray sensor, we have also put these other sensors up there for humidity, radiation, and so on. But this is more for validation purposes of our cosmic ray sensor. Once you're really confident in your sensor, you would not need this additional information anymore. But as we didn't know when we started with this project whether it works at all, we thought to be on the good side, we also install all this kind of additional measurements. So looking back to 2016, we have now on Plain Mort, on top, you see these hourly measurements we have since 2016. And in red, you also see the manual measurements. So in total, 22 manual measurements we did on Plain Mort, and 5 till now on Finland. And what you also see is that we have these temporary continuous measurements. And the first gap in 2017 summer, you actually also see the steep learning curve from Plain Mort compared to Finland, where we have no data gaps on Finland, but on Plain Mort we have some data gaps. So the first data gap was simply because we thought in the summer we need to protect the sensor from radiation, and then we decoupled the whole sensor, but this was a wrong decision. Therefore, we have this data gap. And the second data gap in the winter 2019 was simply because there was such a huge amount of snow that the solar panel was completely buried, and therefore we had some issues with energy consumptions. But otherwise, the device really runs so smoothly. It was a real pleasure to see the data coming in. So here's some results from since 2016 of the snow water equivalent measured by the CRS on Plain Mort compared to manual measurements. And you see that we have, I would say, an average agreement between the manual measurements and the CRS measurements of nearly 1. So we are really extremely satisfied. On Finland, we have much less information. It also seems to be that the measurements are not as reliable, but we only also have 4 or 5 manual measurements. So yeah, we need to figure out more on these performance differences between Plain Mort and Finland. Some open questions here, or some conversion functions we are using, some calibration that maybe can adjust it to the different situations and locations, some corrections functions that we use. And then, of course, as I said, in one case we have 4 observations, in the other case we have 22 validation points, so this also makes a little bit of difference. And then, of course, we have spatial variability of snow measurements and so on. But we are working on that. So, as a short review of a cosmic ray sensor, as I said, it really provides temporally continuous hourly SWE estimates at very high elevation sites. It seems to be a super robust device. Measures very reliable, so almost no or very low maintenance is required. It's kind of transportable. You saw it's a relatively small tube. It's about 10 kilos or so. So if you're strong enough, you can also carry it up to very high elevations. And it's also possible to have near real-time data. However, it's of course only a single site observation, so we have no spatial coverage unless expect the footprint of the cosmic ray sensor, but it's a one in situ situation measurements. So our idea was then how can we spatially and temporally extrapolate these SWE estimates into 2 larger areas, first across glacier areas, but then also across whole mountain ranges. And for that purpose, we included also weather radar data into our studies, then numerical weather prediction models and reanalysis, and we tried to combine all these different data also through machine learning techniques. So here just an example of towards this spatio-temporal extrapolation in Switzerland. Oops. As I said, as a ground reference, we took this cosmic ray sensor data. Then we used the whole data archive from GLAMAS, from the Glacier Monitoring Switzerland, which has a lot of snow depth measurements and also SWE measurements on various glaciers. And we collaborated with Mathieu Switz from Locarno with the weather radar and tried to bring this data, compare this data against each other. So here, just an example from Plain Mort. On the left-hand side, you see this the Plain Mort glacier outline, and the dots are the manual snow depth measurements, and then the colored squares are the interpolated SWE estimates. And on the right-hand side, you see the SWE or the combi-pressive product of the weather radar from Mathieu Switz. And when we compared now this data across here, for example, our 7 glaciers, we see that we have a very nice temporal pattern that very well corresponds, although we have some underestimation by the radar. So we then also tried to extrapolate over the whole Swiss area using the Cosmo 1 predictions. We did this by machine learning approaches to extrapolate over the glacier-wide, and we also tested this on non-glaciarized sites by SWE observations of the SLF stations. We go now a step further and try to use this at the world coverage scale by using observations, observations from the World Glacier Monitoring Service and downscale precipitation from reanalysis data from the MERA-2 and ERA-5 data. And this is work in preparation, in progress, but what we can do here is we can derive vertical profiles at single glacier sites, and especially interested again is the situation at very high elevations. So in Switzerland, for instance, from 3,000 to 4,000 meters height, where we know from glacier dynamics that we have probably a decrease in precipitation, but we actually have no data. And we can do this also for other glaciers. Here an example from Abramov Glacier in Kyrgyzstan, again, where we can very nicely show or model this information at the very high altitudes of the glaciers. So some conclusions. As I said, cosmic ray sensor can be a very promising device for temporary continuous SWI observation at very high mountain regions. It can be used also for validation of other devices. Also a conclusion is that with only one single method, it's probably not sufficient to use in these very high altitude terrains. We need to combine informations, and with that we can hopefully in future improve the quality and quantity of precipitation, liquid and solid information in high altitudes. And just some perspective, we are just a new device based on muon counts now instead of neutron counts, which is a device which is even smaller and lighter, even more robust, even cheaper, and probably even more reliable and precise. We have first year of data on Plan Mort, and we have just submitted to the cryosphere discussion, and it's open for discussion, and have a look and join us in the discussion and shaping these new devices. Thank you very much.
Thank you, Nadine, for this insight. It was really interesting to see how far we are in terms of realizing kind of an automatization of SWI measurements. Mm-hmm. I have a few questions here, and I'm start with a question by Tom Peter. Does using the cosmic ray sensors assume the extraterrestrial cosmic ray flux to be constant? This is not fully true. Depends on solar activity and potential cosmic events. Does this influence your measurements?
Yeah, well, I'm not an expert in this kind of field, but this is true, yeah. It's not constant, and therefore we use the information from the Jungfrau Joch Davos, where we calibrate our measurements with the changes of the incoming cosmic ray radiation with our device. Yeah.
Okay. Then there is one question by Mario, or I assume.
Yeah. Hi, Mario.
Thanks a lot, Nadine, for presenting these innovative solutions. Of course, we would be interested to incorporate these cosmic ray sensors in our vegetal measurements. What are the approximative costs of these sensors, maintenance included?
Yeah. So the Snow Fox, this is the cosmic ray sensor we used. It's about 10,000 Swiss francs, the tube alone. But these muon counts now, they would be about half of the price. It's about 5,000 Swiss francs, the pure tube. Mm-hmm. So, but the more we use, the cheaper it's probably got if economy is right. So you're invited to buy many of them, and then the price will go down.
Then we have a question by Christoph Malti from SLF. Uh-huh. Did you ever use hourly CRS data? Do they temporarily agree with other precip measurements like snow depth radar, precip-GOG?
Yeah, I mean, what we found so far is that they agree really quite well. And I mean, we had many discussions. I mean, if you compare, the problem is always where is the truth. I mean, you can compare, and then you see whether you have a good, if they correlate well, and mostly they did, and where they did not, we tried to find out why, and then you also need to find out which device or which measurement is now the correct one. I mean, it goes into the same direction with manual measurements. I mean, do we trust more manual measurements when we go up there and dig snow pits, or do we trust more the cosmic ray sensor? It's a very good question, and I don't have the answer. I mean, it depends also on the people who dig the snow pit and the weather conditions while you're digging. And I mean, I think the good thing is if you do measurements and if you do model, I mean, if you do both, you really get the feeling about the uncertainties on both sides. If you only model, you also always think, oh, well, observations in the field must be super correct, and vice versa. So, yes, where's the truth? That's a good question. Yeah.
So we have one question by Sonja Zemiratne. How well are the SWI measurements captured in models?
How well are?
The SWI measurements captured in models.
In which models?
It was the same question as before.
Oops.
Models or observations. Okay. Then I see that Bertrand has a question with the microphone.
Yes. Thank you very much. Thank you for this presentation. Actually, SPICE, the solid precipitation, intercomparison experiment was exactly based to understand how we could improve the rain sensor measurement in the Alps, for example. So now we have learned from that SPICE experiment that we can define a transfer function that takes into account the wind, the temperature on the rain sensor detection. And we have equipped a number of sites with this solution. And we are in a way of processing this data. And of course, this combination of your observation, these new types of observation, trying to understand what happens on the rain sensor would be essential, actually. Mm-hmm. I truly appreciate your presentation, and I think it gives an opportunity for Meteo Suisse to do a better job in the future, thanks to you. Thank you very much.
Thank you very much. Yeah.
I quickly check the audience here at Centrum Paul Klee if there are more questions. Otherwise, I hand over to Andrea.
Thank you, Michel. Thank you, Nadine, again.
Thanks a lot.
We move on to, is our last speaker of this session, Damien Bouffard, Swiss Federal Institute of Aquatic Science and Technology, EAWAG. His research is tied to lake ecosystems, and Damien's contribution today is entitled Coupled Information Sources Nurture Water Quality Studies and Services. Please, Damien.
Thank you. So I would just add something. This is a joint presentation with me and Daniel Odermatt, also from EAWAG. And this is a joint presentation because what we want to show today is really the benefits of coupling different information sources when it comes to understanding our ecosystem. By ecosystem, today we will be focusing on lakes now. And I will start with this pie chart showing basically some of the main ecosystem services that are provided by lakes. You do not have to look in detail. What I want to highlight is that you have, like in most ecosystems, a lot of conflicting use. You can think, for instance, that most of you are using lakes for drinking waters, and this is the same. Most of you are also releasing wastewater in lakes, and that is assimilated and diluted. So you see the conflicting use that lake manager has to constantly solve. On top of that, basically, these lakes, these ecosystem services are being perturbed by local forcing, and I would like to insist on land use, so that is on the watershed. each time you change something or you modify something on the watershed, there is a signature on sooner or later in the lake. So that's one perturbation. And the second one, which is well known now, is the global one, the climate change. And basically, lake manager, they have to face a system that is perturbated, constantly perturbated by at least these two drivers. And if you look now back to this pie chart, I would argue that this pie chart can be a little bit misleading. This is a pie chart that you see for ecosystem services. You see also for sustainability assessment, because with this pie chart, you do not recognize that those systems are highly dynamic. And we will discuss the fact that they are highly dynamic, so there are some long-term trends that we need to understand, and also some short-lived events that are also very important for lake managers. So for this, we need observation. So let's look at what is provided or suggested by GCOS in terms of essential climate variables. For lakes, we have 6 variables. I will not tell you, you can just have to read. I will just start by focusing on the lake surface water temperature, so lake surface, with a requirement measurement uncertainty of 1 Kelvin. And if you are looking a little bit at the temporal evolution of the thermal structure on a lake over 1 year in Switzerland or at any mid-latitude, this is the kind of heat map that you will get, and I don't need to detail. You clearly see in the color code is for the temperature, with blue being cold temperature and red warmer temperature. What I want to highlight is, yes, you have a temporal evolution of the lake surface temperature, but if you look in summer, you have a very strong vertical thermal gradient between the surface warm water and the cold deep water. And this stratification during the summer leads to a deep water, which is basically disconnected from the surface water, and maybe more importantly, that is disconnected from the atmosphere. If you're at high altitude, and we have discussed this a lot today, you may have some ice also in winter on top of lakes. So if you want to monitor this, you need time series of surface temperature. Good, we have. You also need, at the very minimum, estimate of the bottom temperature, and if you can resolve the temperature over the water column, this is even better. And with this, you will be able to get a time series of the duration of the summer stratification, which is again important because this is giving you the timing when the deep water is disconnected from the atmosphere. What you need also to know is, for high altitude lakes, basically the duration and the change in duration, the ice phenology. I'd like to explain one more time why this is very important to not only follow the lake surface temperature, and I will give a practical example. Let's try to follow one fish. This is not my expertise. In the future, in a lake where basically the lake is forced by climate change and also excessive land use. In summer, this fish will not be able to stay at the surface because it might be too warm for the species that we are following. And also in summer, because of the excessive land use and the increase in the duration of the stratification, we may have an extended period and sickness of hypoxia in the deep water. And so basically what we have as a consequence is a shrinking in the ecological niche for this given species. So we need more than the lake surface temperature. We need also, very important, to know the evolution of the thermal structure. And we need that not for one lake, but for all lakes in Switzerland. So that's probably a lot to ask. So that's why we need to combine the in situ observation with some other sources. And I will start by presenting what we can do by using hydrodynamic model coupled with in situ observation. And I will just give an example from a recent BAFU project where we try to basically provide some scenario regarding the future of the lake temperature based on the downscale CH 2018 climate change scenario, basically with 3 greenhouse gas emission scenario from 2.6 to 8.5. If you follow the 2 figures on the left, what you have is we decided to follow 29 lakes at along an altitudinal gradient. And what you see here is each line represents the mean result for each RCP scenario of a given lake. And I think the result is very clear. Basically, the trajectory in terms of lake surface temperature is governed by the greenhouse gas scenario emission that in the end we will follow. If you want to look at the same figure on the right, so the polar plot, here basically we just listed the lake from 1 to 29 with the increasing altitude. And you see the same result, that basically the increase in lake surface temperature will be the same more or less in some in lakes, and will be depending on the RCP scenario. The story is a little bit different when it comes to bottom temperature or lake stratification, and that's what you can see on the polar plot on the left. And now you can really see 2 clusters, one for the high altitude lakes. High altitude lakes, this is not so high, we stop at 2,500 meters. But you see that those lakes are way more affected in terms of the duration of the summer stratification than the low land altitude lakes. And basically, we can explain that by looking at also the duration of the winter condition or the duration of the ice cover. And we can take the example of Lake St. Moritz, where basically, depending on the RCP scenario, again, we will have a strong or a moderate decrease in the ice cover duration. So basically, by using a combination of in-situ observation and simple 1D hydrodynamic model, we can already provide some interesting trend in terms of the future of the lake thermal structure. So the general trend. But things are changing very fast. And to show you this, I would like to switch to another project that was led by Daniel Odermatt. That was a project funded by GCOS. And the goal was to make a Swiss glacier lake inventory. If you look at this map on the left, this is an aerial photo taken by the US Army from an airplane in 1946 in summer, and you see a lot of glacier. Let's look at the same place in summer still, but more recently, and you see that there is no more glacier, and the creation of a lot of new lakes. And basically, Daniel's team, what they were trying to see is the temporal evolution over Switzerland, over the Alps, of the creation of new lakes due to the retreat of glacier. And what you see is that you have plenty of new lakes created in Switzerland at high altitude. And one important result is that there are more glacial lakes that have been formed over the last decades compared to any previous decade. So we can still, based on remote sensing from airplane or satellite data, we can also access to long-term trend. And one of the conclusions that we have by looking at the recent past is that things are increasing faster and faster. So that's for the long-term trend that we can monitor by combining remote sensing and in-situ observation, or modeling and in-situ observation. I would like to switch to basically the short-lived event. What I mean here is events of a day, a week, a month, so things that are important from a biogeochemical viewpoint, and that are also very important for lake manager, for instance. And I will use an example from another ECV, so the lake color, or the water living reflectance. And from now on, I will focus on Lake Geneva that you see here. And here we are just following the water leaving reflectance at 665 nanometer. Doesn't really matter. For me, I'm biased. What I see a very strong horizontal gradient. And I see also some structures. And this tells me that this is very important to know basically what happened before and what happened after this satellite image. And this is fundamental to really being able to couple this satellite image with hydrodynamic model. This is something that we started a couple of years ago with a practical example on a calcite precipitation event on Lake Geneva. So that's what you see, I think it was in 2014, with the Landsat satellite, RGB color here, and you see this whitish, milky color on the eastern part of Lake Geneva. This color is clearly an indication of calcite precipitation event, but we also add some information from the field in situ observation a couple of weeks before and after, and we could observe a depletion in calcite, so really showing that there was a strong sedimentation of carbon, so this is important also for the carbon budget of lakes as a source or a sink. So we could really link this event to a calcite precipitation event, but there was still, by looking at this image, some feeling that the Rhone River, the river that we see on the eastern part, was probably contributing to something. So for this, we added a 3D hydrodynamic model with a particle tracking on it, and we could track back that basically the fate of this calcite precipitation event was actually related to the Rhone River. And so specifically here, what our hypothesis is that the fine particles coming from the Rhone River in June at that time was acting as a nucleation point for the lake process, which was the calcite precipitation event. Okay, but this is only interesting if this kind of coupling of remote sensing product and 3D hydrodynamic model can be done in operational mode. So I mean in near real time. So we can really help lake manager. And the second point is, in the end, that will be really useful if this is not only us doing that, but if all the data and all the product are easily and openly accessible. This is something that we started 8 years ago, I think, with Meteolex, which is a website where basically we put all our hydrodynamic results, so from lake temperature and lake circulation for a couple of lakes in Switzerland. And basically you have access and you can download data, hydrodynamic data in the past and also in the next 5 days. Here, with this website, really the focus is on the hydrodynamic modeling part. So basically the in situ and the remote sensing product, everything is assimilated for the model. This is one way to see the problem, but we decided to change a bit our way of thinking and to work on an open data pipelines for lakes data, for research-based lake data, Data Lakes, which is also a web-based application, where the idea is to be able to search, visualize, download any kind of research-based data on Swiss lakes. And here now, we do not focus on modeling part as an end product, but we put the outcome from the model in the database as we would put the remote sensing product and the in situ data. And this is what you can see as an example at the bottom, where basically you can select different layers automatically in near real time. So here we just choose, as an example, an algae bloom, so from the chlorophyll A product from Sentinel-3, and you see the algae bloom on the northern part of Lake Geneva. And if you follow the white line, basically you can see that this algae bloom is being advected by a 2-gyre system that we have on Lake Geneva at that time. So we can really look at the fate of this process. I can't resist showing you the news if you speak French and if you were in Swiss Romande from last week, where there was apparently, according to the newspaper, some smelly algae, an algae bloom on Lake Geneva with a fantastic image from Sentinel-2. This is a fantastic one for lakes in Switzerland. And this is to show you where we are at the moment. Basically, we could, in real time, basically overlay the satellite product from chlorophyll from Sentinel-3. That's the color-coded blue and green representation that you see, and the lake circulation from the 3D hydrodynamic model. And now, the next step is to be, so we are already able to continue this to get the fate of the algae bloom in the next 5 days. And the next step will be to run some inverse model to try to locate some potential hotspot for initiation of this algae bloom or for pollution, the source of any pollutant. I will finish by just 2 points. Probably more environmental climate variables are needed, but there is a solution. It's also to try to use more systematically a combination of the different information sources to really get an integrated view on the ecosystem. And that's what we try to do by also facilitating the access to the data to really being fully open, fully transparent, reproducible, and so on. And I listed 3 examples of websites where you can participate if you want: Meteolex, Simstrat, and DataLex. That's for the standard EAVAG presentation. On a personal level, I think it's fantastic to have observation and high-level prediction. We need to improve, but if we want to be successful and not useless in the end, we need to take action.
Thank you very much. Thank you very much, Damien. I have a question from Martin Hölzle. So how is the development on a worldwide scale? Are there any observations worldwide? And how does the warming look on a global scale if there are measures?
Yeah, so this is improving a lot since a couple of years, especially with some networks like GLEON. We have more and more a better view at a global scale. We have also more and more 1D coupling between in-situ observation and 1D model to get at global scale the evolution of the thermal structure on lakes. There is also an initiative, EasyMIP, which is very interesting and which is going into that direction. In terms of 3D modeling and coupling with remote sensing, I'm not aware of any initiative at a global scale. What we are trying to do now is to increase the number of lakes for Switzerland and in the Alpine region.
Mm-hmm. Excellent. Any more questions?
Otherwise, thank you again, Damien. And at this point in time, actually, thank you again to all the speakers of this water cycle session. We come to our final Meet the Speakers session now. One last time, we encourage you to really use this time slot and to interact with our speakers on GatherTown. They are virtually present until 4 o'clock. At 4 o'clock, we will start our recap session our last synthesis discussion before the recap session, and then already the closing part of this symposium. So with this, I'll leave you to the speakers. Please visit them in the Meet the Speakers room, and see you back here at 4 o'clock.
ask all the speakers of the water cycle session to get on stage and have a seat. Welcome back, everybody. We are just getting ready for the last synthesis discussion. I hope you had a good yet short break, and I hope you had a chance to meet the speakers and that the system worked fine. Note that after this discussion block, we will launch a recap session in which the international keynote speakers will give their synthesis in a brief 5 minutes. And this will prelude the final closing panel discussion with some top-level management representatives of Swiss environmental institutions. And so we are now approaching the really important part of our symposium. And I hand over to Annie for this moderated discussion. You will have 25 minutes. We will give you a sign after 20 minutes that you have 5 minutes to go. Please, Annie, take it over.
Okay, thank you very much. It's a very difficult exercise, especially for me, who is not an expert of all aspects. Anyway, we'll try. As you have seen and as you know, the water cycle involves a very broad range of topics. So it's I don't think we will have time to address everything in 20 minutes. So I would like to, by the way, instead of speaking myself, I would like to prefer you to ask you questions and each of you respond. So I have prepared maybe some naive, I don't know, some questions that I would like to ask to each of you. The first one is, what is, according to you, the most urgent science questions scientists have to solve concerning the water cycle? Is it to study extreme events or the role of the water cycle in climate, or a question about water resources? Another question. So I list my question first. Another question is, in the context of this specific symposium, which is organized by Météo Suisse in the context of GCOS and the Global Atmospheric Watch, what is, according to you, the most important contribution at the national level, or that is of Switzerland, in this context? Another question is relevant to societal aspect. In the domain I know more, we clearly see that there is a gap between the science products and what people in charge of decision making, or in the context of the water cycle, but for example, water resource management, there is a gap between what the science is able to produce and what they need. So what is your opinion on this topic, in particular for concerning the water cycle? So we can go first to this, to listen to you about this general question, and then we can go into more details. I have noted a number of recommendations from each of you during your presentation, and we can address them afterwards. So maybe, I don't know if we start on the left or on the right. Let's, or maybe women first. So.
Yeah. You want to start?
No. Yes.
Yes, I just noted you have 3 questions, and I noted the first one. And the first one is, what is the most important question that the research community should address?
Yes.
I have a biased point of view here, of course. I mean, I talk for my discipline. But I think this goes beyond glaciers and the cryosphere. I think it's extremes. You mentioned that. From some of our work on the glaciers, both in high mountain Asia and the Andes, we started looking at this. Well, we saw mega droughts, for instance. We saw that tremendous mega drought in Chile. And there are contrasts, and we don't know what the role of the cryosphere during those mega droughts is. We have no idea, in fact. There are no studies, also because mega droughts are unprecedented. There is a paper by Spinoni and co-authors a couple of years ago that mapped severe droughts worldwide. But we really don't know what the role of the cryosphere is there. There is also very little knowledge. In fact, I mean, we have experts in this room, Sonia and Lucas, about droughts. But droughts in high mountain regions, I think, are completely unknown. And there are even contrasting hypotheses on what the role of the glaciers is. There is an hypothesis. There was a paper again a couple of years ago said, yes, glaciers are buffer of droughts. So in fact, they enable this sustained release of water. And there was a very recent paper. They focus on a sustained drought, and by mega drought, I mean unprecedented events, but they last more than 1 year. So it's not a heat wave. It lasts more than 1 year, so that there are cascading effects. And they were saying, no, where you have storage elements such as glaciers, in fact, then the precipitation deficit is amplified, and you have this acceleration of the mega droughts. I think this is a super interesting topic, and I think extremes is what we should be looking at if we look at if we talk about the water cycle.
Do you want to address the other question now or later after? Okay, so maybe we continue and then.
I will answer a bit differently because I think it's always field specific. I think what is missing is really an integrated view on the question and more interdisciplinary work. And I think you were mentioning during your presentation the importance of catchment. Studying the catchment. I think this is the kind of thing that is really missing, having all the discipline trying to work together. So that's maybe less of being at the forefront in our respective discipline, but trying to see how our knowledge can be easily transferred to the other to try
more
to really close this water cycle.
Interdisciplinary research.
Yeah.
Yes.
So that will be my suggestion as a priority. Then I have my own research question as well. But
I completely agree. I mean, I had a slide, my last slide, which I didn't get to, was exactly about this. And my questions were, how can we foster that interdisciplinarity? And I really think I had that slide, we need a new generation of models, I think, and models that are not just for glaciers, for snow, for the lakes, right? I mean, we need the super models, and I think we are at the stage that we can afford them, computational in terms of knowledge. Yes, I completely agree with that.
Yes, I would like to raise my hand again for the very high altitudes, actually, and really for precipitation especially, and snow up there, because we really have no idea what's going up there. I mean, we know elevation-dependent warming, for instance, but we have no idea what's about elevation-dependent precipitation in the very high altitudes, and it's so much key. I mean, also for glaciers, we have also mass balance. We have a lot of melt information, but we have purely no information about accumulation. It's also important for permafrost. I mean, if you have the isolating snow cover up there or not, it makes a big difference in the evolution of mountain permafrost. And not even mentioned now the whole water supply and hydrology. So I'm really asking for long-term measurements in high altitudes, and that also needs money and resources, and not only for infrastructure and not only for 3-4 years, but it also needs men or women power to do the measurements up there. And on a longer term perspective, I mean, what I just presented was based on a Swiss National Science Foundation project. This is super great, but it's over now. We will see that we can continue, but it's difficult for universities, and especially also small universities.
You mean that we have the technology, but not the budget? It's what you mean?
Yeah, we have. I mean, we can do better in technology. Still, there is a lot of air for improvement, but we don't have the money and also the sources for the people who. I mean, someone needs to maintain and to do the measurements up there, and this is really missing. And without observations, real observations, we can only guess about the processes. We need these basics.
Okay, good.
Thanks for preparing what I was going to also highlight as I think in a really important science field, at least for me working at the Institute for Atmospheric and Climate Research, and this is to really advance our capabilities to monitor ongoing climate change or ongoing global change in the water science sector. And then not only having technologies for monitoring this and sharing monitoring information regionally, but also worldwide, but also developing tools that help us to interpret the monitoring outcomes. So this can be, for example, methods for attributing change to specific causes, and then maybe also tools that help us to enhance monitoring products that come from certain sensor platforms or in situ observing systems by better ingesting this information, either in physically motivated models through data assimilation techniques or merge the information with other information to derive observational products, ideally at higher resolution and high accuracy, of course.
Okay, thank you very much. I see that time is running fast, so maybe I would like
just
you to
add one thing. Maybe just going back to these high altitudes, maybe we should also, as this is an interdisciplinary effort, we really also should think about creating kind of super sites who are taking into account all basic variables from all cycles. I mean, Reto this morning also raised his question, not only about water cycle, but also energy and radiation cycle. Yeah.
Okay, so I don't know if you want to address the other two questions. Maybe you can discuss the two together. Also, they are completely different. So the role of Switzerland in this issue problem, because I think as a foreign person, I am interested in knowing that, and also the societal application. I would like to have your opinion on. So if you can be short, because I think we still have. 10 minutes at most?
Yes. So I'll be short. I don't know if I'm the most appropriate person to answer your second question, so the role of Switzerland. I did my PhD in Switzerland. I developed a model in the Alps, and then I moved to work in the rest of the water towers of the world. I think Switzerland has incredible infrastructure for research. It has an incredible monitoring network, so this is the best place to develop models, I have to say, and to test them, etc. It has also a reputation. But then I think Switzerland can not only look at Swiss problems.
Yeah,
I think Switzerland should be placed to lead in research on the water cycle in the world. Maybe it's a bit biased point of view. In terms of producing science that is useful for people, we work on water resources, and more our projects. I have a project in Peru which is on Peruvian glacier retreat and water scarcity. So what is the impact of these changes on the water cycle, on food production, energy production, and ecosystems? I think it's fundamental to work with the stakeholders, as they say. It's very difficult. And as a scientist, it's super difficult for me. I mean, it's already difficult to talk to another discipline and to imagine to practitioners on their indigenous communities. But it's a challenge that we have to raise too. I think it's the only way we can go. Keeping an emphasis on fundamental science, though. I mean, it has to be both. It cannot be only applied, it cannot be only fundamental, I think.
Okay, thank you. I fully agree. We have to work with these people, I mean, the stakeholders in general, to define what are the need, because what we produce from research is not necessarily relevant to the need of this.
I think we need both. I think we need to follow also the blue sky science and the ideas and the research agenda, and we need to talk to them and then find them.
But it's a difficult...
it's a difficult, yes. But I think it's also exciting. I think race to the challenge.
Okay, so what is your opinion on this?
Yeah, I will maybe focus on society and science. I think we have to be clear that now it's not possible to end the project with a paper. We need to communicate, especially in environmental science, we need to communicate to a broad audience, to do some outreach when it's possible, to really help the society to understand the problem, what we are doing, and improve the level of understanding. So I think this is something that is very important. And I think this is done more and more in Switzerland. When you look at the funding at SNF and so on, this is really possible. We get some training, we can get some money to do some science outreach. So I think this is going in the right direction. When it comes to discussing more with the public, I think there is something that is complicated, is that, especially with climate change and so on, this is very quickly emotional. And we like to quantify things, and we probably need the support, and we need even more interdisciplinary study. We need probably to work with social science and so on to really learn on how to pass correctly the message. So that's what I would say.
Thank you. So.
Yeah, trying to be brief. So the role of Switzerland, I believe that Switzerland has the potential to act as an international role model in terms of best monitoring practices, for example, both on technology side, but also maybe also on data availability and data sharing side, both for researchers and practitioners. And I think we've also seen like great examples of this. Or mention of this today, like for example the Solar Roof website, which is maybe not related to water cycle research, but similar projects could be done, for example, for flood warning. And then in terms of societal relevance, I believe that operational and actionable data products coming out of our research is something that for whatever component of the water cycle can be of great relevance for societies and practitioners. And this could be in flood forecasting or drought monitoring platform, but also could be, for example, useful data products and snow water equivalent that help maybe hydropower companies or so. But having these products available, easy accessible and operational, I think, is crucial for making the best out of them for society.
Yeah, maybe just once again, I mean, Switzerland itself likes to sell it as a mountain country, so I think we should take this opportunity and also push them to support research in mountain countries and high mountain research in Switzerland, but also abroad. I mean, this is what we stand for also worldwide. So we should also do something in this regard.
Okay, good. I don't know how much time we. 7 minutes? Oh, it's a lot. Okay, so. I noticed from the presentation a few recom, so I can just mention what I noted. Maybe it's not, I don't know, it's probably incomplete. I think from your presentation you said that in situ observation are crucial, and we all agree. But we know that there are many gaps. So what do we do? And also, you mentioned that. You mentioned data science method. I understand artificial intelligence methods could help to fill the gaps. So can you comment on that?
Yeah, sure, I can comment on this. So one thing is we have to, of course, we cannot go back to the past and remonitor, but we can analyze the current state of our observational networks, and maybe we can see where it might be worth strategically to invest. Like, so there was, for example, in relation to the soil moisture monitoring that I showed why the mountainous areas were left out. So maybe ideas like this could then spark like efforts to fill in the gaps both nationally and internationally. And then the second question was related to what to do with the sparse observational networks, or we can maybe apply a similar argument to remote sensing data with swaths or not being able to see through clouds. And I believe that with modern statistical learning tools, and this comes on different labels, artificial intelligence, neural networks, deep learning, there are many methods out there. We can infer relationships between variables that are observed and variables that are not observed quite accurately, and these can help to fill in gaps, at least to a certain degree.
Thank you.
Annie, can I just add
sure.
something to what Lucas was just saying? I think I read somewhere in a paper, I don't remember when and where anymore, that models are the best interpolators if they are sound models. I mean, you have sparse observations, you need to test that your model is doing well there, and then your model can give you the rest. If the model has the physics inside, so to say, this is really goes back to is a model including all the processes, because if it's not, then of course through calibration you compensate for those. But I think if we push also on the modeling side, the two things have to go together. Then we can use models to interpolate the gaps. We can't measure everywhere, right?
Yeah, so this is something that's commonly done in atmospheric sciences and through atmospheric reanalysis, for example, where weather models are forced through observations using data simulation.
But also hydrological model or glacial.
Yeah, and there's definitely scope to further develop the field of data simulation in land hydrology.
And I think the quality of the models. I think that we can discuss.
Okay, so from your talk, Francesca, I noted several things, but just one point because we don't have much time. You said we need to go from point scale to catchment scale. Can you elaborate a little more?
Yes,
you did that in your presentation, but just as a synthesis.
Yes, I was talking about observations and monitoring, because all the modeling we do is for...
Yes,
well,
definitely.
All the modeling by definition, I would say, is almost... Yes. I was thinking about that. I mean, that having just a measurement or point measurements could be... It's a bit what Damien was saying, that we would need... or Nadine mentioned super sites, right? I mean, catchments where you can measure more than one thing. This fosters collaboration and interdisciplinarity, I think. But also one single point, I mean, you can constrain a quantity at that point, but it doesn't tell you anything. It can tell, it depends on the measurements, but has the temporal variability, but definitely doesn't have the spatial variability. And precipitation, for instance, which is a key unknown, I completely agree, is the largest uncertainty in most of the modeling, at least hydrological modeling, but you need the spatial fields. I mean, we had an example that we had a couple of pluviometers, and WRF simulations would give a pattern like this, and another model simulations would give a pattern like that. And both were reproducing those 2 points. So this is what I'm saying, that we need the spatial dimension into...
Yes.
And really, I think this will be this idea of the super sites or the monitoring sites, etc. At the catchment scale is also the hydrological unit in a way. So, or it's an hydrological concept.
Okay, thank you very much. And I'm asking, you said from... I noted one recommendation. You said the cosmic ray sensor are a very promising new sensor. Is GCOS interested? What do you think?
I hope so.
Did you discuss already with GCOS people? Or?
Not really. I mean, it's still at the research level, but yeah, I hope maybe to have attracted some here. I mean, we do have actually also from the US, from the EIAI, we had a demand of helping them to install about 60 CRS in the Andes and in the Himalayas. So this is very new. This collaboration has just established a few weeks ago. So let's see where this is going to.
So definitely what we need is measurement in high altitude areas.
Yeah.
So I think we have to finish the discussion. So I would like to give you the last word. And the recommendation I noted from your presentation is we need coupling, you said remote sensing data, but data in general with models, high resolution models or different kind of models. And I fully agree that we have to develop more and more. This is done already, but more and more assimilation and combination of data and models. So maybe you have the last word.
So I think I was a bit late on my presentation, so I can be very short. Yes, you're right.
Okay.
And I think it's also, from a scientific viewpoint, this is a clear added value, there is no question, but also this is also one way to meet other people, to stimulate new ideas and so on. So I think this is really, on all aspects, the way to go.
Yes. Okay, so I think we have to stop. The only thing I would like to say is that for the water cycle, and this is the same for the other cycles, there are so many different topics. I suppose that there will be a written document, and we can add more ideas on priorities, recommendations. That we did not address today because of lack of time. I suppose, I hope so, anyway. Yes. Okay.
Thank you again, Annie, for leading this synthesis discussion. And yes, we'll come back to that point of this written document right afterwards. But so far, I can say yes, there will be some document.
So I think I have to stay here.
You can stay exactly. Here. Annie, you can stay here. No, it's actually fine. You can take this seat. So yeah, it's now time for the already mentioned recap session, in which the international speakers will summarize the main messages and recommendations of their cycles, as well as regarding perspectives for services.
Yes, Han, Karina, Vincent Henry, and please join Annie here on stage. And Vincent Henry will be with us via Zoom. It works. I'm baffled. It's great. So thanks a lot at Zentrum Paul Klee. So you have 5 minutes each. Well, you will get a sign, but we won't come and do and pass the word to the next one. So Han, you're first, you're second, Karina, Annie, you are third, and then Vincent Henry will get for the final 5 minute slot. So,
okay, thank you. I will abuse my 5 minutes also to say something general from a GCOS perspective. That I've been quite impressed with all the presentations so far. And I think the organizers have done a really great job on putting this together. And there are quite a few things that I will take back to GCOS in terms of writing the next implementation plan. Just to name two things. One is I think there was a lot of emphasis in trying also to provide more regional perspectives. And that relates not only to the carbon cycle, the water cycle, and the energy cycle. That's something that we haven't done so far. We've taken a very global perspective on things. And it's relevant, I think, to ask the question whether if you start doing that more regionally, what the implications are for the requirements for your observing system. The same goes to some extent also for trying to get towards the actual users of the data and informing more and discussing more with the relevant stakeholders in that. So that's on a general level that I think I will take back. In terms of carbon, I think the key thing there is that for some things we simply don't have measurements at all at a global level at the relevant accuracy, and that's particularly related to soil carbon. And soil carbon is an important variable, both in terms of the amount of carbon that's available for respiration, but also in terms of mitigation efforts where it occasionally drops up. And it's to some extent, if I put it a bit black and white, it's pathetic how little we know about the variability of that particular variable. And I think that's something that we really need to think about hard. It was nice to see the presentation also of the combined oxygen CO2 measurements and the fact that that is now available with a cavity ring down spectrometer at a more commercial level suggests that it can be applied more globally than just at a few research sites, because the oxygen measurements are always very, very difficult and you needed very specialized labs. So I think that's, in terms of instrumentation, is a great innovation. When I put the question to my other people, other speakers, what they thought was the most relevant, they said they didn't really want to make new measurements, but they wanted to bridge the scale between the point measurements that are made by the GAW stations and the vertical distribution of the trace gases, and that's, I think, is also a thing that we need to bring into account when we start discussing the next requirement levels in the IP. There is the question that we saw with the presentation of Dominic Brunner, and that relates to some extent to what I said earlier about going regional. If you really want to develop the CO2 monitoring system that Copernicus is aiming for, what are the real specifications both for the in situ data and for the satellite, and are they similar if you just want to observe the global trends or continental scale trends in CO2 concentration and put that at the relevant. There are some serious modeling studies, I think, required to bring light to that particular question. And that is my 5 minutes, I think.
Thank you very much. So first of all, I would like to echo what you have said at the very beginning, that this was a very impressive 2 days in terms of the information, and one of the unique opportunities to really discuss across all cycles. So for the energy cycle, we had a very lively discussion. And so again, highlighting on the one hand the critical importance of the energy balance, but providing information from at global scale, but also at local perspectives, having a specific focus on the major challenges, particularly for aerosols, for the clouds, and for the Fluxus surface budget. So these are these critical parameters of largest uncertainties for the evaluation for the energy budget, and also provide a link from research to service to society and benefiting from the budget approach. So there had been, let's say, 5 major aspects to highlight here. So the first aspect was the aspect of the maintenance and sustainability. So first is that it had been presented on the critical need of the local effective calibration measurement and reference establishment and their linkage to global activities and global data sets, so the critical importance, which was shown, for example, for aerosol. And also there are specific recommendations which are put out and which need to be maintenance. And so another point which came out here, in addition to what is already listed in the science plan on the specific recommendation for the ECVs, is the evaluation of, or a regular evaluation of recalibration of the historical data sets. So I think that has been highlighted here for the aerosols, but it can be applied to other components, like, for example, in the ocean and other parts, so to increase the stability of those reference measurements. And then the second aspect which was coming up was on the aspect of collaboration and breaking silos. So here there was a specific example provided here on how this could be fostered. This was a specific example to refine the linkage between the in-situ community and the remote sensing community. So here was the example provided, again for aerosols, but I think this is also something which could be extended to most of several variables and could be of major benefit, particularly in defining jointly together and continue defining jointly together the observing system recommendations and the critical gaps. The other aspect was an aspect of innovation, and was an aspect on innovation on the energy cycle, but also applied across all the cycles. So, so here is the idea or the recommendation of exploring new methodologies and approaches, so which could be based on and has been done also in the past, but there is a large cloud of opportunities waiting there, while basing on physical budget constraints within the different cycles, but also across the different cycles. It has been shown in the past for some studies that this can provide reliable, independent information, in particular in the evaluation of understanding sources of uncertainties, and to be able then to go back directly to the precise calibration approach, etc., to improve them. And also here had been this had been also discussed in terms of uncertainties with the aerosols, but another idea when also listening to the session on the water cycle could be to focus on one specific topics. You have seen here today a lot about the mountain area, whether this could be an interlinkage of all cycles with a focus on the mountain areas. And then we have an aspect here of change and variation. So this is an aspect of research need in order to advance understanding the change, and also here to go new pathways, and also, as you were already mentioning, gapping the lag between the global aspects and the very local aspects to really provide information at regional scale and information in the change of time. And my final one is the aspect of knowledge transfer and monitoring and reporting. So there's still a huge gap on the exploitation on how we can improve knowledge exchange, cross from science really going to society. And so there are different discussions which have been said, and also different gaps on define between the different sectors who is doing what and how can they be connected from research, services, assessment and reports, communication experts, etc. So a solution could be here indicators as a melting pot, a question on whether there could be an idea to extend the existing GCOS Global Climate Indicator framework for the cycles, and also here to consider there in this indicator idea the missing variables for the targets and etc. as highlighted, like for example the storage part or some derived information from the cycles. Thank you.
Okay, so I think it's my turn. So I will start with the same sentence as we don't have global measurement at the required accuracy to study the global water cycle, but we have a lot of measurements anyway. And the first point I would like to highlight is recommendation I would like to make is produce consistent data set obtained from different sensors, from ground or satellite, for all hydrological variables in an approach similar to what has been done, for example, in the context of the ESA Climate Change Initiative project. And this should be done. This is already done for some variables, but not for all. This is my first point. My second point or recommendation is cross-validate the existing data set via budget closure studies. I think we did that for sea level and for other for the oceanic content, I think also, etc. And it is very instructive. It allows to detect systematic errors and identify missing contribution, etc. So I would recommend to do that systematically for the water cycle at different scale, local, regional, and global scales. Another point is to improve the spatiotemporal resolution and measurement of some hydrological variables involved in extreme events. I think we all agree that the study of and forecast of extreme events is most important, is crucial. Also, the next point is to improve the measurement of cryospheric variables. This has been commented in the previous session. For example, snow depth, rate of snow melting, glaciers mass change, etc. And also, a point that is connected is improve the representation of the cryospheric component in hydrological modeling. So this is really important. And finally, I would like to end on modeling. We have mostly talked about observation today, but modeling is as important as we need both observation and models. So improve global and regional hydrological models, accounting for all type of forcing, and improve in particular the meteorological forcing precipitation for hydrological models. And finally, the problem of assimilation of data in all kinds of models, except coupled climate models, is certainly the way forward for now. So this is all, but I would like to end in the previous session. We several colleagues highlighted the need for developing super sites, and this is another recommendation: developing super sites with different kind of measurement involved in these all three global cycles. This would be really very important, and this would serve as a calibration site, for example, for satellite data, remote sensing data, and this is my last point recommendation. So, it's all. Ah, okay. We don't hear you.
Sorry, I had started but muted. So it's hard to be fourth because many of the key points I think have been said. One thing I really want to say is how much I've been impressed by the world-class presentations that we had in this symposium, which demonstrate with no doubt the leadership of Swiss scientists and Swiss institutions. And I think it was mentioned that Switzerland plays a role model in our domains, and I think it's fully demonstrated with this symposium. As someone with a numerical modeling background and also with a lot of my attention on satellites, being involved in an Earth observation program, I think the symposium for me has put the finger on the value of acquiring observations here in Switzerland, but elsewhere in the world, because that's from these the ground truth that progress can be made. And I think it was quite revealing to see for all three cycles the gaps that still exist in terms of monitoring and of observations, but also sometimes in terms of unknowns, in terms of coupling in these fundamental big cycles that I think we should know better, but we don't. And actually, for me, my reflection is a bit of an exercise of humility, especially when working in an operationally oriented organization like ECMWF, or thinking Météo Suisse with a task and a mandate to deliver at some point in time, not too distant, operational, actionable, reliable products. And I think this symposium shows that, and this was part of the discussion in the last session, calls for almost a next generation of modeling with integration. You can call it data assimilation, you can call it reanalysis. And this next generation comes not only from the brute force of having faster, better supercomputers, but by the multidisciplinarity which is needed. People cannot be expert of the entire Earth system. So in the past, you had a few people developing a model, having their own initial background. But I think today this calls for much more multidisciplinarity, as it was mentioned, I think, in all the three discussion phases. And that's where I see the coordination role of GAW and of GCOS as super important. It's super important to identify at the global level what are the research gaps where countries that have capacities in the world can focus the work. It's also very important to gather the user requirements and the stakeholder requirements to deliver these next generation of information services. So I want to conclude by saying that we have some opportunities, certainly in Europe, with the Copernicus program. Also, I mentioned in my introduction the program called Destination Earth, and this very attractive concept of a digital twin of the Earth. And by combining these advanced systems, satellite, ground-based observation, I think we can success. And I was saying it's an exercise of humility. It's clearly difficult. There are lots of uncertainty when we think at all these reservoirs and cycles and fluxes that we know very imperfectly. It's not because it's difficult that and that there are open science questions that we should not already walk the way of trying to develop Earth's system and climate information services. And I would take the parallel of numerical weather prediction. So when it started, there were lots of open questions. And nevertheless, because developments and research started so long ago, it's because of that today there are early warning capacity in terms of extreme events. And I think that for Earth system information and climate, we can start working this route. So thank you very much.
Thank you very much. Thank you very much. I was going to say, if we were here all in presence, we would give the international keynote speakers a very warm hand of applause, because they did an outstanding job in trying to give us the framework, to lead the discussions of our national contributions through the topics, and provide the closing panel that is just behind me with an excellent summary. So thank you very much again. It is now time for a very significant moment of the symposium. The national and international scientific expert gave us this panorama I just mentioned. And in addition, we heard about the potential, and I think the history of NWP, of numerical weather prediction, is really a very good example of just doing and investing the energy. So we are now looking forward to the views of representatives of the top management of major Swiss environmental institutions.
The discussion is moderated by Thomas Stocker, Professor of Climate and Environmental Physics at the University of Bern and President of the GCOS Center for Climate Change Research. He served as co-chair of Working Group 1 of the IPCC that provided the scientific basis of the Paris Agreement. And also, and that is something you might not know, he's the chairman of the GCOS Switzerland Steering Committee. So please, Thomas, take it away from here, and looking forward to the discussion.
Thank you very much. Welcome, everybody. It's a great pleasure to chair this closing panel here in the next 40 to 45 minutes of this GAW GCOS Symposium that we just had in the last 2 days. We had a very rich program, as you remember, and the opportunity was really here for us to put the Swiss science effort in these 2 worldwide programs in a global context. That was due to a number of international speakers, which we would like to acknowledge. You've also seen that there is a very rich information available, sometimes confusing because there are so many data, so many time series from so many components of the climate system. But I think during these 2 days we have received and obtained a richer and a better overview of what is available and seen the opportunity, what can be done by these data. So we want to take the opportunity in this closing panel to comment on the relevance of the reported results for the implementation and the further development of the Swiss GCOS and GAW contributions in the future. We also want to assess the role of Switzerland in addressing the grand challenges. What are our contribution to actually bring down the silo approaches that often still are the case and present in the science, the silos either of the components of the climate system or the measurements that are being done vis-a-vis the modeling. And finally, consider the potential societal benefits of these programs and suggesting developments. That's a tall order, and we have assembled here a very high-profile panel. I would like to introduce very briefly the participants here on this panel. To my right is Janet Herring. She is the director of ERWAG. This is the Swiss Federal Research Institute on all that concerns water, if I may say. It's not the official name, but it's about right. To my left is Brigitta Buchmann. She is a department head at IMPA. This is the Swiss Federal Institution or Research Institution of Material Science and beyond. To my farther left is Bertrand Colpini. He is the Deputy Director of Meteo Schweiz. And to my far right is Jürg Luterbacher, the Director of Science of the World Meteorological Organization. And remotely, we welcome now Carlos Capozza. He's a division head of hydrology of the Swiss Federal Office of the Environment. And I just like to check with Carlo whether he can hear us and whether we can hear you.
I can hear you very good.
Very good.
You can hear me?
Yes, excellent. Thank you very much. Okay, so I outlined a little bit the goal of our panel here, and I would like to start or structure the discussion in essentially 4 areas. 3 questions that I will pose to the participants of this panel, but of course these questions are only initial sparks that may actually motivate you to bring up new ideas and your own thoughts that have been forming during the last 2 days. We would also like to give the opportunity to the participants. I have really no clue how many of you are still following this discussion here, but I hope we are at big numbers and we will get a few questions that sort of halfway through we will consult our iPad here and then ask a few questions here. So let me start off with the first question. If we look at these 2 big programs, Global Atmospheric Watch and GCOS, the Global Climate Observing System, I wonder where are the stumbling blocks for these 2 large-scale projects and where are the synergies of these 2 programs when we consider them in a combination, which I think is actually quite an innovative step that we have taken in the past 2 days. So I would like to start asking Bertrand about synergies and stumbling blocks, and then we'll pass on to Janet, and then we go up to the global view of the World Meteorological Organization. Please, Bertrand.
Thank you very much, Tom. Then I could make a sort of history of how Switzerland has evolved into these two programs. Thank you very much, Tom. Then I could go back to a little bit of history of how Switzerland has evolved into these two programs. Global Atmosphere Watch was more the air quality program, initially very much research, instrumental development, but always in this direction, more air quality related. Started in '94. And then 2006, Global Climate Observing System, basically saying all the observation that we do on a sustainable, high-quality level, the ones that are at risk, should continue to be done. But interesting to see, if we project now 2020, that basically those research groups in Switzerland that have been involved in GAW or later in GCOS, they more and more tend to be the same people. And we have sort of the same players around the table. And I would say today, this perspective that WMO has given, more integration, a better perspective of all the environmental cycles, we can think about it and take of this an opportunity with these two programs in Switzerland to come closer. So that would be my message.
Thank you, Bertrand.
Yeah.
From a couple of presentations, we've seen that particularly the water cycle combines the two programs. What is to be said from your perspective? How can we build on the synergies? What are the stumbling blocks that are still on the road?
So I've been very impressed with the last couple of days, and it's very interesting for me to really see the types of research products that are coming out of these two very large projects. And I have to say that I myself am not so directly involved. I think actually Brigitte has more to say about some of the history of this. But it certainly seems to be the case that more and more the different types of observations, whether they're remote observations or ground-based observations or everything sort of in the middle with drones or remote vehicles of any kind, that these are starting to come together to bring a full picture and really to address the gaps. It's clear that we have gaps. We have some gaps that are spatially distributed. We have some gaps that we heard a lot about the gaps in the mountain areas. We have gaps now developing because some ground stations are being abandoned, mainly for cost. And I think that these types of programs offer us a chance to bridge across these different gaps, essentially, and make sure that we have a full record. In terms of barriers, I think that the main barrier is that people just have limited time. Mm-hmm. And, it's a limited attention. That's why I think that combining the Global Atmospheric Watch and GCOS together in a symposium is a really very efficient, for me, way to get both of these to come together. And I think we probably need to do more of that, that even if we have to give up a little bit in terms of our own identity for one program or another, that the benefits of coming together outweigh that.
Thank you very much, Janet. That's already, I think, an important statement towards the future, and also a statement that I take away as a chair of the scientific steering committee of one of those programs in Switzerland. Let's turn to the international perspective. If you, as a Swiss researcher in the past, if you now have your hat on as a science director of the World Meteorological Society, how do you see this whole thing from your perspective?
Thanks very much, Thomas, and dear colleagues and friends. I want to share also the view that these 2 days were very beneficial. It was I was really impressed by the quality and the wealth of the presentations, and that really, as you were mentioning, that these two programs presented together and tried to merge, to link, and show potential fields that can be actually addressed together. And you clearly also mentioned the gaps, the challenges associated to your work at the national scale. And I would like to bridge here also at the WMO, from the WMO point of view. As you know, we serve 193 countries, and none of them maybe is as rich as we heard in terms of monitoring, of modeling capacity, of many issues that make Switzerland actually really unique in this world. So also the WMO, we made this reform 1 year ago. We started and we are still there. And it's really clear that this new WMO has a clear, seamless approach from infrastructure research to service provision. And this in a unique and inclusive way. So what you were mentioning, or what I took, is the same challenges we had at the global scale, even more in, for instance, in developing countries. So the one issue is, that was also mentioned yesterday, is about sustainability. So we heard also today we have a few projects that go 3 or 4 years, and then we have to make sure that we have continuous long time series to work on trends, the detection, attribution, just to have very good data. And we lack a lot of information, of course, in many countries of the world. And there comes the whole value chain of having global data, improving the coverage of geographical data, many issues related to quality of data to make actually predictions and numerical weather predictions more accurate, and also in the long term for climate analysis. And of course, this is the first step to increase the amount of data, to make it much more dense, to go further back in time, quality control, and having better products at the global level, but then we need to transpose them also at the local level. And there comes in what I very much liked in the discussion before. We need to show that our work we do from the research, that it's for the benefit of society in all areas of the world. And I think that's a big challenge also WMO faces, to make this clear science to service approach that reaches everybody in the world, that they are protected against risks and they can be protected from natural and extreme events. So as a global scale, we need to focus a lot on other areas where data is really an issue. We don't have any data, you have maybe some information from satellites. But nevertheless, there is this GBON approach that will be discussed and hopefully approved at the next Congress in 1 month, that really tries to go to these countries and approach for much more data that will actually improve the numerical weather prediction, the climate reanalysis in the future, that will actually then benefit and bring back these results to society to protect them more. So I think Switzerland is a great, unique opportunity and example how the program really worked together. And I think on a global scale, we have many other issues we have to solve. And to services, that's an important aspect. And what has been mentioned also is the knowledge transfer, capacity development approaches just to reach those that have not the possibilities as a rich country in Switzerland. So that's for the moment. Thank you, Thomas.
Thank you very much, Jörg, for this perspective. We will come at the end again to the question, what can Switzerland and its research programs do for the world, for the other parts of the world where we really have large spatial gaps in the information. But before turning there, I'd like to look at another aspect of stumbling blocks or synergies, and that is technology. I think we have seen during these 2 days that measurements and measurement devices become more and more sophisticated on the one hand side, but on the other hand, we also see that commercial devices are available to provide us with great measurements and time series that we haven't had access to before. So my question goes to Nina Buchmann, to Brigitte Buchmann. I'm sorry about that. To tell us a little bit about your perspective with the background of an extremely technological infrastructure that you have available, where you not only use these devices but also develop these devices. Where can you see synergies, and where can you see, from your perspective, still stumbling blocks for these two programs? Brigitte, please.
Thank you. I mean, stumbling blocks, I would say stumbling blocks, I would more like benefit from each one of the programs to the other one. But first of all, as Janet mentioned, I would like to say I really was very impressed about the 2 days. As Janet mentioned, I was rather with the program from the very beginning, and I liked very much these days, and I thought that the programs or the Swiss contribution improved dramatically, and I congratulate Meteo Swiss for this joint meeting. I think this is actually what we need. We need working together in different groups, not only between the different cycles, but only between the modelers and the measurement. And I really think both of these activities are very important, and also the integration of all the things are very important. Coming to Thomas' question, yes, I think Switzerland can contribute a lot in developing new instruments. As you probably know, there are instruments developed in Switzerland doing the normal measurements. I think it was possible to have startups in this field, which is also great. I think we have developed in Switzerland measurements with special possibilities, thinking about isotopes, for example, or also putting instruments on balloons, having water vapor profiles, which is also something which is very important. And I think those developments in Switzerland, they can help later on the global programs and have an impact on global scale also, I hope, I guess. Thank you.
Thank you, Brigitte. Speaking of stumbling blocks and synergies, I think we also need to look at the international component, and their calibration and comparability comes in. And that would be my question to Carlo, who represents the Swiss Federal Office of Environment. Your office is in close contact to other offices of different countries, and so my question is, what is your perspective on this comparability? We collect data, but at the end of the day, we would like to merge them with other time series from other countries to get a larger signal that can be interpreted regionally, continentally, and globally.
Thank you very much, Thomas. I think it was very interesting for me to follow the discussion, in particular the recommendations. I wrote about 10, 12 recommendations on the part before, and I speak now about something that we are creating in Switzerland. We have the assignment of the Swiss government to develop monitoring, forecast, and warning for drought. And that's very interesting because the recommendation done of the experts of these groups are completely matching with the challenges that we are dealing with in our working group. The working group is composed by Meteo Swiss, Föhn, Swiss Topo and VSL, and we have the assignment to write a concept and to show the Swiss government how that we want to deal with monitoring and forecast and warning for droughts. Therefore, I think the perspective shows very good that what we need this perspective. We have now the problem nowadays. We can do warning, we can forecast and warning for droughts on a Swiss scale, on a very regional scale. But what the stakeholder needs are information on a local scale. Therefore, we have to improve the research in order to reach this local scale. And the second point in this warning and forecast for droughts is this integrative approach based on satellite monitoring, measurement in situ, and modeling. What we follow with Swiss Topo, Meteo Suisse, and Föhn is to integrate these three ways to measure or to model to have a better prediction of soil moisture that is an important component for the forecasting of drought. Therefore, you see, we are working on this element and we are dealing with these challenges that are exactly corresponding to the recommendation. We need this regional local perspective. We need a discussion with the relevant stakeholder to get out what they need, what services they really need concerning drought, the difference to, for example, to flood. And we need this coupling of data, measured data with models. That's what an example of one topic that we are now working about at the Confederation. And I think that shows very well the importance of this work done in GCOS and GAW.
Thank you, Carlo. Before I move to the second question, I would like to remind the audience who follows us on the internet that there is the opportunity to ask questions. So please post your questions. They will be collected, and then we have the opportunity here to read them on an iPad and ask the participants of the panel. I'd like to take up a keyword that Carlo just mentioned, and that is monitoring. Monitoring, as we all know, is the essential task of those who would like to make a statement about change. And these programs, as we have seen, serve an important role in quantifying the change that we see in the climate system, not only due to anthropogenic causes, but also the natural variability. Many of these time series inform us for the first time about natural variability. So if I look around at this panel, I see representatives of federal offices, federal research institutions, no representative of a research university, because usually they don't really do the monitoring, or they say we don't do monitoring. So the question now to you is, how do you see your role in helping secure monitoring efforts that I think as researchers, scientists, and as citizens, we all want to see time series for a long time, homogenized, reliable, and steady?
Well, the answer is very simple. That's our mission. we are there for that, actually. As a public agency, we are there to make sure those long-term time series and their quality is really our core business. During those 2 days, for me, one thing that was coming again and again is, if Switzerland wants to do better, Switzerland goes global. We have really to reconsider where we contribute on a global scale, because many of the solutions we have for those long time series in Switzerland do exist. Now the question is, where can we help do a better job on the global scale? On the other side, back to what you said, Carlo, this water cycle and the example you have given, all this discussion with you, Sonia, the evapotranspiration, this is something we have to do. I mean, I cannot, in 2021, stay where we are. So here, Switzerland can do better. Also very interesting, your contribution about this snow water equivalent in the Alps. Incredible to think that we're still so poor in terms of quality assessment of what we have as snow water equivalent in the Alps. So here, a must for this evolution. So those were 2-3 ideas. Give the words to someone else. Yeah.
Thank you, Bertrand. Closing the cycles, I've heard below your words. Closing the cycles. The cycles are not really closed. The budgets are not known.
Thank you.
Brigitte.
To see really the changes, we need long-term measurements, we need reliable measurements, and we need comparable measurements. And I think this is really important. This is a statement, I think. To your thing, our institution is a research institution, and unfortunately, we do also not get money for monitoring. But thanks to Föhn, for example, they support research projects where the monitoring data is needed. For example, as you remember, the emission estimate concept Dominic presented yesterday. We get a little bit money, but this is always connected with research programs. And I think this is really essential. If we want to contribute for long term, there we need continuous sustainable funding. Otherwise, it's very difficult, very dangerous also. And I mean, Switzerland is also contributing to European research infrastructure, and also there, if we want to play the role we have right now, to be upfront a leader in setting up these programs, in evaluation of these programs, Switzerland must have the possibility to contribute long-term to these programs. As free programs, ICOS, Actris are keywords we heard the last 2 days, but also Copernicus is a second or a third keyword which has to be mentioned in this connection.
Thank you, Brigitte. We have heard from one federal office a mission statement. What is the mission statement regarding monitoring of the other federal office that we have on the panel, and that is the Federal Office of the Environment? Carlo.
Yeah, exactly. For us, it's the same as Mr. Calpini said, the relevance of high quality, long-term, systematic data record. Our problem, now we are trying to digitalize our data record since 1900 in order to have a longer, long-term data records in order to better understand also the statistical meaning of the single events, to better also forecast what an extreme event is. But our problem today is that we miss a little bit some standard to make this re-digitalization or digitalization of our data. Our data are principal water depths and water flow. But now we decide to better or to work closer with Meteo Swiss in this aspect of data quality. But there is a lot of data. The personal and financial resources to deal with this data are limited, and therefore we have to try to have some systematic to deal with this very important number of data. That's the problem we are dealing with, and that's auch, I hope that the researcher, but also I hope that our partner, Meteo Swiss, that we can have a little bit an harmonized standard. And that's what we are now dealing with. We are in the first phase of this digitalization. It means we digitalize the so-called limnigramme. But now when we go into the second phase, that means that we try to make an output. Then we had to decide what we need really, which precision, and then also how can we compare the measured data since 1972, the digital data, with the data before 1972. That's the problem we are dealing with, and I hope, and I get a lot of inputs of this discussion with researchers, and I hope we can have some help to reach a standard that is for us satisfying. That's our problem now.
Thank you, Carlo. Thank you. Turning to Janet, if we talk about long time series, there are also some very short time series that show some surprises. New substances, for example, in the water. How does that fit into GCOS or GAW?
So, that's a very interesting question. I think one of the interesting things that I'd like to come back to from the last comment is that we have more and more possibility to populate databases with information. And this idea of developing a consensus or standards, I think this is a really critical thing. And also the open data movement is something that will really help to allow everybody to contribute to a longer term record, even if that record is somewhat put together from different sources. And I'd just like to say, it's one thing for universities to say, well, this is not our job, but one of the most important records that we have is the Keeling curve. And that was from a university. Yes. Right? So I think we have to recognize that there are a lot of opportunities to feed in if we have really high quality data and if we're willing to do the work to make that data available, right? So coming to the new substances, I think here, and this is something for Switzerland, as well as keeping longer term records going, we want to make sure that when new issues emerge or new substances emerge, that we can bring those in a way that is somehow comparable or speaks to the historical data as well. And this is always going to be the case. We'll always have new substances coming in.
Thank you, Janet. Brigitte.
Yeah, also in our case, I mean, finding new substances which maybe are produced by industry, and if we can identify these substances, we have a feedback loop then to the measures to reduce these compounds, and we have a basic information for the next generation of the protocols.
Thank you very much. I just look at this iPad here that has a question by Tom Peter, which is addressed to Bertrand. He asked, it has been said that joint GAW GCOS symposia are fruitful and efficient. I think we've seen that blatantly. I fully agree with that, he says. However, some of the discussions sounded as if we might consider merging GCOS and GAW altogether. Certainly there are synergies that are perhaps sometimes so close that even a merger would make sense, but for most part, both programs have their own nature and merit. What is the panel's opinion on this? Bertrand.
Thank you very much. We talk about synergies. We don't talk about merging. This is just an opportunity to become more clever, more efficient, to lower the number of proposals, the research programs in Switzerland. I mean, the partners you have to submit. You submit once in Meteo Suisse. We work together, but at the end, we have two programs. They have different goals and objectives. So synergies, but not merging. By the way, synergies with the Fern, Carlo, many thanks for your mentioning this combined work together, Fern, Meteo Suisse, one database together for the hydrology and for the meteorology. This is just bringing synergies and more efficiency into the public administration. And we are there as a bridge to the research. So when the research has wonderful database and long-term database, we are there in support and as a bridge for this. Yeah, thank you.
Any opposing or complementary views on this question by Tom Peter here? Otherwise, I move to the second and last question here from the audience by Frank Paul. And I think that question is addressed to a higher level in the Swiss administration. So, Carlo, watch. Is there a chance that Switzerland joins Copernicus at some point? They provide money for longer-term monitoring. Carlo, over to you.
Yeah, that's an important question. I think there is some movement in the federal administration concerning Copernicus, but the point is ever the same. Who paid? Many office has an interest, but is the question. I hope.
I just
but
like,
that's is to say. You say, Thomas, it's an higher level that I know that. I can only say there is some movement in this question, there is something going on, but the direction in which it will go on, it will be the Swiss government that will decide.
Thank you very much, Carlos. I just have to add one point here. Since we are just among us and it's a family together, GCOS plus Global Atmosphere Watch, I'm allowed to say that it's a vital need, this contribution and partnership into the Copernicus. At the political level, it's an issue, but it is a vital need for our community. Thank you.
Thank you, Bertrand. I heard that very clear and loud. It's important to say that we're not an island. We are embedded in a world community. And that brings me to the last question here. We have just 5 minutes left. We have heard several times that Switzerland is an exemplary role model in GAW and GCOS science and observations. how can we reach out? Do we need more detail here in our country to measure in even finer grain resolution? Or is there not an opportunity to reach out beyond our boundaries? We have already touched upon that. And so my first question goes here to Jörg Lutherbacher from the WMO. You have the global view. How do you see Switzerland as a potential contributor to boosting observational databases to fill gaps that are so open and so wide? We have seen that in the first day in some overviews. We don't really know what's going on in the climate system to the detail that we know in Switzerland.
Thanks very much. I think the world can learn a lot from Switzerland, this for specific reasons. So it's really the spirit, the brain behind all this research, the collaboration, solution-oriented, the use of synergies we heard, the data stewardship, how you deal with the data exchange, FAIR principle, the joint collaboration, interdisciplinary approach that come up, and also the integration. And I think the next step is maybe to make more clear or more what has been discussed before, the step from the research to operationalization, which is a strong argument in WMO. So we need to make sure what the research to service component, and what I think the world can also learn is the way how the Swiss research is working together with stakeholders. So this mutual benefit, this collaboration, this interaction. So I think there's a lot to learn from Switzerland. So I would see it as a unique country that will feed back to the global view of a really an example that shows on many avenues how really research is working towards approaching these two programs.
We have also heard that individual institutions have quite vigorous programs in certain spots on the globe, and so I think we shouldn't forget that they can operate as seeds to bring this information into other regions of the world. Any other views on this issue? Please, Janet.
So I think one thing that's really important is capacity development in partner countries, especially in the Global South. I heard somebody, I think from PSI, saying that in the Global Atmosphere Watch that they were in Africa. Mm-hmm. Maybe I took that away from Ricky, sorry. But ELMAG also has a lot of activities that are with partner countries, with partner institutions, and where people can go back and forth between the different countries. I think this is really critical. It's not just that we need those measurements in different parts of the world. We need scientific capacity in those parts of the world. It needs to be the local capacity, not just imported. Yeah.
Thank you. Very good. I think we have come to a close of this very interesting panel. I would like to thank all the participants to bring in their thoughts. I hope they have been registered and noted in a final document that would be available, I have heard. For me, these 2 days have been extremely exciting. We have looked at these two programs from a different angle, from the 3 cycles, water, energy, and carbon, and I think that is the right way to look occasionally at these programs, to open up the silos, to see opportunities, to realize synergies, and to feed in the next level of the implementation plans. So thank you very much for that, and I hand over to the 2 moderators here who join us on the stage. Thank you.
Thank you very much. We have well noted everything which has been said during these 2 days and also now during this closing panel discussion. So thank you very much, Thomas, for the moderation. Thank you. We have arrived at the last item on our agenda, but before handing over to Bertrand for his final words, a few last things from our side.
First, we would like to briefly outline how we intend to make best use of everything which has been said in the past 2 days. To be specific, Meteo Swiss plans to publish a white paper before the end of the year, which reports on the main outcomes of this symposium. In addition, it will outline the main recommendations on where future collaboration should focus and engagements of the Swiss GAW and GCOS programs could be strengthened. This white paper is planned to appear by early December, and of course we will announce its publication on various channels.
When we started the organization of this symposium, it was still possible to meet in person in a group of 10 people in a very narrow room at ETH Zurich without wearing any masks. This too as information for you to get to know how long this organizational process actually took. So we have already thanked the scientific program committee at the very beginning of our symposium and all the speakers and moderators as we did go along. However, our organizational team remained behind the scenes so far. In this respect, a big thank you to you, Isabel Werner, she's up there, to Loic Rickenmann here in the room, but also to Alicia Page and Anna Schmid, who were involved in the organization as well.
Also a big thanks to all of you who have participated. We really thank all the poster presenters who took the time to prepare the posters along with the poster pitches. And thank you for your flexibility and willingness to participate in a virtual symposium, for all your inputs and perseverance to stay online until the end. And last but not least, we thank the whole team of Zentrum Paul Klee, who helped us with the considerable complexities of the virtual setting. You really did an amazing job. Thank you very much.
And for all of you who have missed out on some presentations or who would like to recall what has been said during these past days, we will provide all the presentations and also a recording of these past 2 days on our website for you to revisit. With this, we say goodbye.
Have a nice evening.
And a safe journey home in case you have to go home.
And Bertrand, I think this is one last time. The floor is yours.
Thank you so much. And this goodbye event is an event to say thanks to the people behind the scene and in front of the scene. So I really would like to invite all of you who have been directly contributing. Please come on the stage. It's important for everyone to see the staff for the organization, the technician, and just come on the stage. Come with me. And my final word is a word dedicated to Paul Klee. Actually, we are here in a center of creativity and ideas, and this is what I like over the last 2 days. So I'm just talking and talking to make the people move on the stage as fast as possible, because I'm sure you're tired as remote auditors, but it's good for you to see once. Please come in front. Yeah, I'm in the back. Just go there to see everyone. And now you understand the importance of that effort. Thank you very much. Thank you so much, and see you sometimes later. Thank you. Goodbye. Goodbye to all. Thank you very much. Bye-bye. Merci beaucoup.
Super. Excellent. Dank.